Welcome. Over the next 5 hours, we're going to cover the operational side of system design, the knowledge that becomes essential as you grow into senior and staff level roles. This is the material that comes up in senior interviews and it's the same knowledge you gain from operating real world systems at scale. At the senior and staff level, interviews go deeper into how systems actually run in production. Interviewers will ask you about topics like observability, which is how you know whether a system is healthy right now. They'll also ask you about deployments, which is how you roll out changes safely to millions of users. They'll also ask you about distributed tracing, which is how you follow a request across, let's say, 15 microservices in a distributed system to find something where a bug or an issue has occurred. And they'll also ask you about cost, which is like how your architecture decisions affects infrastructure budgets at scale. Now, here's exactly what we'll cover in today's 5-hour course. We start with observability and distributed tracing, which covers structured logging, correlation IDs, metrics, SLIs, and how to trace requests across microservices. This section will run for 55 minutes. Then we'll spend 50 minutes on deployment strategies and safe releases, which will cover topics like CI/CD pipelines, rolling updates, blue-green deployments, Canary rollouts, feature flags, and rollback patterns. After that, we'll spend 40 minutes on security, design, and API protection. So that will cover topics like authentication, authorization, secrets management, zero trust architecture, and rate limiting. Then we'll spend 35 minutes on cost-aware system design, which covers topics like right-sizing compute, reserved versus pod instances, storage tiering, and reducing data transfer cost. After that, we'll spend 35 minutes on global scale and multi-region architecture, which will be covering topics like replication strategies, global load balancing, regional failover, and data sovereignty. And after that, we'll spend 30 minutes on failure handling and recovery patterns, which will cover topics like detection, response, communication, and postmortems. After that, we'll go through 3 real-world case studies for 45 minutes, which will cover social media feeds, payment processing, and real-time chat examples, and we'll apply everything how it's done in real-world production systems. After that, we'll finish it with roughly 20 minutes of interview playbook, which covers exactly how to talk about these concepts in senior and staff level interviews. Now let's talk about our first section, which is observability and distributed tracing. This is all about understanding what your system is exactly doing. So you cannot fix what you cannot see. And you cannot optimize what you cannot measure. Observability is not optional in production systems, it's actually super important. The diagram here shows the flow. Logs feed into metrics, which feed into traces, which inform the alerting, which drives the dashboards. These components work together to give you a complete picture of system health. Looking at the table here, we have 3 pillars of observability. The first pillar is logs, which captures the discrete events. You use the logs for debugging specific issues and maintaining an audit trail of what happened. The second pillar is metrics, which capture aggregated measurements over time. You use metrics to understand trends and to power alerting. The third pillar is traces, which capture the journey of a request across multiple different microservices. And you use traces to understand the performance and dependencies. Each pillar has strengths and weaknesses, so logs have high cardinality and are great for detail but expensive to store and search at scale. Metrics are cheap to store and fast to query, but they lose the detail through aggregation. Traces show the full picture of a request, but they are expensive to collect for every request. The key insight in this part is that you cannot fix what you cannot see. Observability is not optional in production, there is a foundation for everything else. When an incident does happen, observability is what tells you to know how to understand the problem. When performance degrades, observability is what lets you identify the bottleneck. When someone asks, okay, what happened in a postmortem, observability is what lets you answer those questions. Now let us start with logging, specifically structured logging. The format of your logs matter enormously for how useful they will be at scale. Let's look at this unstructured log example. It says something like 2025, 115, 2023, 45 error, payment failed for user, order number, amount, reason, the card declined. This is human readable, which seems good, but let's think about querying this. If you want to find all payment failures for user, let's say 1, 2, 3, 4, 5, you need to write a regex that parses this specific format. And for every team formats, they log differently, so you need different regexes for different microservices. Now, if you look at the structured log example here, it is JSON with explicit fields, timestamp, level, message, user ID, order ID, amount, currency, reason, trace ID, service, and host. Every piece of information is in a named field. The advantages are significant. If you want to find out all the payment failures for user 1, 2, 3, 4, 5, you can just query where user ID equals to 1, 2, 3, 4, 5 and the message equals payment failed. If you want to aggregate error counts by reason, you can just group by reason. Want to correlate with traces, then you can just do a join operation on the trace ID field. The data is queryable, filterable, and aggregatable without any parsing. Modern log aggregation systems like Elasticsearch, Splunk, and Datadog are built for structured logs. They can index each field separately, enabling fast queries across billions of log entries. With unstructured logs, you lose all of those capabilities. So the key takeaway is this. You should be always using structured logging in production. The small additional effort to format logs as JSON pays enormous dividends when you need to debug an incident. Now let us look at how to implement structured logging in Python using the struct log library. First, we configure struct log with processors. The timestamper processor adds ISO formatted timestamps to every log entry. The JSON render processor converts the log to JSON format. We set the wrapper class and context class and specify a logger factory. The key feature of struct log is bound loggers. So when we call logger.bind with user ID, order ID, and amount, we get a new logger that automatically includes those fields in every subsequent log entry. This means we do not have to repeat these values in every log call. Looking at the process payment function here, we first create a bound logger with the context for this payment. Then we log the payment started, and then because we have bounded the user ID, order ID, and amount, those fields are automatically included in the log entry without us explicitly adding them. If the payment succeeds, we log payment succeeded and include the transaction ID. Again, user ID, order ID, and amount automatically included from the binding. If the payment fails with the card declined error, we log payment failed with the reason and error message. The bound fields are still included. The result here is consistent. Structured logs, we know where every entry for a given payment has the same context fields. When you're debugging why a specific payment failed, you can filter on order ID and see the complete story. So the key takeaway is that you should be using a structured logging library like structlog rather than building JSON formatting yourself. These libraries handle the details and make it easy to maintain context across related log entries. So knowing the format is one thing, knowing what to log is another. Let us talk about what events you should capture and what fields to include. Looking at the always log table here, we have 5 categories. First is you log when a request is received, including the method, path, user ID, and trace ID. Second, you log when a request completes, including the status code, duration, and trace ID. Third, you should log when an error occurs, including the error type, error message, and stack trace. Fourth, you should log when external calls are made to other services, including the service name, endpoint, and duration. Fifth, you log business events like orders created or payment processed, including the event type, entity ID, and relevant data. Now let's look at the never log table because that is equally important. You should never log passwords ever under any circumstances. You should never log credit card numbers as this violates the PCI compliance. You should also never log SSNs or government IDs as this violates the privacy regulations. You should also never log API keys or secrets as this creates security risk. And you should also be very careful about logging full request bodies because they might contain PII, which is the personal identifiable information about users. So tension here is real. You would want to have enough detail to debug issues, but you also cannot log sensitive data. The solution is to be explicit about what you log. Do not log entire objects blindly. You should log specific fields that you have verified are safe. So the key takeaway is this. You should log the events you need for debugging and auditing, but be intentional about what fields you include. When in doubt, you should leave it out. Now let us look how to handle sensitive data and how to use log levels appropriately. The sanitize function shows a pattern for redacting sensitive fields before logging. We maintain a set of field names that are sensitive: password, credit card, SSN, ABI key, and token. The function recursively walks through a dictionary. If it encounters a key that matches a sensitive field, it replaces the value with redacted, otherwise, it keeps the original value. The log request function here shows this in practice. We build a dictionary with path, method, body, and headers from the request. Then we pass it through the sanitize before logging. Any sensitive fields in the body or headers will get redacted automatically. Now let us talk about log levels. Debug is for detailed information useful during the development but should not be enabled in production due to volume. Info is for normal operations and business events, the standard production level. Warnings for unexpected situations that were handled successfully, like a retry that eventually succeeded. Errors for failures that need attention, like the payment that failed. Critical is for situations where the system is unusable, like a database connection that cannot be established. The key to log levels is consistency. If one team logs every retry as an error and another logs them as a warning, your alerting becomes unreliable. You should establish team or organization-wide standards for what constitutes each level. So the key takeaway here is that you should sanitize sensitive data before logging and use log levels consistently so your logs are meaningful at scale. When a user reports a problem, you need to find the relevant logs. In a system with 100 microservices and billions of log lines, how do you find the needle in the haystack? The answer is correlation IDs, also called as trace IDs. Now here's the problem. A user says, let's say my order failed. Now let's say in your company you have 100 microservices, each producing thousands of logs per second. So which log entries are relevant to that user's specific order? The solution is to assign a unique identifier to each request at the edge and propagate it through every second service that handles the request. Looking at the diagram here, a request enters the API gateway with, let's say, trace ID ABC123. When the API gateway calls the order service, it passes along the trace ID ABC123. When the order service calls the payment service and inventory service, they both get trace ID ABC123. And when payment service calls the bank API, it passes the trace ID ABC123 as well. Now every log entry from every service includes this trace ID, which is ABC123. So when you query for that trace ID, you get the complete story of that request across all microservices. You can see it enter the API gateway, then it went to order service, called payment, which called the bank service, and called the inventory service, and where exactly things would have gone wrong. The query is pretty trivial. Trace ID equals to ABC123. The result is every log line for every service from your system for that one specific request. What was a needle in a haystack problem now becomes a simple filter. So the key insight is this. Correlation IDs turn distributed debugging from an impossible problem into a straightforward query. And these are essential in any microservices architecture. Now let us look at how to implement correlation IDs in practice. We use a context var to store the trace ID for current request. Context vars are Python's way of maintaining request scope state that is accessible anywhere in the call stack without passing it explicitly. The trace ID middleware over here, which runs on every incoming request. So first we check if the request already has an X trace ID header. If it does, we use that value, which means this request came from another service that is already part of a trace. If there is no header, we generate a new UOID, which means this is the start of a new trace. We store the trace ID in the context var, so it is available anywhere in this request execution. Then we process the request. Before returning the response, we add the X trace ID header so clients can reference this trace in support tickets. The getLogger function returns the logger with a trace ID automatically bound. Any code that calls getLogger gets a logger that includes the trace ID in every entry. The process order function shows how this works in practice. We get a logger which automatically includes a trace ID. When we call the payment service, we explicitly as a trace ID in the X trace ID header. This is how the trace propagates across different services in your system. The receiving service does the same thing. Extract the trace ID from the header, store it in a context var included in all logs. The chain continues through as many services as the request touches. So the key takeaway is that you should be extracting trace IDs from incoming headers or generate new ones, store them in request contexts, include them in all logs, and pass them to downstream services. Now let us move into metrics. So while logs capture individual events, metrics capture aggregated measurements. There are different types of metrics for different purposes. A counter is the simplest type. It counts events and only goes up. Looking at the examples, request total counts total request, error totals counts total errors, orders created counts how many orders have been created. Every time a request comes in, we call request total.increment, which is to increment the counter. Counters are useful for rates. If request total goes from 1000 to 2000 over 10 seconds, your rate is 100 requests per second. Your monitoring system calculates these rates automatically. A gauge measures the current value that can go up or down. Looking at the examples, active connection tracks how many connections are currently open. Queue depth tracks how many messages are waiting in the queue. Memory usage bytes track current memory consumption. The difference from counters is that gauges represent instantaneous state. When a connection opens, we call active connections.increment. When it closes, we call active connections.decrement. At any moment, the gauge tells you the current value, not a cumulative total. Gauges are more useful for saturation metrics. So for example, is your connection pool full? Is your queue backing up? Is the memory pressure high? These are questions related to gauge. So the key takeaway is that you should be using counters for events that happen, using gauges for resources that have current state. Getting that right makes your metrics meaningful. Now let us continue with histograms, which are the most powerful but most complex metric type. A histogram tracks the distribution of values across predefined buckets. Looking at the request duration histogram, we define buckets at 10 milliseconds, 50, 100, 250 milliseconds, 500 milliseconds, and 1 second. And after that, 2.5, 5, and 10 seconds. When a request completes, we observe its duration, and the histogram tracks how many requests fell into each bucket. So why buckets? Because averages actually are not the right way to look at things sometimes. If 99 requests take 10 milliseconds and one request take 10 seconds, the average will be 109 milliseconds. That sounds acceptable, but 1% of users are having a terrible experience with 10-second latencies. Histogram lets you see the full distribution. The response size histogram shows another use case, tracking response body sizes across buckets from 100 bytes to 1 megabyte. In the handle request function, we record the start time, process the request, then observe the duration and response size. Each observation updates the appropriate bucket counters. Histograms enable the percentile calculations, so P50 is the median, where half of the requests are faster. P99 is the 99th percentile, where 99% of requests are faster. These are far more meaningful than averages. Now that we understand metric types, we should talk about what to measure. The RED method provides a simple framework for service level metrics. RED stands for rate, errors, and duration. Rate measures requests per second, how much traffic you are handling. Error measures failed requests per second, how many things are going wrong. And duration measures latency distribution, which means how long requests are taking. Now, if you look at the table over here, rate is measured in requests per second, which is, for example, 1000 requests per second. Errors are measured in errors per second, which is like 5 errors per second. And duration is expressed as percentiles, which is P50 equals 50 milliseconds and P99 being equal to 500 milliseconds. The implementation shows how to capture RED metrics using the Prometheus client libraries. For rate and errors over here, we use a single counter called HTTP request total with labels for method, endpoint, and status. Rate is the total count. Errors are the subset where status is 500 or higher, so your monitoring system can calculate both from the same counter. For duration, we use a histogram called HTTP request duration seconds with labels for method and endpoint. In the handle request function, we record the start time, process the request, then increment the counter with the appropriate labels and observe the duration in the histogram. So, why red? Because these are three important metrics answers the most important questions about a service. Is it handling traffic? Is it returning the errors? Is it fast enough? So if you only track these three things, you should track definitely them. So the key takeaway is that you should be implementing red metrics for every service. They give you a baseline understanding of service health with minimal effort. Focuses on request, use focuses on resources. The use method helps you understand the infrastructure health. Use stands for utilization, saturation, and errors. Utilization measures the percentage of a resource being used, like CPU at 75%. Saturation measures work that is waiting, like a queue depth of 100. Errors measures error counts, like 5 disk errors. The table shows how to apply use to different resources. For CPU, utilization is percentage used, saturation is load average, and errors are not really applicable. For memory, utilization is percentage of RAM used, saturation is swap usage, and errors are OM kills. For disk, utilization is percentage of capacity, saturation is IO queue depth, and errors are disk errors. For network, utilization is bandwidth used, saturation is packet drops, and errors are connection errors. So the last two rows show that the use applies to software resources as well. For a thread pool, utilization is active threads divided by total, saturation is queue depth, and errors are rejected tasks. For a connection pool, utilization is connections in use divided by the max, saturation is wait time for a connection, and errors are connection failures. The power of use method is that it gives you a systematic way to analyze any resource. When something is slow, you can walk through the use metrics for each resource is involved. For example, is it highly utilized? Is it saturated? Or is it producing errors? So the key takeaway is that you should be combining red method for request level health with the use method for resource level health. Together, they cover most of what you need to understand system behavior. Now, red and use methods, they cover generic patterns. But for every application also has domain-specific metrics that matter for the business. Looking at the business metrics examples here, we have counters and gauges for business events. Orders created tracks the total orders created. Order value is a histogram tracking the distribution of order values in dollars. Orders by status is a counter with a status label, so you can track orders by their current status. For users, we track sign-up as a counter and active users as a gauge. For revenue, we track total revenue in cents as a counter. Using cents avoid floating point precision issues. The dependency metric section shows how to track external service calls. External calls is a counter with labels for service, endpoint, and status. This lets you see call rates and error rates broken down by which service you are calling. External duration is a histogram for tracking latency to each external service. The circuit breaker state gauge is interesting. It tracks the state of each circuit breaker, 0 for closed, 1 for open, and 0.5 for half open. This lets you see at a glance which circuits are tripped and you can alert when a circuit opens. The key insight is that application metrics should reflect what matters to your business. An e-commerce site cares about orders and revenue. A social network cares about posts and engagements. A payment processor cares about transactions and settlement times. So the key takeaway is that beyond read and use, identify the metrics that are specific to your business domain and instrument those. These are often the most important metrics for understanding whether your system is doing its job. Now let us go deeper on percentiles and service level indicators. These concepts are essential for understanding the real user experience. Looking at the example, the average latency is 100 milliseconds. That sounds fine, but if you look at the percentile breakdown, P50 is 50 milliseconds, meaning half of requests are faster than 50 milliseconds. P90 is 100 milliseconds, P99 is 2000 milliseconds, and P99.9 is 10,000 milliseconds. Now the average is misleading because it hides the tail. At 1 million requests per day, P99 of 2 seconds means 10,000 requests takes over 2 seconds. P99 of 9 of 10 seconds means 1000 requests take over 10 seconds. Those are real users having terrible user experiences, and the average actually hides them. So service level indicators or SLIs are specific measurements of user experience. The table shows 4 common SLIs. Availability is a percentage of successful requests with the target SLO of 99.9%. Latency is a P99 response time with a target of under 500 milliseconds. The error rate is a percentage of 500 errors, 500 HTTP responses with a target of under 0.1%. Throughput is requests per second with a target of over 10,000. SLOs are the targets for your SLIs. They define what good enough means. So an SLO of 99.9% availability means you're committing to succeed on 999 out of every 1000 requests. So the key takeaway is that always look at the percentiles, not just averages. Define SLIs for the metrics that matters to users and set SLOs that reflect the experience you would want to deliver. Now let us look at how to calculate SLIs and how to use error budgets. The availability SLI is calculated as the sum of requests where status is under HTTP 500 and divided by the sum of all requests times 100. In PromptQL, you can express this by using rate functions over your request counter filtering by status code. The latency SLI can be expressed as a percentage of requests that complete within your target or as a raw percentile value as well. The histogram quantile function in PromptQL calculates the percentiles from histogram buckets. The example calculates P99 latency over a 5-minute window. Now let us talk about error budgets, which are a powerful concept from site reliability engineering. If your SLO is 99.9% availability, you are allowed 0.1% of downtime. Per month, that is about 43 minutes of downtime. Say it's mid-month and you have already used 30 minutes of downtime. Your error budget remains as only 30 minutes. So now what should you do? The answer is to slow down risky deployments and to focus on reliability. Your error budget is almost exhausted, so you cannot afford to take risks that might cause more downtime. Conversely, you should also, if you have barely touched your error budget, you have room to take more risks, ship faster, experiment more. Error budgets gives you a quantitative way to balance reliability against velocity. So the key takeaway is that calculate your SLIs consistently, track them against your SLOs, and use error budgets to make informed decisions about risk and deployment velocity. Now let us move to distributed tracing, which is the third pillar of observability. While logs tells you what happened and metrics tells you how often, traces tell you the full journey of a request. Now here's the problem. A user reports that checkout is slow. Without tracing, you do not know which service is slow. Is it a database? Is it the network latency? There are 10 services involved and you do not know where to look. With tracing, you can see the exact path of a request. You can see how much time was spent in each service. You can identify the bottleneck immediately. Looking at the diagram here, a trace consists of spans. The parent trace ABC123 contains a span for the API gateway that took 5 milliseconds. Inside that, there is a span for order service that took 100 milliseconds. Inside the order service span, there is a database query span that took 80 milliseconds and a payment service span that took 50 milliseconds. Inside payment, there is an external API span that took 45 milliseconds. The hierarchical structure shows you not just the total time, but where that time was spent. In this example, the order service took 100 milliseconds total, but 80 milliseconds of that was just in the database query. So database is your bottleneck. So the key insight is this. Tracing gives you a complete picture of the request flow that logs and metrics cannot just provide. So when you need to understand why something is slow, traces are your primary tool. Now let us define the components of a trace more precisely. Looking at the table here, a trace is an entire request journey identified by the trace ID. A span is a single operation within the trace. The parent span is the calling operation. The child span is the operation being called. Tags are key value metadata attached to a span. Logs are the events that occurred within a span. The span example shows that what a span looks like in JSON. We have a trace ID ABC123 which ties this span to its trace. We have a span ID span 456 which uniquely identifies this span. We have a parent span ID or span 123 which tells us which span called this one. The operation name is db.query, telling us that this span represents a database query. The service is order service, telling us which service executed this span. And we have start time and duration millisecond, showing when and how long it took. The tags object contains metadata about the operation. So for a database span, we might include db.type as PostgreSQL, db.statement as the query, and db.rows affected as a result count. Finally, status tells you whether the operation has succeeded. This helps identify which spans in trace represent failures. So the key takeaway is that traces are made of spans. Spans have parent-child relationships that form a tree, and spans carry tags and logs that provide details about each operation. Now let us look at how to add tracing to your code using OpenTelemetry, which is the emerging standard for distributed tracing. First, we get a tracer from OpenTelemetry, naming it after our service. The tracer is the factory for creating spans. In the process order function, we create a span using a with statement. The tracer.start as current span method creates a new span and sets it as the current span for this context. Any child spans created inside this block would automatically be linked as children. We set attributes on the span using the span.setAttribute. Here we attach the order ID so we can search for traces by order. Inside the main span, we create a child span for the database query. This span is automatically a child of process order because of the nesting. We set the database specific attributes like db.system and db.rows return. And then we create another child span for the payment operation. We set the payment amount as an attribute. If the payment fails, we catch the payment error, set the span status to error with the error message, and re-raise the exception. This marks the span as a failed in the trace visualization. The key here is that the nesting of the with statements creates the parent-child relationships automatically. You do not have to manually pass span IDs around within a single service. So the key takeaway is that you should be using the OpenTelemetry's context management to create spans. Nest your spans to reflect the logical structure of your operations. Set attributes to make spans searchable and understandable. Now, tracing within a single service is one thing. The real challenge is propagating the trace context across service boundaries. Now, let us look at how to do that. The call payment service function shows the outgoing side. Before making an HTTP request to another service, we create an empty headers dictionary. Then we call the inject headers, which is an OpenTelemetry function that adds the trace context headers to the dictionary. Now, when we make the HTTP request, we include these headers and the receiving service can continue the trace. The payment handler function shows the receiving side. When a request comes in, we call the extract in bracket request or headers, which pulls the trace context out of the incoming headers. This gives us a context object. When we create our span, we pass this context, which makes a span a child of the span in the calling service. The table here shows the common header formats. Trace parent is a W3C standard and contains the trace ID, span ID, and span sampling flags. Trace state carries the vendor-specific data, which is XB3. Trace ID is the oldest Zipkin format, which you might encounter in legacy systems. The key point here is that the trace propagation requires explicit effort. You must inject context when making outgoing calls and extract context when receiving incoming calls. If you miss either side, the trace breaks and you lose visibility into cross-service calls. So the key takeaway is that use OpenTelemetry's inject and extract functions to propagate trace context. Make sure every HTTP client and server in your system handles trace headers correctly. Now here's a reality check. Tracing everything is pretty expensive, so let us talk about sampling strategies that let you get value from tracing without breaking the bank. Looking at the cost calculation, imagine 1 million requests per day with an average of 10 spans per request. That is 10 million spans per day or 300 million spans per month. Each span needs to be collected, transmitted, stored, and indexed. The storage and processing cost for this will be very big. The table here shows 4 sampling strategies. So head-based sampling makes a decision at the start of the trace. If you decide to sample this trace, you record all spans. If not, you record nothing. This is simple and predictable, but means you might miss something and miss interesting traces as well. The tail-based sampling waits until the trace is complete. Then it decides whether to keep it based on what happened. Did it error? Was it slow? This lets you keep these interesting traces but require buffering complete traces before deciding. Rate limiting says you will keep a fixed number of traces per second regardless of traffic volume. This control costs but might miss important traces during traffic spikes. Priority based sampling increases the sample rate for errors and slow requests. This focuses your budget on traces most likely to be useful for debugging. So, the key insight is that sampling is necessary at scale and the right strategy depends on your goals. If cost is the primary concern, use rate limiting. If caching problem is a priority, use tail based sampling that keeps errors and slow requests. Now, let us look at sampling implementations in much more detail. For head-based sampling, the code is simple. We define a sample rate of 0.01, which means 1% of traces. The should sample function generates a random number and returns true if it is below the sample rate. At the start of each request, we check should sample and create this pattern with sample ID equal to true or sample ID equal to false accordingly. The limitation is that we decide before we know anything about the request. An important request that fails gets the same 1% chance as trivial request that succeeds. Tail-based sampling is more sophisticated and typically configured at the collector level rather than in application code. The example shows an OpenTelemetry collector configuration with three policies. The first policy is named errors and keeps 100% of traces that contain an error status code. The second policy is named slow requests and it keeps 100% of traces where latency exceeds the 1000 milliseconds. And the third policy is named sample rest and keeps 1% of everything else using probabilistic sampling. The net effect is that you keep all errors, all slow requests, and 1% sample of normal request. Your storage is focused on traces most likely to be useful while you still have a baseline sample of healthy behavior for comparison. So the key takeaway is that at scale, you use the tail-based sampling to keep 100% of errors and slow requests while sampling healthy requests. This gives you the traces you need for debugging while controlling the costs. Now let us talk about alerting, which is how you find out about problems before your users tells you. The goal of alerting is simple. Wake someone up when something is wrong and they can do something about it. But getting alerting right is surprisingly difficult. A good alert has four properties. First, it is actionable, meaning someone can do something about it. Second, it is urgent, meaning it needs attention now, not tomorrow. Third, it is real, meaning it indicates the actual user impact. Fourth, it is documented, meaning there is a runbook explaining what to do. Now, if we look at the bad alert example here, which is CPU is at 80%. So if you think about it, is it a problem? Maybe not. Some applications run hot, but some applications might think this is risky. So what should you do? Unclear. So maybe you should add capacity, maybe wait and see are users affected. So thing is, better alert example would be something like error rate exceeded 1% for 5 minutes. This tells you users are seeing errors right now. The action is clear. Check logs for cause. Rollback if there was a recent deploy. And there is a runbook at a specific URL with detailed steps. The difference is that the first alert is cause-based and tells you about infrastructure state. The second alert is symptom-based and it tells you about user experience. Symptom-based alerts are almost always better because they directly answer the question, are users affected? So the key takeaway is this. Before creating any alert, ask yourself these four questions. Is it actionable? Is it urgent? Is it real? Is it documented? If the answer to any is no, reconsider whether you need that alert. Now let us go deeper on the distinction between cause-based and symptom-based alerts. Looking at the cause-based alerts here by the table, we have CPU over 80%, disk over 90%, memory over 80%, and pod restarted. The problems column explains why these are poor alerts. High CPU may not affect users if the application handles it gracefully. High disk is concerning, but how urgent is it? High memory might be normal for some applications, and a pod restarting might be expected during deployments. Now, if we look at the symptom-based alerts table, error rate over 1% directly means users are seeing errors. P99 latency over 2 seconds means users are actually experiencing slowness. and success rate under 99% means orders are failing, and queue depth over 10,000 means processing is delayed. Each of these symptom-based alerts has a clear user impact. You know something is wrong because users are affected, not because the dashboard number looks high. The rule at the bottom summarizes it pretty well. Alert on symptoms, investigate causes. Your alerting system should tell you that users are affected. Your dashboard and logs should help you figure out why. This does not mean you ignore the infrastructure metrics. You should absolutely track CPU, memory, and disk on dashboards, but you should not be paging someone at 2 a.m. because CPU is at 80%. You should page them because error rate has spiked, then let them investigate and discover that CPU might be the cause. So the key takeaway is that design alerts around user visible symptoms and reserve infrastructure metrics for dashboard and investigation. So not all alerts should page someone. Let us talk about severity levels and how to configure alerts properly. The severity table shows 4 levels. P1 critical requires immediate response and might page someone. Example includes like website is down or data has been lost. P2 high should be addressed within an hour. Examples include partial outages or major features broken. P3 medium should be addressed within 4 hours. Examples could include like degraded performance or minor features affected. P4 low can wait for the next business day. Examples include warning threshold hit or cleanup needed. The key is matching urgency to impact. A complete outage is P1. A degraded recommendation engine that nobody will notice at 3 a.m. is P4. Looking at the Prometheus alert configuration, we define an alert name high error rate. The EXPR field contains a prompt QL expression that calculates the error rate over a 5-minute window. If it exceeds 0.01 or 1%, the alert fires. The for 5 minutes clause is pretty important. The condition must be true for 5 minutes before the alert fires. This prevents the flapping alerts where a brief spike triggers and resolves repeatedly. Labels include severity set to critical, which determines routing, who gets paged, and how urgently. Annotations include a summary, a description that uses template variables to show the actual value, and a runbook URL. So the key takeaway is this: configure severity levels based on user impact and urgency. Use the for clause to prevent flapping. Always include runbook URLs so the on-call engineer knows what to do. It's for on-call rotation is alert fatigue. When there are too many alerts, people start ignoring them, or real issues get missed because they are lost in the noise. The signs for alert fatigue are clear. On-call engineers ignores alerts because most are false positives. Alerts get auto-acknowledged without investigation. Alert storms becomes common where dozens of alerts fire simultaneously, and real issues get missed because they look like just like another noisy alert. The solution table addresses common problems. If you have too many alerts, raise thresholds or reduce scope. If alerts are flapping, meaning firing and resolving repeatedly, add like a for clause that requires the condition to persist. If you have duplicate alerts where the same issue triggers multiple alerts, group related alerts together. If alerts are non-actionable, delete them or convert them to dashboard metrics that you monitor but do not alert on. If there is no runbook, either add one or delete the alert. The last point deserves emphasis. An alert without a runbook is worse than no alert. It pages someone, they do not know what to do, they ignore it, and you have trained them to ignore alerts. Every alert should have a runbook, even if the runbook just says investigate logs and escalate if needed. So the key takeaway is that regularly audit your alerts, delete the ones that do not lead to action, tune the ones that fire too often, add runbooks to the ones that remain. Your goal is zero false positives. Now let us look at systematic process for maintaining alert hygiene and an example of alert aggregation. The alert hygiene process suggests a monthly review. First, examine which alerts have fired. Second, determine which were actionable, meaning someone actually did something in response. Third, check which led to real fixes versus being noise. Fourth, decide which alerts should be deleted. So the key question is that if an alert has fired but no action has been taken, either delete it or raise the threshold. That alert is not providing value, and if the same alert fires repeatedly for the same underlying issue, either fix the underlying issue or automate the remediation. Now, if you look at the alert aggregation example here, the bad alert fires on pod high CPU for each individual pod which when container CPU usage exceeds 0.9. If you have 100 pods, you might get 100 separate alerts. This is overwhelming and makes it hard to see the overall picture. The better alert fires once for service high CPU using the average CPU across all pods for the service. If the average exceeds 0.8, you get one alert that says the API service has high CPU rather than 100 alerts for individual pods. Alert aggregation reduces noise while preserving the signal. You know the service is struggling. If you need to know which specific pods are hot, you can look at the dashboards during investigation. So the key takeaway is that aggregate alerts at the service level rather than the instance level. One alert that says your service is broken is more useful than 100 alerts that say pod 1 is broken, pod 2 is broken, pod 3 is broken. Wrap up the observability section with dashboards. Dashboards are where you make data visible and where you go to understand system health at a glance. The diagram shows a dashboard hierarchy with 3 levels: service overview at the top, component details in the middle, and individual instance at the bottom. This hierarchy reflects how you typically investigate issues. Start high level, then you drill down as needed. Level 1 is service overview. At a glance, you should be able to answer, is the service healthy? The dashboard shows green or red status, error rate, trend, latency at P50 and P99, and request rate. You should be able to look at this dashboard for 5 seconds and know if something is wrong. Level 2 is component details. When you know something is wrong, you drill down here to understand which component is causing the issue. This level shows database metrics, cache hit rate, dependency health, and resource utilization. These are the building blocks that affect the service level metrics. Level 3 is instance details. When you have identified a problematic component, you might need to drill into individual pods or servers. This level shows individual pod metrics, specific queries, and debug information. You rarely need this level, but when you do, you need it badly. So the key takeaway for this section and for observability as a whole is this: design your dashboards to support the investigation workflow. Start with the service level view that answers is something wrong, then provide drill down paths and that answer what is wrong and where specifically is it wrong. Now let's talk about dashboards and specifically what every service dashboard should actually be showing. When you spin up a new service in production, you are going to need a dashboard. But what should be on it? If you just throw random metrics onto a Grafana dashboard, you will end up with just more noise than actually signal. So there is actually a well-established framework for this, and it comes from Google's Site Reliability Engineering team. They call it the 4 golden signals. The first signal is latency. Your dashboard should show P50, P95, and P99 latency over time. But why these specific percentiles? So let's talk about that. The reason is that because number 1, the P50 tells you that, okay, what is the typical user experience? The P95 will tell you actually what is your slower users are experiencing. And the P99 actually catches the tail latency that often affects your most important users, like enterprise customers making large transactions. This directly maps to user experience, so it's super important. The second signal is traffic. This should show how many requests per second are hitting your service. So why is super important? It's important because the traffic will actually tells you what is the load and what is the capacity. If your traffic suddenly doubles and your latency stays flat, your system is healthy. If your traffic doubles and latency actually spikes, you have a scaling problem. Traffic is also your early warning system for viral moments or unexpected load. The third signal is errors. So this should show your error rate as a percentage. Not just raw error counts, but also the percentage of requests that are failing. So why percentage and not the absolute count? The reason is because let's say if you have 10 errors out of 100 requests, that is a 10% error rate, and that's a serious problem. But if you have 10 errors out of 1 million requests, that is 0.01%, and that's probably acceptable and it's not that big of an alert. The error rate directly reflects your reliability. And the fourth signal is saturation. This should show resource utilization, for example, CPU, memory, connection pools, queue depths. So saturation tells you about the headroom. Even if your latency and error rate look fine right now, if your CPU is, let's say, at 90%, you have no room to handle a traffic spike. Saturation is your forward-looking indicator. So now for dashboard layout, you should start with arranging these in, let's say, a 2 by 2 grid. So latency and traffic should be in the top row as line charts. Errors and saturation should be, let's say you can put them in the bottom row with errors as a line chart and saturation as gauges. And then below the grid itself, you should have a section showing recent deployments so you can correlate any metric changes with code releases. And finally, a section showing active alerts so that anyone looking at the dashboard immediately knows if something is on fire. So the key insight here is that these four signals, which is latency, traffic, errors, and saturation, will give you the complete coverage of a service health from the user's perspective, and this framework should be the foundation of every production dashboard you should be building. Okay, now let's talk about how to actually implement each of these panels on your dashboard because the details matter quite a bit here. So for panel 1, I would say your latency panel, you should show 3 lines on the same chart. The P50 should be in the green because that is a happy path representing typical user experience. The P95 should be in yellow as a warning zone, and the P99 should be in red because that is where problems often hide. You should also add a dashed line showing your SLO threshold so you can immediately see where the latency is approaching or breaching your target. For panel 2, your traffic panel, you should show request per second as a primary line, but here's a really useful addition. You should consider adding a dashed line showing traffic from the same time yesterday. This gives you immediate context, and if the traffic is 50% lower than yesterday at the same time, either something is broken or there is a holiday for probably in your user market that you have forgotten about. Comparatively, baselines turn actually raw numbers into meaningful signals, so they are super important. For panel 3, which is you should consider putting as your errors panel, you should show error rate as a percentage, but you should also break it down by error type using a stacked area chart. This way you can see not just that the errors have spiked, but whether the errors are like HTTP 500 errors, 503 errors, HTTP 429 rate limits, or something else entirely. Different error types have different root causes and different remediation paths. For panel 4, your saturation panel, you should show the CPU utilization as a gauge, memory utilization as a gauge, connection pool usage, and the queue depth. Gauges work well here because you care about the current value relative to the maximum capacity, not the trend over time. Finally, for contextual information, your dashboard should show recent deployments as vertical lines overlaid on your charts, so this makes correlation pretty easy. This should also show that you should have a status banner showing active incidents, a display of your SLO budget remaining as a percentage, and links to runbooks for quick access during incidents. So the key insight here is that a well-designed dashboard should let anyone on your team glance at that, let's say in 5 seconds, and they can understand whether the service is healthy or not. Now let us talk about one of the most powerful concepts in observability, which is correlation. Having logs, metrics, and traces is great, but the real power comes from connecting them together so you can go from alert to root cause in minutes instead of debugging for hours. So let me walk you through what a typical investigation flow should look like. It starts with an error alert firing, something like, let's say, error rate greater than 1%. Then you check your dashboard and see, there was an error spike at, let's say, 1023. Then you drill down into your metrics and see the errors are coming from the, let's say, /checkout endpoint specifically. And then you filter your traces to show traces for /checkout that have errors. You find a specific trace for trace ID, let's say ABC123, and then you pull up all logs that share that same trace ID. And finally, you discover the root cause. Let's say it could be like it was a database connection timeout. Notice how we went from a high-level symptoms, which is like an error rate up, all the way down to specific root cause, database timeout, in 7 steps. This is only possible when your logs, metrics, and traces share the correlation IDs. So how do you enable this? The key is that you include a trace ID everywhere. In your logging, when you log an event like let's say checkout failed, you should include a trace ID as a field along with other contexts like user ID and the specific error. In your metrics, you should attach the trace ID via exemplars when you record observations like request duration. The trace ID becomes a universal key that lets you pivot from any signal to any other signal. You see a spike in metrics, you click to see whether traces were involved. You find a trace, you click to see all the logs from that request. And this connected flow is what separates world-class observability from just having a lot of data that you honestly cannot leverage when there are incidents happening. So the key takeaway is that the trace ID should be included in every log entry and attached as an exemplar to your metrics because it is a thread that ties your entire observability story together, especially in distributed systems. Okay, now let's look at the exemplars in more detail because this is a relatively new feature that many teams have not yet fully adopted, but it's super powerful. Exemplars are a way to attach specific trace IDs to your metric data points. So let's say when you see a spike in your P99 latency graph, you click on that spike and immediately you get a trace ID for one of the slow requests that contributed to it. So here's how the implementation look like. You create a histogram for tracking request duration with the endpoint as a label. Then in your request handler, you measure the duration of each request. When you record the observation to the histogram, you also pass an exemplar parameter containing the trace ID. Now, here's where the magic happens in Grafana. You see a spike in your P99 latency, you click on that spike, the exemplar shows you the trace ID of an actual request that was slow at that moment. You click on the trace ID and it opens the trace directly in Jaeger or Tempo. Now you can see exactly what happens in that slow request, which service calls took longest, where the delays occurred, and what errors happened along the way. Without exemplars, you see a latency spike and then you have to guess which trace to look at or manually search through thousands of traces to be able to find one that matches the time window. With exemplars, you go directly from metric anomaly to specific trace in literally 2 seconds. So the key insight here is that exemplars bridge the gap between aggregate metrics and individual request traces, and when they transform your debugging workflow from searching for, let's say, needles in haystack to actually following direct links, so you go from point A to point B in just 2 clicks. Now let's talk about observability anti-patterns because there are some common mistakes that teams make that actually make debugging much more harder and not easier. So understanding what not to do is just as important as understanding what you should be doing. The first anti-pattern is logging everything. You might think more logs equals better observability, but that is actually not true. When you log every function entry and exit, every variable value, every database call and response, you create so much noise that finding meaningful information becomes nearly impossible. And your logging costs will also go through the roof. Instead, you should log meaningful events. Instead of 5 debug statements for a single operation, you should log one info level event that captures the outcome. Let's say, for example, order processed with the order ID and the duration in milliseconds. The single log line will tell you everything that you need to know and is actually searchable when debugging. The second anti-pattern is metrics without labels. So if you create a counter, let's say call a request total with no labels, you can see your total request count, but you cannot answer any useful questions. For example, which endpoints are getting the most traffic, which ones are failing, and you have no way to slice the data. Instead, your counter should include labels for methods, endpoints, and status. Then you can filter by get request to, let's say, checkout endpoint that return 500 errors. You can also aggregate by endpoint to see which one are the busiest endpoints. So labels are what makes metrics easy to query and super useful. So the key insight here is that observability is not about volume of data. It's about the right data captured in the right structure so you can actually answer the questions when something goes wrong. Now let us continue with more observability anti-patterns because there are a few more critical mistakes worth understanding. The third anti-pattern is high cardinality labels. This is one of the most expensive mistakes you can make. If you add user ID as a label on your metrics and you have millions of users, you have just created millions of time series. Your metric storage will explode and your queries will become slow and your monitoring bill will actually go through the roof. Instead, you should use bounded labels. Instead of user ID, you should use, let's say, user type with values like free, premium, and enterprise. Now you have 3 time series instead of millions. You can still segment your data meaningfully and your costs will stay predictable. The fourth anti-pattern is no correlation IDs. When you log payment process with no context, you cannot connect that log to anything else. If the payment service is logged it and the order service also logs something and the notification service logs something else, you have no way to know where all these services are talking to which request and whether they came from the same user request or not. Instead, every log should include a trace ID and any relevant business identifiers, let's say like order ID. Now, you can search all through the logs related to a single request across all your services and especially important distributed systems where multiple microservices are operating. The fifth anti-pattern is alerting on causes instead of symptoms. When you alert on CPU being above 80%, you're alerting on a cause, not a symptom. High CPU might not affect users at all if you have headroom. On the other hand, you could have a low CPU and still have users experiencing errors due to a different issue entirely. Instead, you should be alerting on symptoms, things that are actually affecting users. For example, high error rate, high latency, and failed transactions. These are things that matter to your business, and you should use the cause metrics like CPU for investigation and capacity planning, but not for alerting. So the key takeaway is that these anti-patterns often feel intuitive at first, but they lead to observability systems that are expensive, noisy, and unhelpful when you actually need them. Okay, now let us summarize the key takeaways from everything we have covered in observability today. For logging, there are 4 critical practices. First, use structured logging, meaning JSON format, not plain text strings. Structured logs are searchable and parsable. Second, you should be including trace ID in every single log entry. There is a correlation key across the entire system. Third, log events, not debug statements. So you should be logging the completion of meaningful operations, not every step along the way. Fourth, you should be sanitizing sensitive data. So for example, you should be never logging passwords, API keys, credit card numbers, or any personally identifiable information like which is essentially what we term as PII. For metrics, there are also 4 critical practices. First, you should use the RED method for request-driven metrics, which is rate, errors, and duration. So that stands for RED, R-E-D. These 3 metrics give you a complete picture of how your service is handling traffic. Second, you should use the use method for resource metrics, U for utilization, S for saturation, and E for errors. So for example, you should use like a CPU, memory, and disk resources and measure them and try to see if there's something is going wrong there. Third, you should define your SLIs, which is service level indicators. And track the error budgets so you know objectively whether your service is meeting its reliability targets or not. Fourth, you should avoid high cardinality labels, which means never put the unbounded values like user IDs or session IDs as metric labels. These practices form the foundation of effective logging and metrics. In the next slide, we'll cover the remaining pillars, which is tracing, alerting, and dashboards. Now let's cover tracing, alerting, and dashboards. For tracing, there are 4 essential practices. First, you should be tracing requests across all your microservices. Every service boundary should propagate trace context. Second, you should be propagating context via headers using standard formats like, let's say, W3C trace context or B3 headers, so different services and different languages can all participate in the same trace. Third, you should be using sampling to control cost. You do not need to trace 100% request. Even 1% sampling gives you plenty of data for debugging while keeping storage costs manageable. Fourth, link traces to logs and metrics using exemplars and trace IDs so you can pivot between different telemetry types during investigations. For alerting, there are 4 principles to follow. First, you should be alerting on symptoms, not causes. You should alert when the user is affected, not when an internal metrics look concerning. Second, every alert must be actionable. If there's nothing someone can do at 3 a.m. when this alert fires, you should not be paging anyone at 3 a.m. Third, you should include a runbook links in every alert so that an on-call engineer can immediately find the remediation steps. Fourth, you should review and prune alerts regularly. Alerts that are always ignored should be deleted or fixed. For dashboards, there are 4 requirements. First, show the 4 golden signals: latency, traffic, errors, and saturation. Second, Provide drill down capabilities so people can go from high level overview to specific details. Third, include the deployment markers so metric changes can be correlated with code changes. Fourth, link to traces and logs so investigation can continue when someone spots an anomaly. Next, we shift the gears to our next section, which is deployment strategies, where will we cover how to get your code to actual production much more safely. So let's do that. Now this is a section where we focus on getting your code to production safely. We are going to cover CI/CD pipelines, different deployment strategies, rollbacks, feature flags, and database migrations. But first, let us talk about why deployment even matters so much in production scenarios. Let's say in an interview setting, you might say that, okay, we'll deploy to the new version, and then you just cover that and move to the next topic in system design interview. However, but in the production, the question actually becomes much more detailed. For example, how do we deploy without the downtime? In an interview, you might just say that, okay, we push to production, but in production, the question becomes like, okay, how do we detect problems in the production, and that too much faster and in much less time? And again, comparing to an interview, like, the scope of deployment topics that are covered in interview, another thing is that, candidates generally say that, okay, we can update the servers, right? But in production scenarios, when you're actually acting as a software engineer in the industry, you have to go think of much more details like, okay, how do we do rollback in seconds if something goes wrong? So here's the key insight I want you to, internalize and remember for your career. Deployment is not the end of development, it's the beginning of production. The moment code hits production is when the real test starts. And how you deploy determines how fast you can recover from mistakes. Think about it this way. If you deploy in a way that, okay, it takes 30 minutes to roll back and you have a bug that causes a 5% error rate, you have just given 5% of your users a bad experience for 30 minutes. But if you deploy in a way that lets you roll back in 30 seconds, that same bug only affects your users for 30 seconds before they're back to the working version. So a deployment strategy you choose directly impacts reliability, so your mean time to recovery, and ultimately your user's experience. So let us dive into more details how to do this well. Now let us start with CI/CD pipelines, which are the foundation of getting code from a developer's machine to production reliably. The flow looks like this. A developer will commit code, then the pipeline will build the code, then unit tests will run, the integration tests will run, and then a security scan checks for vulnerabilities. Then the next step is where the code deploys to staging, then end-to-end tests will run against the staging, and finally the code deploys to production. Let me break down each stage and why it matters. The build stage compiles your code and creates a deployable artifact. This typically takes 1 to 5 minutes. The unit test stage verifies that individual components work correctly in isolation. This takes roughly 2 to 10 minutes and runs fast because there are no external dependencies. The integration test stage actually verifies that, okay, the different components, they work correctly together, often with real databases and real message queues. This will roughly take around 5 to 15 minutes in a typical scenario. The security scan stage checks for known vulnerabilities in your dependencies and your code. This roughly takes 2 to 5 minutes. And the staging deploy stage, which will put your code in a production-like environment where you can test it without affecting real users, and this takes roughly 5 to 10 minutes as well. The end-to-end test stage, which stands for end-to-end, like integration testing, verifies that the complete user workflows, they work correctly. This will take roughly 5 to 20 minutes. And finally, the production deploy stage releases your code to real users. This will roughly take 5 to 30 minutes depending on your deployment strategy. So the key insight is that each stage catches different classes of bugs, and the earlier you catch a bug, the cheaper it is to fix. A bug caught in unit tests will cost you minutes. A bug caught in production, costs incidents. So the sooner you catch the bug, the better it is. Now let us talk about what actually gets deployed. There's the concept of build artifacts. The principle here is that immutable artifacts, which is build once and deploy everywhere. The exact same artifact that you tested in staging should be the exact same artifact that goes to production. You should never rebuild for the production, because then when you are not actually deploying what you have actually tested in staging. Different type of applications had different artifact types. So for microservices, you typically build container images, something like Docker.io slash my app, v1.2.3. For Java applications, you build jar or var files like, my app -123.jar. For Go or Rust applications, you build the native binaries like my app, Linux AMD 64. Or for libraries, you build the packages like, let's say, mylib, .tar.gs. So for artifact versioning, you have several options. You could use a semantic versioning, let's say like my app, 123, which is human readable and follow conventions. You could also use the git sha, like for example, my app -abc 123 def, which ties directly to a specific commit. Or you can actually, this is something to be considered as well, which is you could use a timestamp plus the sha, like my app 2025 1015 and then -abc 123. This gives you both chronological ordering from the timestamp and the exact commit identification from the sha. So why does the timestamp plus sha work so well? Because when you're looking at running containers at 3 a.m., let's say during an incident, you can immediately see when this artifact was built, and you can trace it back to an exact commit. Semantic versions require looking up which commit maps to which version, and git shas alone do not tell you, when they were actually built. So the key insight is that your artifact strategy should make it trivially easy to answer questions like, okay, what code is currently running in production at any moment? Now let's talk about the container image best practices, since containers are the most common artifact type for microservices. Here's an example of what not to do. Using, let's say, from Python latest means your base image can change between builds. Using copy.app without a multi-stage build means your final image includes all your build dependencies. This creates larger images, less reproducibility, and potential security issues, so please don't do that. Now here's a better approach. First, pin your base image to a specific version, let's say from Python 3.11.5 Slim. The Slim variant is smaller and has fewer unnecessary packages. Then use a multi-stage build. Your first stage, labeled as builder, installs all your dependencies. Your final stage copies only what you need from the builder stage, which is the installed packages. Then copy your application code, switch to a non-root user for security, and define your startup command. So now why the multi-stage builds? Because your final image only contains what you need to run, not what you needed to build. This means smaller images, faster deployments, and a smaller attack surface. For image scanning, your CI pipeline should scan every image for known vulnerabilities. You can use tools like Trivy to scan your image and fail the pipeline if the critical vulnerabilities are found. This prevents deploying images with known security issues. Now, the key insight here is that your container image should be minimal, reproducible, and scanned for security vulnerabilities before it even reaches the production. Now, let us talk about what to test before your code reaches production, because not all tests are created equal. You have probably heard of testing pyramid. So, for example, at the bottom you have unit test, which is many tests and they are very fast, they are very cheap to run. In the middle, you have integration tests, which are fewer tests, medium speed, and more complex to set up. At the top, you have end-to-end tests, which are very few tests. Actually, they're very slow, expensive, and can be flaky as well. So here are some concrete numbers to think about. You should roughly, depending on your code base, you should, have a ballpark around 1,000 plus unit tests. So they they run, in milliseconds each, and they're very stable. Ideally, you should have roughly 100 to 500 integration tests. Again, it depends on your code base size. And they should run, in seconds each, and they're mostly stable as well. For end-to-end tests, you should ideally have, let's say, 10 to 50 end-to-end tests, because, they take minutes to run each and can be flaky because they involve real browsers, real networks, and real timing issues. So now, why this distribution? Because of its cost-benefit trade-off. Unit tests are cheap to write, fast to run, and they're reliable. So you can have thousands of them. End-to-end tests are expensive to write, slow to run, and they're often flaky. So if you had thousands of end-to-end tests, your CI pipeline would essentially take hours, and you would have consistently, chasing down flaky test failures. The goal is to push as much as testing possible down the pyramid. If you can catch a bug with a unit test, do not rely on an integration test to catch it. If you can catch it with an integration test, do not rely on an end-to-end test to catch it. Now each layer should catch what the layers below cannot. So the key insight here is that a fast, reliable test suite is worth more than a comprehensive but slow and flaky one, because teams they actually run fast tests on every commit. Now let me show you an example of what a complete CI pipeline configuration might look like in practice. So here you start with unit test running PyTest against your unit test directory with parallelization enabled. You set a timeout of 10 minutes because if unit tests take longer than that, then something is wrong. Then you run integration test along with PyTest, but against your integration test directory. Here you spin up actual services like Postgres 15 and Redis 7 as part of your test environment. Timeout here is 20 minutes since these tests tend to be slower than the unit tests. Then you run the security scans using multiple tools. Bandit scans for your Python source code for security issues, safety checks, for dependencies, for unknown vulnerabilities, and Trivy scans for container images for vulnerabilities. Then you deploy to staging using kubectl and apply with the staging context. So this puts your code in a production-like environment. Then you run end-to-end tests using a tool like Cypress pointed at your staging URL. Timeout here is 30 minutes because these tests involve real browser automation. Finally, you deploy to production using kubectl apply with a production context. Notice the when manual flag here. So when which means actually a human must approve the production deployment. There's a decision point where someone reviews the staging results before releasing it to real users. So the key insight is that your pipeline should be a series of quality gates where each stage must pass before proceeding to the next, with human approval required for the final production deployment. Now let us talk about the different strategies you can use to actually deploy your code to production. Each strategy has different risk levels, rollback speeds, and complexity trade-offs. The first strategy is called recreate. This has high risk, slow rollback, but low complexity. You stop the old version, then you start the new version. There's downtime during the transition. The second strategy is rolling update. This has medium risk, medium rollback speed, and low complexity. You gradually replace old instances with new instances one at a time. The third strategy is blue-green. This has low risk, fast rollback, but medium complexity. You run two identical environments and switch traffic between them. And the fourth strategy is Canary. This has very low risk, fast rollback, but high complexity. You gradually shift traffic from old to new, monitoring metrics at each step. The fifth strategy is Shadow, also called Dark Launch. This has no user risk since users never see the new version. You mirror the traffic to the new version but discard its responses. This is high complexity but great for validation. So now this is how you should consider choosing between these options. For low traffic internal tools, recreate or rolling is fine. For business critical external services, using blue, green or Canary is recommended. And for high risk changes like major rewrites, use Canary with a slow rollout. For new features where you're uncertain about behavior, you should consider using shadow traffic testing to validate before any users see it. So the key insight is that the right deployment strategy depends on how much risk you can tolerate and how fast you need to be able to roll back. Now let us start with the simplest deployment strategy, which is recreate. The idea is pretty straightforward. You stop all the instances of the old version, then you start all the instances of the new version. The flow looks like this. You have a V1 running, then V1 stops, then V2 starts, then V2 is running. During that middle period when the V1 has stopped and V2 has not yet started, there is downtime. In Kubernetes, you implement this by setting the strategy type to recreate in your deployment spec. When you update the image to v2, Kubernetes will terminate all the old pods before creating new ones. So when should you use this strategy? The first use case is development and staging environments where downtime does not matter. The second use case is database schema changes that require the old version to be completely gone before the new version starts. The third use case is applications that fundamentally cannot run two versions simultaneously, perhaps because they take exclusive locks on the same resource. The trade-off is clear. You get simplicity, but you pay with downtime. For many production services, any downtime is unacceptable, but for some use cases, a brief maintenance window is perfectly fine, and the simplicity of Recreate makes it worth considering. So the key insight is that Recreate is the right choice when downtime is acceptable and simplicity is valued, but it should never be used for user-facing services that need high availability. Now let's talk about the next deployment strategy, which is rolling update. This is one of the most commonly used deployment strategy. The idea is gradual replacement. So you replace the old instances with new instances one at a time, maintaining the capacity throughput. The flow looks like this. You start with 3 v1 instances, and then let's say you add one v2 instance, verify it's healthy, then you remove one v1 instance. Now you have 2 v1 and 1 v2 instances running. You repeat this process, adding v2 instances and removing v1 instances until all 3 instances are v2. At no point did you have less than your required capacity. Now, here's how you will implement this in Kubernetes. You set the strategy type to rolling update and configure 2 parameters. Max surge is set to 1, which means at most 1 extra pod can exist during the update. Max unavailable is set to 0, which means you always maintain full capacity. The process works like this. Kubernetes starts a new v2 pod. It waits for that pod to pass its health check. Once the new pod is healthy, Kubernetes terminates the one old v1 pod. Then it repeats until the rollout is complete. This strategy maintains availability throughout the deployment. Users never experience downtime. So if the new version has a problem and fails health checks, the rollout pauses and old instances continue serving traffic. So the key insight is that rolling update gives you zero downtime deployments with minimal additional infrastructure, which is why it is default choice for most services. Now let us dive deeper into parameters that control the rolling update behavior, because tuning these correctly matters quite a bit. With max surge of 1 and max unavailable of 0, you get the safest but slowest rollout. You always maintain full capacity, but you need extra resources during the deployment since you run both old and new pods. With max surge of 0 and max unavailable of 1, you get resource efficient but capacity reduced rollout. You never exceed your normal resource allocation, but you temporarily have reduced capacity. With max surge of 50% and max unavailable of 50%, you get a fast rollout, but with both higher resource usage and reduced capacity during the transition. This is riskier but faster for large deployments. For rolling update to work correctly, you need proper health checks. Your container spec should include a readiness probe that tells Kubernetes when the pod is ready to receive the traffic. You set the HTTP GET path to your health endpoint, something like health/ready. You set the initial delay seconds to give your application time to start up. And you set period seconds to control how often Kubernetes checks. You should also have a liveness probe that tells Kubernetes when to restart a pod because it is unhealthy. So this uses a different endpoint, let's say like /health/live, and has different timing parameters. The critical point is that the new pods only receive traffic after passing the readiness check. This is what prevents broken deployments from affecting the users. If the new version cannot pass the health checks, it never receives the traffic and the rollout stops. So the key insight is that health checks are not optional for rolling update. Without proper readiness probes, Kubernetes cannot know when new pods are ready, and you will route traffic to pods that are still initializing. Now let's talk about the blue-green deployments. So this strategy uses 2 identical environments, one called blue and one called green. Only one receives the production traffic at a time. And here's how it works. Your load balancer routes the traffic to blue, which is running V1. Green exists but it's currently idle. When you want to deploy V2, you deploy it to green. You test V2 on green while blue continues serving the production traffic. Once you're confident V2 works, you switch the load balancer to point at the green. Now, green serves production traffic and blue is idle. If something goes wrong, you can switch back to blue instantly. The flow is pretty straightforward. Blue environment runs the V1, serving production traffic. You deploy V2 to green environment. You test V2 on green, maybe by hitting it directly or sending a small amount of test traffic. You switch the load balancer from blue to green. Blue becomes a standby with V1 still running and ready. If V2 has any problems, you switch back to blue, which takes only seconds. The instant rollback capability is a killer feature of blue-green deployments. With rolling update, if you discover a problem 50% through the rollout, you have a mix of V1 and V2 serving traffic while you roll back. With blue-green deployments, you flip one switch and 100% of traffic is back on the known good version immediately. So the key insight is that blue-green is the right choice when instant rollback capability is worth the cost of running two complete environments. How to implement blue-green deployments in Kubernetes. The approach uses labels and service selectors. You create here two separate deployment resources. The first is MyAppBlue with the version label of blue. The second is MyAppGreen with a version label of green. Both deployments have pods with the app label set to MyApp, but they differ in the version label. The service resource is what controls which deployment will receive the traffic. The selector specifies both app as MyApp and version as blue. This means the service routes traffic only to pods that have labels matching. When you want to switch from blue to green, you update the service selector to version as green. Now all traffic routes to the green deployment. When you want to roll back, you change the selector back to version blue. This approach is clean and declarative, so the switch is literally changing one value in the service spec. In practice, you would automate this through your CI/CD pipeline with verification steps between the switch and any cleanup. One important detail to note is that both blue and green need to be running and healthy before you switch. You deploy to green, verify green is healthy, then switch traffic. The ordering matters here. So the key insight is that the Kubernetes implementation of blue-green deployment is actually straightforward once you understand that the service selector is your traffic switch here. Now let us talk honestly about the trade-offs of blue-green deployment because this strategy is not right for every situation. The advantages are pretty compelling. So you get the instant rollback by switching the service selector back. You get the full testing before the switch since green runs your complete production workload before any user sees it. You get zero downtime since the switch is atomic from the user's perspective. And the model is simple to understand. Two environments, which is one is active. However, there are still significant disadvantages. The most obvious one is double infrastructure cost. You need to be running two complete environments, which means double the compute, double the memory, and double the database connections. For large services, this can be very expensive. Database migrations are complex with blue-green deployments, so both blue and green need to access the same database, which means both versions of your code need to work with the database schema. This constrains what kind of schema changes you can make. Now, long-running connections may drop during the switch as well. So if a user has a WebSocket connection to blue, switching traffic to green does not migrate that connection. The user will need to reconnect. And you need infrastructure automation to make this practical. So manual switching service selector is pretty error prone. So this approach of blue-green deployments needs to be part of a CI/CD setup. So now when should you use the blue-green deployments? It's a good fit for critical applications requiring instant rollback when you can afford the infrastructure cost and when the testing in a production-like environment is essential before any users see the new code. So the key insight is that blue-green trades the infrastructure cost for safety and speed of rollback. Whether the trade-off makes sense depends on your application's criticality and your budget. Now let us talk about Canary deployments, which gives you even more control over risk than the blue-green deployments. With Canary deployments, you gradually shift traffic from the old version to the new version while monitoring metrics at each step. So here's how it works. Your load balancer sends 95% of the traffic to V1, which is your stable version, and 5% of the traffic to V2, which is your canary. You monitor the metrics for the canary. If the metrics look good, you increase the canary percentage. If the metrics look bad, you route 100% back to the stable. A typical canary progression might look like this. Stage 1, you send 1% of traffic to canary for 10 minutes and monitor the error rates. Stage 2, you increase it to 5% for 30 minutes and monitor the latency. Stage 3, you increase to 25% for 1 hour and monitor the business metrics like conversion rates. Stage 4, you increase to 50% for 2 hours of full validation. And for stage 5, you go to 100% and the canary becomes a new stable. At any stage, if your error rate increases by more than 0.1% or your P99 latency increases by more than 10% or your business metrics degrade, you roll back immediately by routing the 100% of the traffic back to the stable. The power of Canary deployments is that you catch problems early when only a small percentage of users are affected. If stage 1 reveals a problem, only 1% of users were impacted for 10 minutes. Compare that to blue-green deployment where you switched 100% of the traffic and discover the problem after it has affected literally everyone. So the key insight is that Canary deployments let you validate new code with real production traffic while limiting the blast radius. So if something goes wrong, it could be limited to very few number of users. Now let me show you how to implement Canary deployments using Istio, which is a popular service mesh for traffic management. You create a virtual service resource that defines how traffic should be routed. The HTTP route section specifies 2 destinations, stable with weight 95 and canary with weight 5. This means 95% of the requests go to the stable subset and 5% go to the canary subset. You then create a destination rule that defines what those subsets actually are. The stable subset matches the pods with the version label v1. The canary subset matches the pods with version label v2. To increase the canary percentage, you update the weights in the virtual service. To roll back, you set the stable weight to 100 and the canary weight to 0. What makes Istio powerful for this is that the traffic splitting happens at the network layer. Your application code does not need to know anything about the canaries. The mesh actually handles everything about the routing transparently. You can also do more sophisticated traffic splitting. For example, you could send all requests from internal employees to the canary first, or route based on headers for beta testers. Istio gives you the fine-grained control over which traffic goes where. So the key insight is that a service mesh like Istio makes Canary deployments operationally simple because traffic splitting is configuration, not code. Now let us talk about automated Canary analysis because manually watching dashboards during every deployment does not scale. The idea is to programmatically compare metrics between stable and canary and automatically decide whether to proceed or roll back. You implement a canary analyzer class that takes metrics from both stable and canary. The analyze method first compares the error rates. You calculate the increase in canary error rate related to the stable. If that increases more than 10%, you return rollback with a reason explaining that the error rate is too high. Then you compare the latency, so you calculate the increase in canary P99 latency relative to the stable. If that increase is more than 20%, you return rollback explaining what that latency is too high. If both checks pass, you return proceed with the message that metrics are healthy. This automated analysis runs from each canary stage, and if it returns the rollback, the system automatically routes the traffic back to the stable. For tooling, there are several options. Argo Rollouts is a Kubernetes native and has built-in automated analysis. Flagger integrates with Istio and Linkerd and works well with the GitOps. Spinnaker, which is a multi-cloud capable and has advanced pipelines for complex deployments, is also an option. These tools combine the traffic shifting with metric analysis to create fully automated, progressive delivery pipelines. So the key insight is that automated canary analysis removes the human judgment from routine deployments while still catching problems before there are significant problems with any traffic that affects the users. Now let us talk about shadow deployments, which are also called dark launch. So this is a strategy for testing new code with production traffic without any risk to the users. So here's how it works. A request comes in, it goes to v1, which processes it and responds to the user. The same request also goes to v2, which processes it, but the response is discarded. The user only ever sees the V1 response. V2's behavior is captured in logs and metrics for analysis. This lets you validate the V2 behavior against real production traffic patterns without any user impact. If V2 crashes, there is no problem, users never see it. If V2 produces wrong results, no problem, you're not returning those results anyways. So shadow deployments are perfect for several use cases. When you're testing a new algorithm, you can compare whether V2 produces the same results as V1. When you have done a performance rewrite, you can verify that the V2 is actually faster under real load. When you're migrating to a new database, you can see if it handles the production traffic patterns. And let's say when you're updating a new, like an ML model, you can compare the predictions without affecting the user experience. The key is that you get real production traffic patterns, which are very hard to simulate. Production traffic has seasonal patterns, weird edge cases, and traffic shapes that synthetic tests never capture. Shadow testing lets you see how new code handles the real thing. So the key insight is that shadow deployment is the safest way to validate new code because users never see the shadow version, making the risk to users literally zero. Now let me show you how to implement shadow traffic in code. Your request handler processes each request through two paths. The primary path is what responds to the user. You create a task to call the primary server and await it. And this is the response the user sees. The shadow path is fire and forget. So if the request should be shadow based on your sampling logic, you create another task to call the shadow servers, but you do not await it. You do not want the shadow processing to slow down your user responses. You only wait for the primary task, then you return its response. The shadow task runs asynchronously and as a result is discarded. The should shadow function actually controls what percentage of traffic gets shadowed. A simple implementation uses consistent hashing on the request ID. Hashing ensures the same request always gets the same shadow decision, which is important for reproducibility. For comparison analysis, you collect both responses and compare them. You record the latency difference so you can see if the shadow is faster or slower. If the results differ, you increment a mismatch metric and log the details. And this lets you quantify how often V2 disagrees with V1 and investigate specific cases where they differ. So the key insight is that shadow deployments require asynchronous processing, so shadow traffic does not add latency to the user request, plus comparison infrastructure to actually learn from the results. Now let us talk about rollbacks. No matter how careful you are with testing and Canary deployments, sometimes bad code reaches production and you need to undo the damage quickly. Knowing when to roll back is as important as knowing how. Here are the signals you should monitor and their thresholds. If your error rate spikes by more than 1%, there is an immediate rollback situation. Users are experiencing failures, so if the P99 latency increases to more than 2x your baseline, you should investigate and likely roll back. Users are experiencing slow responses, so if the CPU or memory usage spikes above 80% and stays there, you should investigate as well. This might indicate a resource leak or infinite loop. So if you get let's say multiple customer complaints, you should also investigate and likely roll back. Users are generally very proactive in telling you when something is wrong. Now here's a decision tree for rollbacks. First, you should ask, is the issue caused by the deployment? If no, then fix the issue without rolling back since the deployment is not the problem. If yes, then ask, is it fixable quickly within 15 minutes? If yes, then consider fixing forward rather than rolling back. If no, then roll back. Also ask that is the user's impact severe? If yes, then roll back immediately. Do not spend time investigating. If no, you should investigate first and then decide. The key principle is that when users are being impacted, time matters more than understanding. Roll back first, investigate later. You can always redeploy once you understand and fix the issue. So the key takeaway is that rollback decisions should be pre-planned with clear thresholds, not improvised during the chaos of an incident. Now let me show you the practical mechanics of rolling back in Kubernetes. To view your rollout history, you run kubectl rollout history deployment /myapp, where myapp would be the name of your, let's say, example app. This shows you the revisions that Kubernetes has stored, each tied to a specific version of your deployment. To roll back to the previous version, you run kubectl rollout undo deployment /myapp. This reverts to whatever was running before your current deployment. If you need to roll back to a specific older version, you run kube control rollout undo deployment / myapp to revision equal to 3. This lets you go back to multiple revisions if needed. To check the status of your rollback, you run kube control rollout status deployment / myapp. This shows you whether the rollback is progressing or complete. But manual rollbacks require human intervention. So for example, for critical services, you want automated rollback. Argo rollouts let you define this declaratively. So in your rollout spec, you define canary steps. So for example, you set wait to 5%, pause for 10 minutes, run analysis, set wait to 50%, pause for 30 minutes, set wait to 100%. This analysis step references an analysis template that checks the success rate. If the analysis fails, Argo rollouts automatically abort the rollout and routes traffic back to the stable version. The abort scale down delay seconds parameter controls how quickly the canary pods are terminated after a rollback. So the key insight is that automated rollback based on metric analysis is a gold standard because it removes the human reaction time from the recovery process. Now let me show you what an analysis template for automated rollbacks looks like. You create an analysis template resource that takes the service name as an argument. The metrics section defines what to measure and what constitutes success or failure. The success rate matrix runs every 1 minute, takes 5 measurements, and succeeds if the result is 0.99 or higher, meaning 99% success rate. If it fails, it will see if it sees the 3 consecutive failures. The provider section defines how to get the metric. In this case, we are querying Prometheus, so the query calculates success rate by dividing successful requests, that means those with 500 status codes, and then we divide it by total request over the last 5 minutes. The service name is parameterized, so the same template works for any service. Now, what does this mean in practice? During a Canary deployment, Argo rollouts queries the Prometheus every minute. If the Canary success rate drops below 99% 3 times in a row, the rollout automatically aborts, and then the traffic returns back to this table. This is the power of combining progressive delivery with metric analysis. You do not need humans watching dashboards. The system watches it for you and responds faster than any human could. So the key insight is that defining success criteria in code means your rollback behavior is deterministic, auditable, and does not depend on someone waking up at 3 a.m. and doing it manually. Now let us talk about the hardest part of rollbacks, which is database schema changes. This is where most rollback strategies break down. Now here is the problem. Your V1 schema, let's say, has a users table with columns as ID, name, and email. Your V2 schema, let's say, renames name to first name and last name. So you deploy V2 and run the migration. The schema changes. Then you discover that V2 has a critical bug. Now you roll back to V1, but V1 expects a column called name which no longer exists, and then V1 will have bugs and crashes. This is why database rollbacks are so tricky. Unlike code, you cannot just switch to the older version. The database state has been modified. The solution here is backward compatible migration done in phases. So for example, in phase 1, you add the new columns, first name, last name. V1 code ignores columns it does not use, so V1 still works. You deploy V2 code only after the new columns exist. In phase 2, V2 code writes to both old and new columns. It writes to name and also to the first name, last name. It reads from the new columns. So if you need to roll back, V1 reads the old name column, whereas the V2 was still populating. In phase 3, you backfill existing data. So you copy the name values into the first name, last name for older records, and then you verify data consistency. In phase 4, only after you have rollback window has passed and V1 is no longer needed, you remove the old name column. So the key insight is that database migrations must be designed for rollback from the start. If you cannot roll back the schema change, you cannot safely roll back the code that depends on it. Feature flags, which are one of the most powerful tools for safe releases. The core idea is decoupling deployment from release. Without feature flags, deployment equals release. So when new code hits production, all users see it immediately. There is no way to turn it off without rolling back the deployment. With feature flags, deployment and release are two separate events. Deployment means code goes to the production, but the new behavior is behind a flag, so it is inactive. Release means the feature flag is enabled, making the new behavior visible to users. In code, this looks pretty simple. Your function checks if the feature flag, let's say new recommendation algorithm, is enabled for this user. If yes, it uses the new algorithm. If no, it uses the old algorithm. Both code paths exist in the production and the flag controls which one executes. This provides several powerful benefits. So first is safe releases. You can enable for 1% of the users first and monitor before going wider. Second is the instant rollback. If something goes wrong, you disable the feature flag. No deployment needed, no waiting for pods to restart. Third is A/B testing. Different users can get different experiences, letting you measure which performs better. Fourth is a trunk-based development, so you can merge incomplete features to main because they are hidden behind feature flags. So the key insight is that feature flags give you a runtime control plane for your features separate from the deployment pipeline, which dramatically increases your ability to release safely. Now let me show you how to implement a basic feature flag system. Here in this example, your feature flags class takes the configuration source and provides an isEnable method. This method takes the flag name, optionally a user ID, and a default value. First, you fetch the flag configuration. If the flag does not exist, you return the default value. Then you check the global kill switch. If the flag is not enabled, you return false regardless of other settings. Next, you check the rollout percentage. If the flag is 50% rollout and a user ID is provided, you use consistent hashing to determine if this user is in the rollout. You hash the combination of a flag name and user ID, then take let's say modulo 100. If the result is less than the rollout percentage, the user is in. If it is greater or equal, the user is out. So now why consistent hashing? Because the same user gets the same result every time. If user, let's say user ID 123 is in the 10% rollout today, they will still be in tomorrow. They will not flip-flop between old and new experiences randomly. Finally, you check the allow list. If the user is explicitly on the allow list, they get the feature regardless of rollout percentage. This lets you enable for internal testers or specific customers before rolling out more broadly. So the key insight is that a feature flag system is fundamentally a decision function. Given a flag name and context, should this feature be enabled or not? Now let me show you what feature flag configuration looks like in practice. A flag like, let's say, new checkout flow has several properties. Enabled is true, meaning the flag is active and can be evaluated. Rollout percent is 10, meaning 10% of users see the new experience. Allow list contains specific user IDs who should always see the feature regardless of rollout percentage. The description explains what the flag controls. The owner identifies which team is responsible, and created at and expires at track the flag's lifecycle. Another flag like dark mode might have rollout percentage at 100, meaning all users get it, but with the segments property, limiting it to premium users only. For usage patterns, there are several common practices and approaches here. A simple on-off flag like maintenance mode returns the maintenance page for all users when enabled. A user-specific rollout flag like a new search uses the user ID to determine whether to show the old or new experience. An operational flag like cached ETL seconds returns a value instead of just true or false, letting you tune operational parameters without deployments. This flexibility is why feature flags are so powerful. They are not just for feature releases, they can even control A/B test, operational parameters, kill switches, and more. So the key insight is that a feature flag configuration should include metadata like ownership and expiration to support flag lifecycle management. Now let us talk about managing feature flags well, because flags can easily become technical debt if not maintained properly. Every flag should follow a lifecycle. First, it is created, so the flag is added but disabled by default. Then next is testing, so enabled for internal users only. Then the next stage is rollout, which is gradual increase from 1% to 10% to 50% and then to 100%. The next stage is stable, so the flag has been set at 100% for 2 or more weeks with no issues. And finally is cleanup. So you remove the flag from the code and delete the dead code path that was never executed. That cleanup stage is critical. Here's what happens when you skip it. Your code has an if statement checking if a feature flag is enabled. That flag has been at 100% for 2 years. So the code then inside that if block is the only code that ever runs. And the else block is dead code, never executed, but it still exists. You are now maintaining two code paths, and new developers are now confused about which one matters. The fix is simple. After the flag has been stable for at 100% for 2 weeks, you should remove the flag. Delete the if statement, delete the else block. The new behavior becomes the only behavior. So the key insight is that feature flags are temporary by design. A flag that lives forever is not a feature flag, it is configuration, and it should be modeled differently. More best practices for feature flags. Naming conventions matter, so do not use names like, let's say, flag123 or test feature or something like that. These tells you absolutely nothing 6 months later down the road when someone is trying to understand your code. Instead, you should be using descriptive names like checkout single page flow or search ML ranking v2 or let's say payments per Stripe integration. The names should tell you what the flag controls. Documentation for each flag should include several fields. Description explains, what the flag does in plain English. Owner identifies which team is responsible for that flag. Slack channel tells you, let's say, where to ask questions. Jira ticket links your relevant project or feature. And rollout plan describes the intended progression. 1% in week 1, 10% in week 2, 50% in week 3, and 100% in week 4. Rollback procedure explains how to disable if something goes wrong. Cleanup date sets an expiration for when the flag should be removed. For production practice, you should review flags monthly. Any flag that has been at 100% for more than 2 weeks should be cleaned up. Set expiration dates when creating flags so you have a built-in reminder. You should treat flag cleanup as a regular maintenance, not optional housekeeping. So the key insight is that the effort to clean up flags is paid back many times over in code clarity and reduced maintenance burden. Now let us talk about deployment anti-patterns because understanding what not to do helps you avoid common mistakes. The first anti-pattern is big bang deployments. So this is where you accumulate 3 months of changes, deploy everything at once, and then hope that nothing breaks. But when something does break, you have no idea which of the 500 changes would have caused it. And then debugging is pretty problematic as well. Instead, you should be deploying multiple times per day with small incremental changes. Each deployment changes only one single thing. So when something breaks, you know exactly what caused it because you know exactly what changed. The second anti-pattern is no rollback plan. Your deploy function just runs, you just say kube control apply and hopes for the best. When the new version has problems, everyone scrambles to figure out how to undo it. Instead, your deploy function should record the previous version first, then apply the new version, then run health checks. If the health checks fail, automatically roll back to the previous version and alert the team. A rollback capability should be built into your deployment process, not improvised during incidents. So the key insight is that deployment anti-patterns usually come from optimizing for the happy path while ignoring the failure scenarios. Now let me cover a few more deployment anti-patterns. So third anti-pattern is deploying database and code together. You deploy code that expects a new column, then run the migration that adds a column. For the 30 seconds in between, your code is crashing because the column does not exist yet. Instead, you should be running the migration first. Wait for it to complete and replicate to all database replicas. Then you deploy the code that uses the new column. The schema change is always ahead of the code change. The fourth anti-pattern is feature flags without cleanup. Your code has nested if statements checking new flow, then let's say feature flag checking like new flow 2, v2 inside that, and then new flow v3 inside that. The actual business logic is buried under 3 layers of flag checks. Each flag was added in a different year and never cleaned up. Instead, you should be cleaning up flags after a full rollout. Set a rule that any code path that should have at most 2 active flags. Flag hygiene is as important as code hygiene. The fifth anti-pattern is no deployment windows. You deploy Friday at 5 p.m. and let's say you go for the home for the weekend, right? So then if something breaks, no one is around to fix it. and your users will suffer all weekend. That's why you should not be deploying on Fridays, so that to avoid incidents on the weekend. Instead, you should deploy on, let's say, on Tuesday morning when your whole team is available to monitor and respond. You should avoid deployments before holidays, before weekends, and before any period when the team will not be available. So the key insight is that deployment practices should account for what happens when things go wrong, not just when they go right. Now, let me summarize the key takeaways from our deployment strategy section. For CI/CD pipelines, there are 4 essential practices. First, build the immutable artifacts, build once, deploy the same artifact everywhere. Second, test before you deploy with unit tests, integration tests, and end-to-end tests. Third, scan for security vulnerabilities in both your code and your container images. Fourth, automate everything so deployments are consistent and reliable. For deployment strategies, match your strategy to your needs. Use the rolling update for most services and it provides zero downtime with low complexity. Use blue-green for critical services that need instant rollback capability. Use Canary for high-risk changes where you want to limit the blast radius. Use Shadow for validation scenarios where you want to test with production traffic without affecting users. Each strategy has trade-offs in risk, rollback speed, and complexity and cost, so you should be choosing based on your specific business requirements. Also, for rollbacks, there are 4 essential practices. First, every deployment must be rollback ready. If you cannot roll back, you should not be deploying. Second, automate the rollback triggers based on the metrics so you don't need to depend on human reaction time. Third, database changes must be backward compatible so that the rolling back code does not break against the current schema. Fourth, test your rollback procedure regularly because an untested rollback is not a reliable rollback. For feature flags, there are 4 essential practices. First, separate the deployment from release so code can exist in production before users see it. Second, use gradual rollout, which is 1% to 10% to 50% and to 100%. Monitor at each stage before expanding. Third, clean up the flags after full rollout to avoid accumulating flag debt. And fourth, document ownership and expiration for every flag so there is accountability for the cleanup. Now, in the next section, we'll move to security in production, where we'll cover how to protect our system and our users. Now, let's move to our next section, which is all about security in production. We will cover authentication, authorization, secrets management, network security, and data protection. But first, let us talk about security mindset. In an interview setting, you might say something like, okay, we'll work on authentication as a simple checkbox item. However, in production, the thinking is more like quote unquote, defense in depth, which means like where no single layer's failure compromises the whole system. In an interview, you might say something like, okay, we'll encrypt passwords. But in production, you need to go, much more in detail, and the thinking should be you need to assume the breach and limit the blast radius, because you design assuming that the attackers will eventually get in and then limit what they can access to. So that should be your approach. Similarly, in an interview, you might say, okay, that you will use HTTPS. However, in production, your thinking needs to be zero trust networking, where you verify every request even on the internal networks. So the key insight is that you should internalize that security is not a feature. It's a property of the system, so every design decision has security implications. When you choose how to restore data, where to put network boundaries, how to handle authentication, you are making security decisions whether you realize it or not. Security is also not something you added to the end. You must be woven into your part of your initial architecture from the beginning. So retrofitting security is very expensive, error prone, and often impossible for fundamental design choices. So as we go through this section, you should be thinking security as a property that emerges from good decisions throughout your system, not as a layer you add on top. Now let us start with authentication, specifically token-based authentication, using JWTs. So this is how most modern applications verify user identity. The flow works something like this. A user logs in with their credentials, and the auth server validates the credentials and issues a JWT, which is a JSON Web Token. The user stores the JWT, typically in browser, local storage, or a secure cookie. On subsequent requests, the user includes the JWT. Each service can validate the JWT without calling back to the auth server. A JWT has three parts separated by dots: header, payload, and signature. The header specifies the algorithm used for signing. The payload contains the claims, data about the user, like their user ID, email, roles, when the token was issued, and when it expires. And the third, signature, is a cryptographic verification that the header and payload have not been tampered with. Now here's an example payload. The subfield is the subject, typically the user ID. The email field contains the user's email. The roles field contains that that's their permissions. And the id field is that the issued id field with the timestamp when the token was created. The exp field is the expiration when the token becomes invalid. So now what makes JWTs so powerful is that any service can actually validate them independently. You check the signature against a shared secret or public key, verify the expiration has not passed, and read the claims. No database lookup is required for basic validation. So the key insight is that JWTs enable stateless authentication where any service can verify a user's identity without centralized session storage. Now let us talk about JWT best practices because JWTs are easy to implement wrong. First, you should be using short expiration times, typically 15 to 60 minutes for access tokens. Why? Because if a token is stolen, the window of vulnerability is limited. A token that expires in 15 minutes is only useful for 15 minutes. Second, you should use refresh tokens to get new access tokens without requiring the users to log in again. The refresh token has a longer expiration, maybe let's say 7 days, and is used only to get new access tokens. Sorry. Third, you should be storing tokens in HTTP only cookies instead of local storage. HTTP only cookies cannot be accessed by JavaScript, which prevents the XSS attacks from stealing the tokens. Fourth, you should include only necessary claims in the token. So for example, you should not be putting sensitive data like social security numbers, for example, in JWT tokens. Remember that JWTs are signed, but they are not encrypted, so anyone can read the payload. Fifth, always validate the signature server side. Never trust a JWT without the verification. So an unsigned or improperly signed JWT could be forged by an attacker. For the login flow, when a user authenticates successfully, you create both the access token with short expiration and the refresh token with longer expiration. You store a hash of the refresh token in your database. You return both tokens to the client. The access token is used for API calls, and when it expires, the client uses the refresh token to get a new access token. So the key insight is that the combination of short-lived access tokens and long-lived refresh tokens gives you both security and usability. Now let me show you how token refresh works in practice because this is how often where implementations go wrong. When a client calls a refresh access token with a refresh token, you first decode the refresh token to get the user ID. Then you look up the stored hash for that user's refresh token in a database. If the hash does not match what was provided, the token is invalid, either forged or already replaced by a newer one. Then you check if the refresh token has been revoked. This handles the logout case where a user explicitly invalidates their tokens. If the token is revoked, you reject the request. Now, if all checks pass, you issue a new access token with fresh expiration. So the client can now make authenticated requests for another 15 minutes. For logout, you need to handle token revocation. You add the refresh token to a revocation list, which you check during refresh. You also delete the stored refresh token for that user. This prevents the refresh token from being used again. So now why is this complexity necessary? Because JWTs are stateless. You cannot invalidate an access token once it has been issued. It will be valid until it expires. But you can invalidate the refresh tokens, which prevents getting the new access tokens. So the short access token expiration means any valid token become invalid within minutes of logout. So the key insight is that token revocation happens at the refresh token level, and short access token expiration limits how long a revoked session remains functional. Now let us talk about authorization, which is about controlling what authenticated users can do. So authentication answers, okay, who is this person? However, authorization answers, okay, what is this person allowed to do? The most common approach is role-based access control, which is essentially called RBAC. You define roles with set of permissions. An admin role might have read, write, delete, and manage users' permissions. An editor role might have read and write. A viewer role might only have read permission. So when checking permissions, you look up the user's role, get the allowed actions for that role, and check if the requested action is in that list. If not, you raise a permission denied error. RBAC is simple and works well for most applications, but sometimes you need more flexibility. So attribute-based access control, or ABAC, makes decisions based on multiple attributes. You might check that the user's department matches the resources department. For example, that the user's clearance level is high enough for resource classification, or that the action is in the user's allowed actions, that resource is not archived unless that user has archive access. All these rules must pass for access to be granted. So attribute-based access control, which is ABAC, is much more complex but much more flexible. You can express policies like, let's say, user can edit documents in their own department that are not archived and are not above their clearance level, without then creating a bunch of specific rules. So the key insight is that RBAC is simpler and sufficient for most of the cases, while ABAC provides fine-grained control when business rules are much more complex. Now let me compare RBAC and ABAC more directly and show a real-world authorization pattern. In terms of complexity, RBAC is simple while ABAC is complex. In terms of flexibility, RBAC is limited to predefined roles while ABAC can express any policy. In terms of maintenance, RBAC is easy because you just manage role assignments, while ABAC is harder because you're managing complex rule sets. For use cases, RBAC works for most applications, while ABAC is needed when you require fine-grained control based on multiple attributes. Now let me show you how resource level permissions, which is common pattern that goes beyond simple role checks. Consider a can edit document function. First, you check if the user is the document owner. Owners can always edit their own documents. Second, you check if there is an explicit share granting this user edit or admin permission on this document. Third, you check if the document belongs to the team the user is a member of, and if the team has the edit or admin permission. This layered approach is common in real applications, so if you have global roles but you also have resource-specific permissions, then this would be the case. For example, a user might be a viewer globally but have edit access to specific documents they own or that were shared with them. So the key insight is that real authorization systems often combine role-based and resource-based checks to handle both global permissions and specific access grants. Now let's talk about secrets management, which is about handling sensitive configurations securely. This includes API keys, database credentials, encryption keys, service account tokens, and certificates. Before we discuss how to manage secrets well, let us look at the anti-patterns, the things you should never do. First, you should never hardcode secrets in your code. Let's say if you have database URL variable with the password visible in your source file, that password is now in version control forever, and that you should never do, ever. That's not a good practice at all. Because anyone with access to your repo now will have your database password. Second, never commit secrets to Git, even in .env files. If a .env file is committed to your repository, it is available in the Git history, even if you later delete it. Git history is permanent. Third, never log secrets. If you log your connection string, including credentials, those credentials are now in your log aggregation system, visible to anyone with log access, potentially searchable and retained for however long you keep logs. These mistakes are extremely common and extremely dangerous. A single exposed database credential can lead to complete data breach. A leaked API key can result in authorization, unauthorized changes, or data access. So the key insight is that secrets require special handling throughout their lifecycle. How are they stored, how are they accessed, and how they are transmitted. Let me show you the progression from basic to production grade secrets management. The basic approach is environment variables. So your code reads something like database URL and API key from the environment variables instead of hard coding them. In Kubernetes, you create a secret resource and mount it as environment variables in your pod. This is better than hard coding because the secrets are not in your source code, but environment variables do have limitations. They are visible to anyone who can exec into the container. They do not support rotation without restarting the application, and managing them at scale becomes complex. The production approach uses a dedicated secrets manager. So with AWS Secret Manager, for example, your code calls get secret value with the secret name. The secrets manager returns the secret value which you parse and use. So what makes this better? Secrets manager provides access control. You can specify exactly what services can access which secrets. It provides audit logging so you know who accessed which secret when. It supports rotation so you can change secrets without restarting applications. And it centralizes management. All secrets are in one place with consistent policies. You configure which secret your application reads by environment variable, but the actual secret values are stored securely in the secrets manager, not in the environment variables. So the key insight is that dedicated secret managers provide access control, audit logging, and rotation capabilities that environment variables simply cannot match. Now let me show you how HashiCorp Vault, which is a popular choice for advanced secrets management, how it works and how it operates. So you create a Vault client class that connects to the Vault using the address and token from environment variables. The getSecret method reads the secret from path using Vault's key value version to secrets engine. But the real powerful feature is the dynamic secrets. The getDatabase credentials method does not read a stored password. Instead, it asks the Vault to generate a temporary database credentials just for this request. Vault connects to your database, creates a new user with a random password, grants appropriate permissions, and returns the credentials to your application. These dynamic credentials have a TTL, a time to live. After a few hours, Vault automatically revokes them. Your application can request new credentials when needed. Compare this to static secrets. Static secrets are long-lived, maybe years. These are shared across all instances of your application. Rotation is manual and requires coordination. If they are breached, the attacker has access for a very long time. Dynamic secrets are, however, short-lived, mostly at most hours. Each application instance gets unique credentials. Rotation is automatic, so if they are breached, the attacker has access only until the TTL expires, which might be just a few hours. So the key insight is that dynamic secrets dramatically reduce the blast radius of credential leaks because leaked credentials are unique to one instance and expire quickly. Now let us talk about secret rotation, which is about changing secrets without causing downtime. The rotation process has 4 phases. First, generate the new secret. Second, deploy your application configured to accept both the old and the new secret. Third, verify the new secret works. Fourth, remove the old secret. Now why is the accept both phase critical? Because during rotation, you might have some clients using the old secret and some using the new secret. If you instantly reject the old secret, those clients break. Let me show you an implementation. You create here a rotatable secret class that tracks both current and previous secret values along with the last refresh time. The refresh method fetches the latest secret from the vault, moves current to previous, and sets the new value as current. The validate method checks if a provided key matches either current or previous. This way, clients using either secret rotation are accepted during the rotation window. You set a periodic refresh, maybe every hour, so the secret automatically rotates. After the refresh, any client using the previous secret has until the next refresh to update. The key insight is that rotation requires a transition period where both old and new secrets are valid, which allow the clients to update without coordinated downtime. Let me close this section with network security and the principles of defense in depth. The idea is that no single security layer should be your only protection. You have multiple layers, each catching with what the other layer is missing. So traffic flows to secure several security layers. First is the WAF, which is Web Application Firewall, which protects against SQL injection, XSS attacks, and DDoS. Second is the load balancer, which handles the TLS termination and rate limiting. Third is the API gateway, which handles authentication and authorization. Fourth is the service mesh, which provides MTLS between the services and traffic policies. And fifth is the application layer, which does input validation and business logic checks. And sixth is the database, which has encryption at rest and access control. Each layer provides specific protections. The WAF catches common web attacks at the edge before they reach your infrastructure. The load balancer ensures encrypted connections and prevents individual clients from overwhelming your system. The API gateway verifies identity and permissions before requests reach your services. The service mesh encrypts all the internal traffic and enforces policies about which services can talk to which. The application validates that inputs make sense for your business logic. The database encrypts stored data and limits which application can access which tables. If any single layer fails or is bypassed, the other layers still provide protection. An attacker who gets past the WAF still has to deal with authentication. An attacker who steals credentials still cannot access encrypted data at rest. So the key insight is that difference in depth means security failures are contained rather than catastrophic, because multiple independent layers must all fail for a complete breach. Now let us talk about Zero Trust, which has become the gold standard for network security in modern production systems. For the long time, most organizations operated on what we call perimeter-based security. The idea was simple. If you're inside the corporate network, you are trusted. If you're outside, you are not. Think of it like a castle with a moat. Once you get past the drawbridge, you can walk around freely inside. The problem with this approach should be very obvious that, when you think about it, like what happens when an attacker gets inside? Maybe they compromised an employee's laptop through a phishing email. Maybe they exploited a vulnerability in a VPN endpoint. Once they're past that parameter, they now have access to everything. They can literally move laterally from system to system, accessing databases, internal APIs, sensitive services, all because the network trusts them implicitly. Zero Trust flips this model completely. The philosophy actually should be trust nothing by default, verify every single request, and always assume that a breach has already occurred. You're not being paranoid, you're just being realistic. In a world where breaches happen to even the most sophisticated organizations, designing a system to limit damage when a breach occurs is just good engineering. Now let us look at the 4 core principles of Zero Trust. The first is verify explicitly, which means you should authenticate every single request, not just the initial login. The second is least privilege, meaning every service and every user should have the minimal permissions they actually need to do their jobs and nothing more. The third is assume breach, which drives you to the design systems that limit the blast radius when something does go wrong. And the fourth is encrypt everything, and I mean literally everything, including the traffic between your own internal services, not just the traffic coming in from the internet. So the key insight here is that Zero Trust is not a security product you can buy. It is an architectural philosophy that shapes how you design every interaction in your system. Now let us talk about how Zero Trust actually gets implemented in practice, specifically through mutual TLS or MTLS for service-to-service authentication. In a traditional setup, when one service calls another, there is often no authentication at all. The assumption is that if the request came from inside the network, it must be legitimate. But we just discussed that why that assumption can be dangerous. So with MTLS, both sides of a connection present certificate to each other. The client proves its identity to the server, and the server proves its identity to the client. This means even an attacker somehow gets inside your network, they cannot impersonate one of your services without having the correct certificate. Now, looking at this Istio configuration, we are doing 2 things. First, we are setting up a peer authentication resource that enforces strict MTLS mode for all traffic in the production namespace. This means any service that tries to communicate without proper TLS certificates will be rejected. Then we have an authorization policy that goes even further. This policy says that only the API gateway service account, specifically the one at, let's say for example, cluster.local/ns/production/sa/API gateway is allowed to call the order service. And even then, it can only use get and post methods on the orders endpoints. Now, let's think about what this means in practice. Even if an attacker compromises your logging service, they cannot use that access to call your order service and steal customer data. The authorization policy explicitly denies that connection. So the takeaway here is that MTLS combined with authorization policies gives you defense in depth. You are not just relying on the network perimeter anymore. Every single service-to-service call is authenticated and authorized independently. Now let us talk about network policies, which gives you even more fine-grained control over traffic flow within your Kubernetes cluster. The fundamental principle here should be in default deny. Instead of allowing all traffic and then trying to block the bad stuff, you start by blocking everything and then explicitly allow only the traffic that should happen. Looking at this first network policy, we are creating a default deny ingress rule for the entire production namespace. The pod selector is empty, which means this policy applies to every pod in the namespace. And since we are only specifying ingress in policy types with no actual ingress rules defined, this effectively blocks all incoming traffics to all pods. Now with everything blocked, we need to explicitly allow the legitimate traffic flows. The second policy shows how to do this. This allow API to database policy targets pods with the label app database. Then it specifies the ingress traffic is allowed from pods with the label app API server, but only on TCP port, let's say 5432, which is a Postgres SQL port. So why does this matter? Imagine you have 50 different microservices in your cluster. Without network policies, any of those services can talk to any other service. If an attacker compromises your image processing service, they can immediately start probing your database, your user service, and your payment service. With network policies, the attack surface shrinks dramatically. Your image processing service can only talk to the specific services it needs to talk to. Everything else is blocked at the network level before it even reaches the application. The key insight is that network policies implement the principle of least privilege at the network layer. Each service can only communicate with exactly what it needs, nothing more. Now let us talk about encryption, which is one of the most fundamental aspects of protecting data in production systems. When we think about encryption, we need to consider three different states that data can be in. The first is in transit, which is the data moving over the network. You protect this with TLS or HTTPS. The second is at rest, which is the data stored on disk, in databases, and object storage. You protect this with encryption algorithms like AES 256 or full disk encryption. And the third is in use, which is data is actively being processed in memory. This is the hardest to protect and typically requires specialized hardware like secure enclaves. Now let us look at proper TLS configuration in Python. We are creating an SSL context and setting the minimum version to TLS 1.2. This is important because older versions like TLS 1.0 and 1.1 have known vulnerabilities. Then we are specifying a cipher suite that only includes strong modern ciphers. These ECDHE and DHE ciphers provide forward secrecy, which means that even if your private key is compromised later, past communications will remain secure. For database encryption, this PostgreSQL example shows a column-level encryption using PG crypto. We are encrypting a social security number before storing it. Even if someone gains unauthorized access to your database, they see an encrypted gibberish instead of actual SSN values. But here's an important point that many teams actually miss. Encryption is not just about checking a compliance box. You need to think about key management. Where do you store the encryption keys? How do you rotate them? Who has access to them? And if your encryption key is hardcoded in your application or stored in the same database as the encrypted data, you have not actually improved your security posture much. So remember, encryption protects data at multiple levels, but the value of encryption is only as good as your key management practices. Now let us talk about handling PII, which is personally identifiable information, which is one of the most sensitive aspects of building production systems. Not all PII is created equal. Different categories require different levels of protection. Direct identifiers like social security numbers and passport numbers require the highest level of protection because they can uniquely identify a person and are frequently used in identity theft. Contact information like email, phone, and addresses also require high protection. Financial data like credit card and bank account numbers also need the highest protection. Health information requires the highest protection as well and falls under specific regulations like HIPAA in the United States. And behavioral data like browsing history requires medium protection through privacy regulations. Are generally now tightening up the requirements here as well. Now let us look at the three key strategies for protecting PII. The first is tokenization. Instead of storing the actual sensitive value, you generate a random token and store that instead. The mapping between the token and the real value gets stored in a secure vault. Your application works with tokens and only when absolutely necessary does it retrieve the actual value. The second strategy is masking. This is when you need to show some data to users but not all of it. For a credit card, you might show only the last 4 digits while replacing the rest with asterisks. The user can verify that it's their card, but anyone looking over their shoulder cannot steal their full number. The third strategy is anonymization. This is about removing identifying information while preserving the analytical value. Instead of storing a user's exact birth date, you store their age group. Instead of storing the exact zip code, you store the region. This lets you do aggregate analysis without being able to identify specific individuals. The key insight here is that different use cases require different approaches. You should be asking yourself, okay, what is the minimum amount of PII I actually need for this feature? Then protect everything beyond that. Now let us continue our discussion of PII handling by looking at the data retention policies and GDPR compliance. A common mistake is keeping data forever because you might need it someday. This creates enormous liability, so every piece of data you store is a piece of data that can be breached, subpoenaed, or became a compliance violation. You should have clear retention policies that specify how long each type of data is kept and then automatically deleted when that period expires. Now, if you look at this data retention class, we have defined policies for different data types. User sessions should be kept for 30 days since they are only relevant while the user is actively using your service. Audit logs should be kept for 365 days or 1 year because you need them for security investigations, but not forever. Payment records should be kept for 7 years because of financial compliance requirements in many jurisdictions. And when a user deletes their account, their data should be fully removed within 30 days as required by the GDPR. The cleanup expired data method runs daily and automatically deletes any data older than its retention period. This is not an optional cleanup. This should be treated as a critical scheduled job that runs reliably. Now let us talk about GDPR specifically. The regulation grants users 4 key rights. The first is the right to access, meaning users can request a copy of all data you have about them. You need an endpoint that exposes the data in a readable format. The second is the right to deletion, meaning users can request that you delete all of their data. The third is the right to portability, meaning users should be able to get their data in a machine-readable format so they can take it to a competitor. And the fourth is the right to rectification, meaning users can correct the inaccurate data about themselves. So the takeaway is that the data protection is not just about security, it is about respecting user rights and building systems that make compliance automatic rather than afterthought. Now let us talk about rate limiting, which is one of the most important defenses against API abuse. Without rate limiting, a single malicious user can overwhelm your entire system. They could essentially, run credential stuffing attacks, trying millions of username password combinations. They could even abuse this API to scrape data or perform DDoS attacks, which is denial of service attacks. They could also rack up enormous cost if your API call is expensive, for downstream services. Looking at this rate limiter class we have here, the implementation is pretty straightforward, but it's still pretty effective. We are using Redis as our backing store because it is fast and handles distributed systems well. The isAllowed method increments a counter for each unique key and checks if it has exceeded the limit. On the first request, we set an expiration on the key so the counter automatically resets after the time windows pass. In this example, we are allowing 100 requests per minute per user. When a user exceeds this limit, we return an HTTP 429 status code, which means too many requests. We also include a retry after a header telling the client how long to wait before trying again. So why Redis for this? Because in a distributed system, you might have 20 different servers handling requests. If each server tracked rate limits independently, a user could just spread their requests across servers and bypass your limits. Redis gives you a centralized counter that all servers share. The key insight here is that rate limiting should be one of the first things you implement on any public API. It protects you from both malicious actors and from well-meaning users who accidentally create infinite loops or have buggy clients. Now let us go deeper on rate limiting by looking at tiered limits and different limits for different endpoints. Not all users should have the same limits. Anonymous users who have not even logged in should have very restricted limits, perhaps 10 requests per minute. This prevents abuse from bots and scrapers. Free tier users get a reasonable limit, let's say like 100 requests per minute. Paying customers get even more generous limits at like 1000 requests per minute. And enterprise customers with dedicated support and infrastructure can have much higher limits at let's say like 10,000 requests per minute. This tiered approach aligns with the cost and the usage. So, users who need higher limits are paying for the infrastructure to support them. Now, let us talk about the rate limit headers. Good API design include headers that tell clients their current, rate limit status. The X rate limit header actually shows their maximum allowed request. X rate limit remaining shows how many requests they have left in the current window. And X rate limit reset shows when the window resets. This transparency lets well-behaved clients implement their own throttling and avoid hitting your limits. Finally, different endpoints should have different limits. A longer endpoint should have a very strict limit of perhaps let's say 5 attempts per minute to prevent brute force attacks. Expensive operations like search, which might query multiple databases and do complex computation, should have lower limits like let's say 30 per minute. And standard CRUD operations can have higher limits since they are cheap to process. So the key takeaway is that rate limiting should be granular and thoughtful. One size does not fit all. You need to think about the cost of each endpoint, the risk of abuse, and the legitimate usage pattern of your users. Now let's talk about input validation, which operates on a simple but critical principle, which is that you should never trust your user input. Let me walk you through the most common attack vectors. SQL injection happens when an attacker submits input like a semicolon followed by let's say drop table users, and your application naively concatenates that into a SQL query. Cross-site scripting or XSS happens when an attacker submits JavaScript in a form field and your application renders it back to other users, allowing the attacker to steal cookies or credentials. Path traversal happens when an attacker submits a file name like let's say ///password to access files outside the intended directory. And command injection happens when users input and get passed to the shell commands. Looking at this pedantic model, we are doing proper input validation. The email field has a maximum length of 255 characters. The username field must be between 3 and 50 characters and can only contain alphanumeric characters and underscores, which is enforced by the regex pattern. The age field must be between 0 and 50 to prevent obvious invalid values. And we also have custom validators. The validate email method here uses a regex to check the email format and converts it to lowercase for consistency. The validate age method here provides a clear error message if someone tries to submit an invalid page. And why is this important? Let's think about that for a second. Because attackers will submit anything they can think of. They will put JavaScript in your email field. They will put SQL commands in your username field. They'll submit negative numbers and massive numbers and special characters. Validation is your first line of defense. The key insight is that validation should happen at the boundary of your system before untrusted input touches any of your business logic. Now let us look at the specific examples of SQL injection and XSS prevention because these are the two most common and dangerous vulnerabilities. For SQL injection, let's look at the bad example first. We are building a SQL query using an F string directly concatenating the username variable into the query. If an attacker submits admin apostrophe dash dash as the username, and the resulting query will become select from all users where username is equal to admin, the two dashes start a SQL statement which comments out anything after it, like a password check. The attacker has just bypassed authentication. The correct approach is to use parameterized queries. Instead of concatenating variables, you use placeholders, which in this case is %s, and pass the values separately. The database driver then properly escapes the input, treating it as data rather than SQL code. If an attacker submits admin apostrophe dash dash, the query searches for the user literally named that string rather than executing as a SQL. For XSS, the bad example actually directly embeds user input into the HTML. If a user submits comment containing a script tag that calls steal document.cookie, that JavaScript will execute in every other user's browser when they view the comment. The correct approach is to escape HTML characters. The HTML.escape function converts special characters into their shitty HTML entities. The less than sign becomes ampersand the semicolon. The script tag becomes the visible text rather than the executable code. So remember, parameterized queries for SQL and output encoding for HTML are non-negotiable practices. Every framework has built-in tools for these, so please use them. Now let us talk about audit logging, which is essential for security monitoring, incident response, and compliance. Audit logs should capture all security-related events. For successful logins, you should capture the user ID, their IP address, the timestamp, and the authentication method they used. For failed logins, capture the attempted username, IP address, timestamp, and the reason for failure, since this helps identify brute force attacks. For permission denied events, capture who tried to access what resource and what action they attempted. For data access events, capture who accessed what type of data and which specific records. For data modifications, capture the before and after values so you can trace what has changed. And for admin actions, capture everything, as these high privilege operations should be fully auditable. Looking at this audit log class, we are capturing comprehensive information for every event. We record the timestamp in UTC for consistency across time zones. We capture the event type and user ID. We grab the client IP address and user agent, which help identify the device and location. We include the trace ID so we can correlate this audit entry with other logs from the same request, and when we include the specific details of what happened. Notice that we are adding an immutable audit store. Audit logs should not be editable even by administrators. If an attacker gains admin access, they should not be able to cover their tracks by modifying the audit logs. Many organizations write audit logs to a separate system with write-only access. Finally, we check if the event is suspicious and alert the security team if it is. Audit logs are not just for compliance, they are an active security monitoring tool. The key takeaway is that comprehensive audit logging is how you investigate incidents after they happen and detect attacks while they are happening. Suspicious activity from your audit logs. This security monitor class shows 3 common detection patterns. First, we look for multiple failed login attempts. If there are 5 or more failed logins from the same user within 15 minutes, that is likely a brute force attack. We alert the security team and temporarily block the further attempts from that user. Second, we check for logins from a new locations. If a user has always logged in from IP addresses, let's say in New York, and suddenly they start logging in, they're logging in from an IP address in UK or France, that might be a legitimate travel or it might be a compromised account. Either way, it deserves attention. Third, we implement impossible travel, detection. So for example, if a user has logged in from New York 30 minutes ago and now they're logging in from Tokyo, That is physically impossible. No one can travel, like thousands of kilometers in 30 minutes. There is a strong signal that account has been compromised and someone else is using it from a different location. The implementation calculation calculates, here the distance between the last login location and the current one, then divides that by the time elapsed. If the speed exceeds, let's say 500 miles per hour, which is faster than commercial air travel, something suspicious is happening. Now, these detection patterns catch real attacks. I have seen teams discover breaches within minutes because their monitoring system flagged impossible travel, while without such monitoring, the breach might have gone undetected for much longer period of time. So the key insight is that audit logs are only valuable if you actually analyze them. You should build automated detection for common attack patterns and have a process for responding to those alerts. Now let us talk about the common security anti-patterns that are actually happening in our industry quite a bit. So the first anti-pattern is security by obscurity. So in this example, someone has, let's say, created an admin panel at a URL with random characters, thinking that nobody will guess it. So that is not security. Attackers use automated tools that discover these endpoints pretty quickly. So web servers, they get leaked. Developers sometimes they mention URLs and commit messages. That is not ideal. The correct approach is to implement proper authentication and role-based access. So you should be using a clear, obvious URL like, let's say, /admin, but require that the user be authenticated and have the admin role. The second anti-pattern is trusting clients and validation. In this example, the client sends a price along with the order, and thus the server trusts that price. An attacker can actually modify the request to set their own price at 1 cent instead of the actual amount. The correct approach is to always validate on the server side. Look up the item by its ID and use the price from your database, not the price sent by the client. Client-side validation is for user experience, server-side validation is for security. You need both, but never rely solely on the client. So these anti-patterns persist because they feel like work, but you deploy, let's say, the URL and nothing happens. Bad happens, but you trust the client price, and again nobody cheats. But thing is, the security failures are silent until they're catastrophic. So you need to keep these anti-patterns in mind and try to avoid them. And the takeaway here is that to assume that attackers actually know your system pretty well. You should always be assuming that they can modify any client-side data. So make sure you design your security assuming the worst-case scenario, because eventually something like that will happen and you need to be prepared for that. Now let us continue with two more pretty important anti-patterns. So the third anti-pattern is overly permissive CORS, which stands for cross-origin resource sharing. In this example, we are setting access control allow origin to a wildcard asterisk, allowing essentially any website to make requests to our API. This means a malicious website could make requests to your API on behalf of unsuspecting users who visit it, potentially stealing their data and performing actions without their knowledge. The correct approach is to maintain a whitelist of allowed origins. So for example, only your own domains like let's say myapp.com and admin.myapp.com should be allowed to make cross-origin requests. When a request comes in, you should be checking if the origin is in your allowed list, and only then you include the CORS header. This will prevent other websites from abusing your API. The fourth anti-pattern is essentially logging the sensitive data. So developers often add detailed logging during debugging and forget to remove it. Logging username and password like this is a bad example, means that anyone with access to your logs now essentially has access to your credentials. So this includes your logging infrastructure, your log aggregation service, and anyone who get access to those systems. The rule is simple. You should be never logging passwords, tokens, session IDs, credit card numbers, or any other sensitive data. If you need to track authentication attempts, log the username but never the password. So now, why do these anti-patterns persist? Because they are essentially easy and the consequences are not immediate. Permissive CORS makes development faster when you're building that front end. Detailed logging helps you debug issues, but both create vulnerabilities that attackers will eventually find. So the key takeaway is that to build security habits into your development process, code review should catch these issues before they even reach production. Now let me summarize the key security practices we have covered today. For authentication, you should be using short-lived JWT tokens with refresh tokens. Access tokens should expire in minutes, not hours or days, limiting the window of vulnerability if one is stolen. You should be storing tokens securely using HTTP-only cookies, which cannot be accessed by JavaScript and are therefore protected from XSS attacks. And you should also be implementing proper logout by revoking tokens, not just by deleting them from the client. For authorization, you should be using role-based access control or RBAC for most applications. It is well understood, easy to audit, and sufficient for most needs. You should always be checking permissions at the resource level, not just at the API level. A user might have permission to view some orders, but not all orders, and you should be following the principle of least privilege. Every user and every service should have only the permissions they actually need. For secrets management, you should never be hard-coding your secrets in your code or configuration files. This includes, database passwords, API keys, or encryption keys. You should be using a dedicated secrets manager like HashiCorp Vault or AWS Secrets Manager. These tools provide secure storage, access control, and audit logging. You should be rotating secrets regularly, ideally automatically, and use dynamic secrets when possible, where the credentials are generated on demand and they expire after use. These practices form the foundation of secure systems. So each one addresses a specific category of attack, and together they provide defense in depth. Now let us continue our security summary with network security, data protection, and API security. For network security, you should be embracing zero trust and verify every request regardless of where it originates. You should be implementing MTLS for service-to-service communication so that the services authenticate each other, not just the clients to services. You should be using network policies with the default deny approach, explicitly allowing only the traffic that should occur. And then you should be deploying a web application firewall or WAF for traffic coming from the internet to catch common attacks before they reach your application. For data protection, you should be encrypting data both in the transit and at the rest. So use TLS for all the network communication, including between your own internal services. You should be using AES 256 or similar strong encryption for stored data. You should be handling PII with special care using tokenization, masking, and anonymization as appropriate. And then you should also be implementing data retention policies that automatically delete data when it's no longer needed. Also, you should be supporting GDPR rights, including access, deletion, portability, and rectification. For ABAC security, you should be implementing rate limiting at multiple levels per user, per IP, and per endpoint. You should also be performing input validation on the server side for every piece of data that comes from clients. You should be using parameterized queries, not string concatenation, for all the database operations. And you should be maintaining comprehensive audit logging that captures all security level relevant events. Security is not a feature you add at the end. It is a mindset that influences every design decision. So coming up next, we'll be shifting to a different challenge, which is the cost optimization as a super important area. Now let us talk about cost optimization, which becomes increasingly important as your system scales. The flow of cost optimization starts with visibility, meaning you need to understand where your money is going. Then comes the right sizing, where you match your resource to the actual usage. And then the reserve capacity, where you commit to predictable workloads for discounts. Then you consider the spot and preemptive instances, where you use spare capacity for fault-tolerant workloads. And finally, architecture optimization, where you design your system for efficiency from the ground up. So why does the cost matter so much? At the small scale, cloud costs are very manageable, so a startup spending $10,000 per month can optimize 10% and let's say save $1,000. That is pretty nice, but it's not transformational. But as you grow, those percentages become enormous. A mid-sized company spending, let's say, $1 million per month would save, $10,000 from the same optimization. And enterprise spending, $10 million per month will save even more money, like $1 million, because the 10% of the bigger amount for bigger company is much bigger absolute savings. So here's a key insight that many teams miss. At scale, small efficiencies become massive costs. A query that is 10 milliseconds slower than it needs to be does not sound like a big deal. But if that query runs a billion times per month, those extra milliseconds translates to thousands of additional compute hours, which translate to real dollars. Cost optimization is not about being cheap, it's about being efficient. The money you save on wasteful infrastructure can be invested in building better products, paying your team better, or simply having better margins. So now let us look at how to do this systematically. So before you can optimize your cost, you need to understand where your money is going. A typical cloud cost breakdown, looks something like this. So for example, compute, which includes VMs, containers, and serverless functions, usually accounts for 40 to 60% of your bill. Storage includes object storage, databases, and backups. That typically runs between 15 to 20%. Now, data transfer costs, which includes the egress to the internet, CDN, and cross-region traffic, often surprise teams at around 10 to 20%. Managed databases like RDS, DynamoDB, and Redis account for another 10 to 20%, and the remaining 5 to 10% covers monitoring, security tools, and miscellaneous services. The most important thing you can do for cost visibility is to tag all your resources. So for example, this CloudFormation example here shows proper tagging. So we are tagging the instance with this environment, which is a production. We are tagging the team that owns it, which is platform. We are tagging the service it belongs to, which is API gateway. And then we are including a cost center code for financial tracking. With consistent tagging, you can answer critical questions. For example, which team is spending the most, which service costs the most to run, and how much are we spending on production versus development versus testing. Without tags, your cloud bill is just like one big number, and optimizing a single big number isn't not possible. So the first step in cost optimization is visibility. So you should be tagging everything and enforce tagging as part of your deployment process. Do not let resources be created without proper tags. Now let us look at how to build cost monitoring and anomaly detection. This generate cost report function here queries your cloud provider's cost data grouped by service, team, and environment. Then it calculates month-over-month trends so you can see if the costs are increasing or decreasing. It also runs anomaly detection to catch unusual spikes. If anomalies are found, it automatically alerts the finance team. The anomaly detection logic here is pretty straightforward but effective. For each service, we compare the current cost to the historical average. If the current cost exceeds the average by more than 2 standard deviations, we flag it as an anomaly. This catches situations like someone accidentally leaving expensive GPU instances running, or a misconfigured autoscaling policy that spins up hundreds of unnecessary instances. So why is anomaly detection important? Because cloud costs can spiral out of control very quickly. A bug in your code could cause infinite retries that hit an expensive API millions of times. A developer could spin up a test environment with production-size resources and then just forget about it. Without anomaly detection, you might not notice until you get a bill that is 10 times higher than expected. So the key insight here is that cost visibility should be continuous, not a monthly review. You should be setting up dashboards that show real-time cost. You should be setting up alerts that fire when spending exceeds the thresholds. And you should be, making cost awareness part of your team's daily operations. Now let us talk about right sizing, which is about matching your resources to actual usage. The problem is that teams almost, always over provision. They think that they might need 16 vCPUs and 64 GB RAM someday, so they provision that now. But when you look at the actual usage, the average is often only around 2 vCPUs and 88 GB of RAM. That means 12.5% utilization and 87.5% of your cost is being wasted. So this analyze instance sizing function here shows how to do right sizing systematically. It pulls the CPU and memory utilization metrics for the past 14 days, then calculates the 95th percentile, not the average. So now why P95? Because you would want to handle your peak loads, not just the average load. Then it adds a 20% headroom to be safe and finds the smallest instance type that meets those requirements. Let me give you a few concrete numbers. Say your current instance is an M5.4x large, which costs around $0.768 per hour. The analysis shows that your P95 CPU usage is 25% and P95 memory is 30%. With 20% headroom, you need an instance with 25% plus 5% capacity, which is roughly 30% of 16 vCPUs, meaning roughly 5 vCPUs. You could downsize that to an, let's say M5.x large at $0.12 per hour. That is a 75% cost reduction on that single instance. Now, if you multiply that across hundreds of instances, so that will be a huge cost saving. That is why, right sizing is often the single biggest cost optimization opportunity. The takeaway is here that to analyze the actual usage data, you should not, you should be doing that instead of guessing around, what you might need. So right size based on your P95 plus headroom and review the sizing quarterly as your traffic patterns change. Now let us talk about choosing the right instance types and implementing autoscaling. Different workloads need different instance families. For web servers with balanced CPU and memory needs, use general purpose instances like T3 or M65. For batch processing that is CPU heavy but does not need much memory, you should be using compute optimized instances like C6i. For databases that need a lot of memory to cache the data, use memory optimized instances like R6i. For machine learning training, you shouldn't use GPU instances like P4D. And for burstable workloads that spike occasionally, use burstable instances like T3, where you pay for the burst capacity rather than the sustained high performance. So this Kubernetes horizontal pod autoscaler configuration shows proper autoscaling. We are setting min replicas to 2, which ensures that we always have redundancy even during low traffic. We are setting max replicas to 20, which caps our scale to prevent dynamic cost. And we are triggering scaling, at 70% CPU utilization. So why 70%? Because you would want some headroom. If you scale at 90% utilization, by the time new instances are ready, you might already be overwhelmed. 70% gives you room to handle traffic spikes while new capacity spins up. Autoscaling is how you get the best of both worlds. You scale up during peak hours to handle the load and scale down during quiet periods to save money. Without autoscaling, you are either over provisioned during quiet hour times or under provisioned during peaks. The key insight is that right sizing is not a one-time exercise. It should be automated and continuous. Your traffic patterns change, your code efficiency changes, and your resources needs change with them. Now let's talk about reserve capacity, which is about trading flexibility for savings. Cloud providers offer several pricing models. On-demand pricing has no commitment and no savings, but full flexibility. Reserve instances with 1-year commitment gives you 30 to 40% savings. Reserve instances with a 3-year commitment gives you 50 to 60% savings, but very low flexibility since you're locked in for 3 years. Saving plans offer a middle ground with 30 to 50% savings with and medium flexibility. The key question is, what workload should you preserve? The answer is your baseline steady state workload. So look at your usage over the past few months. What is the minimum number of instances you always have running, even during your quietest periods? So reserve that baseline. Everything over the baseline, your variable and burst capacity stays on demand. Now let me give you an example. Say you have a minimum of 10 instances always running, but during peak hours you scale up to 50 instances. You should reserve those 10 baseline instances, saving 30 to 40% on the 60% of your total instance hours. The extra 40 instances during peaks stay on demand and giving you flexibility. The math works out favorably. If your steady state is 60% of your total compute, you save 40% on that through reservations, you save 24% overall, even with the variable portion at full price. So the takeaway is this: is to reserve your baseline, not your peak. Analyze your historical storage, historical usage to actually find the steady state minimum, and then you commit to that. Now let us look at how to calculate the optimal commitment level. This calculate optimal commitment function here analyzes 90 days of hourly cost data to find your safe baseline. It calculates the 10 percentile of hourly cost. So why P10? Because that represents your consistently low baseline. Even during your quietest periods, you are spending at least this much. This is the amount you can safely commit to without risk of overcommitting. Then the function calculates the annual cost under two scenarios. First, the on-demand scenario where you pay full price for everything. Second, the savings plan scenario where you pay 60% of normal price, which is a 40% discount for a committed amount and full price for everything above that. The difference between these two is your annual savings. For many organizations, this is hundreds of thousands of dollars. A few important considerations when committing. First, commit to P10, not the average. If you commit to your average usage, you will be overcommitted during quiet periods. P10 is conservative and safe, so you should consider that. Second, you should be using saving plans over specific reserve instances when possible. Savings plans apply across instances types and even across regions, giving you flexibility to change your infrastructure without losing your discount. Third, you should be reviewing annually. Your baseline chart changes as your business grows, so what was the right commitment a year ago might not be right for your next year. So you need to change and learn and adapt to that. So the key insight is that commitment discounts are free money if you calculate correctly. You are going to run that baseline capacity regardless, so you might as well pay less for it. Now let us talk about spot instances, which can save you 60 to 90% compared to on-demand pricing. Spot instances are spare capacity that cloud providers sell at a steep discount. The catch is that they can be interrupted with just 2 minutes of notice when the provider needs their capacity back. This makes them unsuitable for some workloads but perfect for others. Good candidates for spot instances include batch processing jobs that can checkpoint their progress, CI/CD build agents that can be replaced without losing state, data processing pipelines that can retry from the last checkpoint, development and testing environments where occasional interruption is acceptable, and stateless web workers if you have proper handling for graceful shutdown. Bad candidates for spot instances include a single point of failure where interruption means downtime, stateful services without replication, long-running transactions that cannot be interrupted, and real-time critical systems where even brief interruption is unacceptable. The economics are pretty compelling. If you are running 100 instances for batch processing at $0.10 per hour on demand, that is $72,000 per month. With Spot at a 70% discount, that is $21,000 per month, so you save over $50,000 monthly. The key insight is that Spot instances require you to design for failure. Your workload needs to handle interruptions gracefully. But if you can do that, then the savings are pretty huge and enormous, and you should definitely consider that. Now let us look at how to actually implement Spot instance handling. This check spot interruption function here queries the EC2 instance metadata service. AWS provides a special endpoint that returns the termination time when a spot interruption is imminent. You should poll this endpoint every few seconds. When interruption is detected, the graceful shutdown function kicks in. First, it stops accepting new work. No new requests or jobs should be routed to this instance. Second, it completes the in-flight request with a timeout. You have about 2 minutes, so give current work 90 seconds to finish. Third, it saves any checkpoint state. For batch processing, this might mean saving the progress marker so that the next instance can resume where this one left off. The key is that your application must be designed to handle this. If your batch job processes records 1 through a million gets interrupted at 500,000, it needs to save that progress marker. So when a new instance picks up the job, it should resume from 500,001 and not start from record 1, which is the beginning. For web applications, the pattern is simpler. Stop accepting new requests, let the existing request complete, and let the load balancer route new traffic to other instances. As long as you have multiple instances, users should not notice individual interruptions. So the key takeaway is that the spot savings require engineering investment. You need graceful shutdown handling, checkpointing for long-running work, and proper load balancing. But once you have the infrastructure, you can safely use spot instances for a significant portion of your workload. Now let us look at mixed instance strategies which combine spot and on-demand for more reliability. The AWS autoscaling group configuration shows here a best practice approach. The on-demand base capacity is set to 2, meaning you always have at least 2 on-demand instances that cannot be interrupted. And this ensures that you never go to zero capacity during a widespread spot interruption. And then on-demand percentage above base capacity is actually set to 20, meaning for every 5 instances above the base, 1 is on-demand and 4 are spot. The spot allocation strategy is set to capacity optimized, which chooses spot pools that are least likely to be interrupted. Notice that we are also specifying multiple instance type overrides, so C5.xlarge, C5a.xlarge, C5n.xlarge, and C4.xlarge. This diversification is important because spot interruptions tend to happen to specific instance types in specific availability zones. By being flexible about which types you use, you reduce the chance that a single interruption event takes down many of your instances. The Kubernetes configuration shows how to handle spot nodes. We add a toleration so pods can be scheduled on spot nodes, which typically have a taint to prevent pods from landing there by default. Then we add node affinity that prefers spot nodes but allows on-demand as a fallback. So the key insight is to never go all in on spot. So use a mixed strategy where you have a reliable on-demand base and you use spot instances for the variable portion. This gives you the most of the savings while maintaining reliability. Now let us talk about storage optimization, which is about matching your storage type to your access patterns. Different storage tiers have dramatically different costs. SSD storage like GP3 costs the most because it provides on the millisecond access times, which is appropriate for active databases. HDD storage like ST1 costs less and it still provides millisecond access for sequential reads, which is good for logs and analytics. S3 standard costs even less and is good for frequently accessed objects. S3 infrequent access costs roughly half of the standard and is good for data access monthly. And S3 Glacier costs a fraction of standard, but it takes hours to retrieve, making it suitable only for archives you really need. The mistakes teams make is storing everything on the most expensive tier. Your database needs SSD, but your 3-year-old log files do not. This S3 lifecycle policy shows that how to automate the tiering process. Files in the log prefix automatically move to infrequent access about after 30 days, then to Glacier after 90 days, and then they get deleted after 365 days. You set this up once and you then forget about it. Data automatically moves to cheaper tiers as it ages. The cost difference over here is substantial. Say you have 100 TB of logs. On S3 standard, that costs around $2,300 per month. On Glacier, it costs around $100 per month. If those are old logs you rarely access, you are wasting $2,200 per month by not tiering. The key takeaway is that to understand your data access patterns, match each dataset to the appropriate tier. Automate the movement with lifecycle policies so it happens without manual intervention needed from your part. Now let us talk specifically about database costs, which are often one of the largest line items on cloud bills. Several factors drive the database cost. Instance size is typically the biggest factor, and right sizing based on actual CPU and memory utilization will help here. Storage costs include both capacity and IOPS, and you should provision only the IOPS you actually need based on your query patterns. Backups cost money as well, and you should optimize retention to keep what you need for compliance and disaster recovery, but not more. Read replicas double or triple your costs, so you use them only if you actually need read scaling or regional distribution. Multi-availability zone deployments also doubles your costs, but is required for production workloads that need high availability. But here is something many teams overlook. Query optimization can reduce the database cost more than any other infrastructure change. Now consider this example. A poorly optimized query takes 500 milliseconds. It runs, let's say, 10,000 times per day, consuming 5,000 seconds of database CPU time daily. After adding proper indexes and rewriting the query, it takes 50 milliseconds. Same 10,000 executions now, but now only 500 seconds of CPU time. That is a 10 times the reduction in your database load. So what does this mean in practice? You might be able to downsize your database instance from an R5.2x large to an R5.x large, saving $500 to $5,000 per month depending on your provider and region. That the cheapest compute is the compute you do not use. Optimize your queries before throwing more hardware at the problem. Now let us talk about data transfer costs, which are often called the hidden cost of cloud computing. Cloud providers typically do not charge for data coming in, but they do charge for significantly for data going out. Same region transfers are usually free or cheap. Cross-region transfers cost around $0.02 per gigabyte, and transfers to the internet cost around $0.09 per gigabyte. These numbers seem small until you multiply them by terabytes. Now let's look at this code optimization example. The bad approach queries all columns with select star and returns the full user objects. Each user might be 10 kilobytes of data. With million users, that is 10 GB of egress. And at $0.09 per gigabyte, that is $900 for a single API response. The good approach query is only the columns you need, which is ID and name. Each user is now 100 bytes, same million users, but now they are only 100 MB of egress. That is $9 instead of $900. Now, for serving the static content like images, CSS, and JavaScript, you should be using a CDN. Without a CDN, serving 1 TB of static assets from your origin costs around $90 per month in egress. With the CDN, like let's say CloudFront, the CDN cost is about $8.50 per month, and your origin egress drops to about $5 per month since most requests are being served from the CDN edge. That is a saving of $80 per month, and this scales linearly with traffic. The key insight is that to deliberate about what data you need to transfer and from where, you should be only returning the fields that your clients need. You should be caching aggressively at the edge, and be especially careful about the cross-region transfers. Now let us talk about building cost efficiency in your architecture from the start. A common question is whether to use serverless or containers. The answer depends on your traffic pattern. Serverless has zero cost when idle. Your function does not run, you do not pay. Containers have a minimum cost because you need at least some pods running to avoid the cold starts. But serverless has cold starts that can add 100 milliseconds to 5 seconds of latency on the first request. The break-even point is typically around 10 requests per second sustained. Below that, serverless is cheaper because you are not paying for idle time. Above that, containers become more economical because you have eliminated the cold start overhead, and container pricing is lower per request at the volume. Now let us talk about caching, which might be the single highest ROI optimization you can make. Say each database query costs around 0.0001 in compute time. You run 10 million queries per day, which costs now $1,000 per day or $30,000 per month. Now, if you add Redis cache for let's say $100 per month with a 95% cache hit rate, you now run only 500,000 database queries per day. So your database costs drop to $1,500 per month. Total cost with cache is $1,600 per month, and you have just saved $28,000 per month. The key insight here is that the architecture decisions made early have compounding effects on cost. A system designed for efficiency from the start will always be cheaper to run than one where efficiency was bolted on later. Patterns that impact cost, which is asynchronous processing and compute efficiency. The synchronous approach to order processing has a client waiting while you validate the order, charge the payment, and update the inventory, and then send a confirmation email. The entire chain takes, let's say, around 760 milliseconds, and your server is busy for the whole duration. You need enough server capacity to handle all the concurrent requests through this entire flow. However, the asynchronous approach validates the order immediately, which takes roughly 10 milliseconds. Then it queues the rest for the background processing and returns the response. The expensive operations like payment processing and email sending happen now asynchronously. Your web server can now handle 76 times more requests with the same resources because each request only takes 10 milliseconds instead of 760. For compute-heavy workloads, choosing the right compute time matters enormously. Say you need to process 1 million images per day. Using general-purpose C5.xlarge instances, you can process 1,000 images per hour. So you need about 42 instances running around the clock. That will cost you around $3,600 per month. But using GPU instances optimized for image processing, you can process 10,000 images per hour. You only need 4 instances running for 100 hours. That will cost you around $1,200 per month. So the right tool for the job will actually save you 67%. So the takeaway is to think about efficiency at the architecture level. Asynchronous processing reduces the resources needed for each request. Specialized compute reduces the time needed for specialized workloads. Both translate directly to local costs, so you should be considering both approaches when doing system design in production. Now let us talk about cost governance, which is about preventing surprises before they happen. This create per cost budget function shows how to set up a proper budget alerts. So we are creating a $50,000 monthly budget for the production environment. Then we set up two types of notifications. The first notification triggers when actual spend reaches 80% of the budget. That is an early warning. You still have headroom, but you should investigate why costs are higher than expected. The second notification triggers when forecasted spend exceeds 100% of the budget. Cloud providers can predict your end of month spend based on your current trajectory. If this forecast exceeds your budget, you want to know immediately so you can take action before the month ends. Notice that we are using both email and SNS for notifications. Email goes to humans who can investigate. SNS can trigger automated workflows like spinning down non-critical environments or paging the on-call engineer. The key is to set budgets at multiple levels. You should be having an overall organization budget. You should be also having a per team budget so that the teams are accountable for their spending. And also you should be having per environment budgets so you catch runaway cost in development or staging before they become production issues. So the cost governance is not about being restrictive. It's about being aware of the costs. So teams should know what they are spending and be empowered to make informed decisions about cost versus capability trade-offs. Now let's look at automated cost controls for when alerts are not enough. So the cost card class here runs hourly and checks if daily spending has exceeded thresholds. At 80% of the daily limit, it sends a warning. Teams can investigate and decide if the elevated cost is expected, but if spending exceeds the limit entirely, it takes automatic action. The emergency cost reduction method shows that what automated controls might look like. First, it scales down non-production environments. Development and staging probably do not need to be running at full capacity if you're in a cross crisis. Second, it disables the expensive features using feature flags. Maybe you have a heavy analytics pipeline or ML inference that is non-critical to your core operations. Third, it pages the engineering leadership because this is a significant event that needs human awareness. A few important considerations here. First, be careful about what you're automating. Scaling down development is low risk. Automatically shutting down production services is high risk. You should start conservative. Second, make sure that your automated actions are logged and reversible. You need to understand what happened and be able to undo it. Third, set appropriate thresholds. If your daily limit is too tight, the automation will trigger constantly and become noise. So the key insight is that automation catches problem outside your business hours. A bug deployed on Friday night that causes a runaway cost should not wait until Monday morning for someone to notice. Automated controls will provide a safety net in situations like this. Now let us talk about common cost anti-patterns that a lot of teams make in production. So the first anti-pattern is over provisioning with the justification that you might need it someday. In this example, let's say a team provisions 100 instances, but they actually uses only 20. That is 80% of the waste. The root cause is usually fear. Engineers worry that okay, they will be blamed if the system is not able to handle load, so they over provision. The fix is to implement proper auto scaling and build confidence that the system can scale up when needed. The second anti-pattern is zombie resources. These are resources created for testing, experiments, or temporary projects that were never cleaned up. Looking at these examples, let's say test database John 2023 or experiment ML model V17, these names tell you the story that someone created them, used them, and then forgot about them. The monthly cost might be, let's say, like $5,000 for resources that actually no one has touched in 6 months. And these are common, resources when hackathons happens, people are prototyping or trying to move or start new projects. So this is actually a very common scenario in companies. The solution is a regular cleanup based on your last access time. And this find zombie resources function here scans all resources and flags any that have not been accessed in 30 days and are not explicitly marked as permanent. These should be reviewed and typically, deleted if they are not needed. A good practice is to require an expiration date on all non-production resources. So when you create a test environment, you have to specify when it should be automatically deleted. This prevents zombies from, accumulating. The takeaway is that cost waste often comes from, inattention rather than bad decisions. Build systems and processes that will catch these waste automatically. Now let us continue with two more costly anti-patterns. The third anti-pattern is ignoring reserved instance coverage. In this example, let's say a company spends $100,000 per month on demand, but 80% of that workload is steady state. Without reservations, they pay $100,000. With 80% reserved at a 40% discount, they would actually pay $48,000 for reserved portion plus $20,000 for on-demand portion, totaling only $68,000. That is $32,000 per month they are throwing away by not committing. So why does this happen? Sometimes organizations do not know about reservation programs. Sometimes they are worried about commitment. Sometimes the finance team is not aligned with the engineering. Whatever the reason could be, it is often the easiest cost optimization to implement once you identify it. The fourth anti-pattern is unnecessary cross-region data transfer. In this example, the application runs in US East 1 but has a database replica in US West 2 that it syncs 1 TB of data with monthly. That cross-region transfer will cost you around $20 per terabyte. With constant synchronization, that could be $600 per month just for moving data between regions. The question to ask is, why is that a replica in a different region? If it is needed for disaster recovery, okay, then possibly you may need it. If it is there because someone thought it might be useful someday to be in that region, that is $600 per month of, just on a possibility that might not be true in future. So the key insight is that cost anti-patterns persist because nobody is actually looking at them. You should make cost review a regular practice. You should be looking for over provisioning, zombie resources, missing reservations, and unnecessary data transfer. Now let us summarize the key cost optimization practices we have covered today. For cost visibility, tag all resources with team, service, and environments so you can attribute costs accurately. You should be creating cost dashboards for each team so they can see their own spending. You should be setting up anomaly detection to catch unusual spikes early, and you should also be reviewing costs weekly, not just when the monthly bill arrives. For right sizing, analyze the actual CPU and memory utilization, not what you think you might need. You should be using P95 plus 20% headroom as your sizing target, and you should be implementing auto scaling so resources match demand dynamically. As well as you should also be reviewing instance types quarterly as your usage patterns change. For commitment discounts, reserve your steady state baseline workload, not your peak. You should be using saving plans instead of specific reserved instances when possible for more flexibility. Also, you should be aiming for 60 to 80% of your coverage of your consistent workload. Also, you should be reviewing your commitments annually as your baseline changes. These three areas, visibility, right sizing, and commitments, typically capture the majority of cost optimization opportunity for most organizations. You should start here before moving to more advanced optimization. So please keep this in mind. Now let us continue with the cost summary with spot instances, storage, and architecture. For spot instances, you should be using them for fault-tolerant workloads that can handle interruptions. You should be implementing graceful shutdown as well, handling and checkpointing because they're super important too. Then you should be mixing spot with on-demand for reliability and never going 100% spot on production workloads. The potential savings of 60 to 90% is significant for appropriate workloads. For storage optimization, you should be implementing lifecycle policies that automatically move data to cheaper tiers as it ages. You should be using the appropriate storage tier for each access pattern, and you should also be cleaning up unused volumes and snapshots regularly. And you should also be archiving old data to Glacier rather than deleting it, since storage is cheap enough to keep indefinitely if tiered properly. For architecture optimization, cache aggressively since caching has perhaps the highest ROI of any optimization. You should be using asynchronous processing to reduce the resources needed for each request. You should also be minimizing data transfer by returning only needed fields and using CDNs. And you should be choosing the right compute type for each workload, whether that is general purpose, compute optimized, memory optimized, or GPU instances. Cost optimization is not a one-time project, it's an ongoing practice. The most efficient organizations build cost awareness into their culture, where every engineer thinks about the cost implications of their design decisions. Next, now we'll shift to multi-region and global scale in our next section, where we'll be seeing that some of the cost optimizations we have discussed, like co-locating resources, that have become much more nuanced. Now let us talk about multi-region architecture, which is how you serve users around the globe with low latency and high availability. A multi-region deployment might have your application, let's say, running in US East, US West, EU West, and AP Southeast, and all interconnected and all capable of serving users. So why would you need this complexity? There are four main reasons. The first is low latency worldwide. So users in Tokyo do not want to wait for the request to travel to a server in Virginia. The second is high availability. If an entire region fails, then this does happen sometimes, you need to survive that failure. The third is data sovereignty. Regulations like GDPR require that EU user data be processed only within the EU. And the fourth is disaster recovery. So geographic redundancy protects against regional disasters. Now, here's a key insight that I want you to take away from this section. Multi-region is not just about deploying your application in more places. It is fundamentally changes how you think about data consistency, failover, and operational complexity. A bug that would be annoying in a single region can become a much more serious problem when replicated across 4 regions. A network partition that would be invisible in a single region becomes a major incident when it splits your global database. So now let's look at how to navigate these challenges. Before we dive into solutions, let us understand the problem. Physics matters and you cannot beat the speed of light. Data traveling over fiber optic cable moves at roughly 2/3 the speed of light. From New York to London is about, let's say, around 5,500 kilometers. The absolute minimum round trip is 37 milliseconds. From New York to Tokyo is about 10,800 kilometers, so with a minimum of 72 milliseconds. And from London to Sydney is about 17,000 kilometers with a minimum of 113 milliseconds. And these are just the theoretical minimums. Real latency includes routing, switching, and processing, so the actual latency is 2 to 3 times higher than these numbers. So what does this mean for our users? With a single region in US East, your US users experience 20 milliseconds of latency, which is excellent. but your EU users experience 100 milliseconds and your Asia users will experience 200 milliseconds on every single request. With multi-region deployment, all users experience roughly 20 milliseconds because they're connected to the region closest to them. Here's a rule of thumb that should guide your decisions. Every 100 milliseconds of latency reduces conversions by 1%. A user in Tokyo experiencing 200 milliseconds of extra latency on every request is having a measurably worse experience that translates to measurably lower engagement. The takeaway is that multi-region is not just about disaster recovery, it's also about delivering a consistently good experience to all your users, regardless of where they are, and this is super important for business. There are fundamentally two patterns for multi-region deployment: active-passive and active-active. In active-passive, one region handles all the traffic, it is a primary. The other regions sit idle, replicating data from the primary, ready to take over if the primary fails. Users always connect to the primary regardless of their location. Active-passive is simpler to implement. You do not have to worry about data conflicts because writes only happen in one place. You do not need global load balancing, but it does solve the latency problem. Users far from the primary region still experience high latency. In active-active, both regions handle traffic, so users connected to whichever region is closest. So both regions have databases that synchronize with each other. Active-active solves the latency problem. All users get a nearby region. It also provides better availability since failover is automatic and nearly instant, but is significantly more complex. You have to deal with data synchronization, conflict resolution, and operational complexity. The choice depends on your requirements. If your primary concern is disaster recovery and most of your users are in one geography, active-passive might be sufficient. If you have global user base and latency matters, you need active-active. Now let us look at these patterns in much more detail. Now let us compare these patterns more systematically. In terms of complexity, active-passive is lower complexity while active-active is significantly higher. You are essentially running two parallel systems that need to stay synchronized. In terms of cost, active-passive is lower since your standby region can run at reduced capacity. Active-active requires full capacity in every region. For latency, active-passive provides higher latency for users far from the primary. Active-active provides low latency for all your users. For failover time, active-passive takes minutes because you need to promote the standby and redirect traffic. Active-active takes seconds because traffic just stops going to the failed region. For data consistency, active-passive is simpler since writes happen in one place. Active-active is complex because you need to handle concurrent writes to different regions. There is also a third pattern called follow the sun. In this model, the primary region shifts based on the time of the day. EU West might be primary from 6 a.m. to 6 p.m. UTC, where European users are active, and then US East become primary for 6 p.m. to 6 a.m. UTC when American users are active. Traffic naturally follows the daylight hours. This is a hybrid approach that can work well for certain workloads. The key insight is that there is no universally right answer. You should be choosing the pattern that matches your specific requirements for latency, availability, consistency, and operational capacity. Now let us talk about the hardest part of multi-region, which is keeping data synchronized. There are two fundamental approaches. Synchronous replication means a write is not considered complete until it has been confirmed by the replica. The primary writes the data, waits for the replica to acknowledge it has received, and return the data, and only then returns the success to the client. Synchronous replication provides strong consistency, so you never have a situation where the primary has data but the replica does not. If the primary fails, the replica has everything, but the trade-off here is the latency. Every write has to wait for a round trip to the replica, which could be 100 milliseconds or more for cross-region replication. Asynchronous replication means the primary writes the data and immediately returns the success. The data gets replicated to secondary in the background. Asynchronous replication provides lower write latency because you do not have to wait for the replica, but you get eventual consistency. There is a window called replication lag where the primary has the data that the replica has not received yet. If the primary fails during this window, the data is lost. For financial transactions where data loss is unacceptable, you want synchronous replication and accept the latency cost. For most other applications, asynchronous replication with its faster writes, and acceptable eventual consistency is the better trade-off. The takeaway is to choose your replication strategy based on your tolerance for data loss versus your latency requirements. Now let us talk about conflict resolution, which is a pretty big problem in active-active multi-region deployments. Now consider this scenario. At the exact same moment, a user in US updates their name to Alice through the, let's say, US East region, while a user in EU updates the same record name to Bob through EU West. Both writes, succeed in the local region. And now what? The database replicate to each other and discover they have conflicting updates on the same record. There are several strategies for resolving this. Last write wins uses timestamps to determine which write happened later and keep that one. This is simple but can lose updates. First write wins rejects the later write and forces the client to retry. This preserves the data but requires more complex client handling. Most strategies attempt to combine changes, which works for some data types but is complex to implement correctly. Conflict resolution is where your application defines the domain-specific rules for handling conflicts. The last write wins implementation shown here is simple, so compare timestamps and return whichever record was updated more recently. But understand the implication. One user's update just vanished. If Alice updated her name and Bob updated his name on the same record, one of those updates are pretty much gone. So the key insight is that true concurrent writes to the same record are actually rare in most applications. Users typically work on their own data, but conflicts do occur, and you need a strategy, and you need to understand the consequences of that strategy. Now let us talk about CRDTs, which is conflict-free replicated data types, which are a mathematically elegant solution to some conflict problems. The core idea is to design your data structures so that the conflicts are impossible by definition. Any operation can be applied in any order, and you always get the same result. The gcounter class is a simple example. Instead of storing a single counter value, you store a count per region. When a region increments the counter, it only increments its own count. To get the total value, you sum all region counts. When you merge two counters, you take the maximum for each region. So why does it work? Because each region only ever increments its own count. And there is never a conflict about what a region's count should be, and max is commutative and associative, meaning it does not matter what order you apply to merge operations. CRDTs work well for specific use cases, so gcounters work for things like view counts and like counts. Gsets work for things like tags and members where you can only read and never remove. LWW registers work well for user preferences where last write wins is acceptable. OR maps work for shopping carts where you want to merge items. But CRDTs do not solve all problems. If your business logic requires true serializable transactions, CRDTs will not help. They are a tool for specific data patterns, not a universal solution. The key takeaway is that to consider CRDTs when your data structure fits, they can eliminate entire categories of conflict problems. To this the right region, there is the job of global load balancing. DNS-based routing is the most common approach. When a user looks up your domain, the DNS server examines their location either from the IP address or from the location of the DNS resolver and returns the IP address to the nearest region. A US user gets useast.example.com. As an EU user, you'll get euwest.example.com. And an Asia user will get apsoutheast.example.com. And there are several routing policies you can use. Geolocation routing sends users to region designated for their geographic location. This is good when you need predictable routing for compliance or regulatory reasons. Latency-based routing sends users to whichever region actually has the lowest latency to them. This adapts to network conditions automatically, so weighted routing distributes traffic by percentage, which is useful for gradual migrations or canary deployments. Failover routing defines the primary and secondary, sending traffic to secondary only when the primary fails at checks. For most applications, latency-based routing is the best choice. It automatically adapts to changing network conditions and does not require you to maintain geographic mapping tables. The key insight is that global load balancing is the entry point. You should get this right and users automatically get sent to the best region for them. If you get this wrong, and all your multi-region investment will be wasted. Now let us look at some more advanced global load balancing concepts. Anycast routing is a technique where the same IP address is announced from multiple locations around the world. When a user connects to that IP, the network automatically routes to them to the nearest announcement. A user in London connects to the London point of presence. A user in Tokyo connects to the Tokyo point of presence. Same IP address, different physical destinations. Anycast is used by CDNs and DNS providers to achieve extremely low latency global distribution. It is elegant because users do not need to resolve different DNS names for different regions. There is one IP and the network figures out the best path. This Route 53 configuration here shows DNS-based routing with health checks. We are creating an A record for api.example.com that points to a specific IP in US East 1. The set identifier and region parameters tell Route 53 that this is a latency-based routing record for US East 1. And the health check ID parameter means Route 53 will only return this record if the health check is passing. The health-based routing code shows the application level equivalent. So we check the health of each region and only include the healthy regions in our available endpoints. We can also weight regions based on the current capacity. So the key takeaway is that global load balancing should be health aware. Never send users to a region that is unhealthy. Combine geographic or latency-based routing with continuous health checks. Now let us talk about what happens when an entire region fails. The failover process follows a predictable sequence. First, health checks start failing. Your global load balancer is continuously checking each region, and when a region becomes unhealthy, those checks fail. Second, you need to confirm the failure is real and not transient. A brief network blip should not trigger failover. Third, you update the DNS or load balancer configuration to stop sending traffic to the failed region. Fourth, traffic shifts to the surviving regions. And the fifth is that you monitor the situation and begin recovery. The timeline for all this is too important to understand. Detection typically takes 30 to 60 seconds because health checks run on intervals and you usually want multiple failures before acting. Decision takes another around 1 to 5 minutes because you want to confirm the failure is real. DNS propagation takes 1 to 5 minutes because DNS records are cached globally. Traffic shift takes 5 to 15 minutes because clients hold DNS responses for their TTL version. Full failover, where all the traffic has migrated, takes around 10 to 30 minutes. This timeline is why active-passive failover take minutes while active-active takes seconds. In active-active, traffic is already going to multiple regions. When one fails, client immediately retry and against another region. There is no DNS propagation delay. The key insight is that your failover time is dominated by DNS TTL and client retry behavior, not by how fast you can detect the failure. Now let us look at how to implement automated failover. The regional failover class runs continuously, checking the health of each region. If a region's success rate drops below the threshold, which is 50% in this example, it triggers the confirm failure method. So why do we need to confirm the failure? Because we want to avoid false positives. Network partitions can make a region look failed from some vantage point but not others. So we check from multiple locations, US East, EU West, and AP South. If 2 of the 3 locations agree the region is unhealthy, we proceed with the failover. The execute failover method does 3 things. First, it updates the DNS to remove the failed regions so new connections stop going there. Second, it scales up the surviving regions because they now need to handle more traffic, some headroom. Third, it alerts the on-call engineer because automated failover is great, but humans need to know what happened and manage the recovery. A few considerations for automated failover. First, set your thresholds carefully. Too sensitive and you will have false positive. Too conservative and you will be slow to respond to real failures. Second, make sure your surviving regions can handle the load. If you are running at 70% capacity in each region and one fails, the others need to handle 100% plus some more margin. Third, test your failover regularly. The one way to trust automation is to exercise it. The takeaway is that automated failover is essential for multi-region high availability, but must be carefully implemented to avoid false positive and ensure capacity. Now let us talk about data sovereignty, which is about keeping data where regulations require it to be. Different jurisdictions have different requirements. GDPR requires that EU user data must be processable within the EU, and then other countries do the same. HIPAA imposes specific requirements on healthcare data handling in the US. The architecture to support data sovereignty typically involves regional databases with no cross-region replication of user data. EU users connect to the EU region, the data lives in the EU database and it never leaves. US users connect to the US region with data in the US database. Global services that need to operate across region only has access to metadata, not person data. The implementation shown here routes the users to appropriate database based on their country. The get database for user function here checks the user's country and returns the corresponding regional database. The store user data function then writes to that specific database. This is straightforward in concept, but it has significant implications. So you cannot simply query all users anymore because user data is distributed across multiple databases in multiple jurisdictions. Analytics and reporting becomes much more complex. Cross-region features need careful design to avoid accidentally moving personal data. So the key insight is that data sovereignty requirements should be baked into your architecture from the start. Retrofitting them later will be extremely difficult. Now let's look at the nuances of handling cross-border requests. The Sovereign Data Manager class shows how to handle the complexity. When getting a user profile, we first determine which region the user's data lives in. If the requesting service is in the same region, we return the full profile with all the data. But if the request is coming from a different region, we return only the public profile with non-PII data. The pattern respects the data sovereignty while also still allowing the global operations. A user in the EU can have their profile viewed by someone in the US, but the US-based service only sees the public non-person information. The person data never leaves the EU. The process request method shows another pattern. So some operations must be processed in the user's region because the data is the personal data. For those, we make a remote call to the correct region and let that region handle their operation. Other operations can be processed locally because they do not involve personal data. This adds latency for cross-region operations because it involves the personal data. So a US-based admin viewing an EU user's full profile incurs a cross-Atlantic round trip. This is unavoidable because if you want to comply with the data sovereignty requirements. So the key takeaway from this entire multi-region section is that global scale brings fundamental trade-offs. You are trading simplicity for latency, consistency for availability, and operational complexity for resilience. Understanding these trade-offs is how you make the right decisions for your specific business requirements. Region architecture. You have regions in US East, EU West, and maybe Asia Pacific. Everything looks great on paper, but here's the uncomfortable truth. If you have not tested your multi-region setup rigorously, you do not actually have multi-region resilience. You actually just have multi-region cost. So now let us talk about what you should be testing in a multi-region system. The first test type should be latency test. These validate that users are actually getting routed to the nearest region. If a user in London is hitting your US East servers instead of EU West servers, something is wrong with the DNS or the load balancer configuration, and your users are experiencing unnecessary latency. The second test type should be the failover drills. These validate that traffic actually shifts correctly when the region fails. This is the whole point of having multiple regions, so you need to prove it works before you need it and in an actual real incident. The third test type should be replication tests. These validate that your data is syncing correctly across multiple regions. So if you are running active-active, you need confidence that writes in one region are showing up in the other regions within your expected replication lag. The fourth test type should be conflict test. These validate that concurrent writes are being handled properly. So remember, in active-active configuration, two users in different regions could update the same record at the same moment. Your conflict resolution strategy needs to be tested, not just designed. And the fifth test type should be sovereignty tests. So these validate that the data is staying in the correct region based on regulatory environments. If you promise your European customers that their data stays in EU West, you need to prove that it's actually done. Now let me walk you through how to approach chaos engineering for multi-region systems. The idea is to deliberately simulate region failures in a controlled way and measure the impact. In this region failure test function here, we start by collecting baseline metrics for 10 minutes. This gives us a reference point for how the system normally behaves. Then we simulate the region failure by blocking all traffic to US East. This mimics what would happen if the entire region went down. If we collect the metrics during the failure for 30 minutes to see how the system responds, then we restore the traffic and validate the results. The assertions here are pretty important. So we are saying that during a full region failure, error rate should stay below 1%. We are saying that P99 latency should be no more than double the baseline, which is reasonable because the traffic is now going to more distant regions. And we are saying that throughput should be stay above 90% of the normal. If any of these fail, your multi-region setup is not actually providing the resilience you designed it for. So the key takeaway here is that multi-region is not a checkbox you mark as a done. It's a capability you have to continuously prove through testing. The chaos engineering approach lets you find problems in controlled conditions rather than discovering them during an actual regional outage at 3 a.m. Now let us talk about the game day exercises which take chaos engineering a step further by involving the whole team in a structured simulation. A game day is essentially a scheduled drill where you deliberately break something in production or a production-like environment and practice as your response as a team. The goal is to find gaps in your automation, runbooks, and team coordination before a real incident forces you to find them at 3 a.m. Here's how a well-structured game day should work for a multi-region scenario. The first phase is preparation, which happens the day before. You should notify all stakeholders so nobody panics when things start falling. You should ensure that you have a proper on-call coverage during the exercise, and critically, you should verify your rollback capability works before you start breaking things. The second phase is execution. At 9 a.m., you start monitoring baseline metrics so you have a reference point. At 9:30, you announce the test start to the team. At 9:35, you can simulate the US East failure. At 9:40, you observe whether the automatic failover kicks in as expected. At 9:50, you verify that the EU West is actually handling the traffic. At 10 a.m., you check data consistency to make sure that no data was lost or corrupted during the failover. And at 10:15 a.m., you restore the US East. At 10:30 a.m., you verify that traffic rebalances correctly. And at 10:45, you end the test. Then the third phase is the postmortem. You should be asking questions like, okay, what worked well? What failed or did not work as expected? What manual steps did we take that could be automated? And then you update your runbooks based on what you learned. The key insight here is that game days are not just about testing the technology, they're about testing the people and processes too. You want to discover that someone does not know how to access the failover controls during a drill, not during a real outage. Now let us talk about something that often gets overlooked in multi-region discussions, which is cost. Multi-region is not cheap, and going in without understanding the cost implications can lead to some painful surprises. Let me walk you through the cost multipliers you should expect. For compute, you're looking at 2 to 3x at your single region cost. You need instances running in multiple regions, and each region needs enough capacity to handle failover traffic. For database, again, it will be 2 to 3x. You need replicas in each region, and those replicas need compute and storage. For storage, you should expect 2 to 3x cost as well. Your data is being replicated across regions, so you are paying for that storage multiple times. And the data transfer is where it gets interesting. In a single region, most of your traffic stays within the region and is relatively cheap. In multi-region, you have constant cross-region replication traffic, and cloud providers charge significantly more for the data that crosses regional boundaries. For operations, you should expect 1.5 to 2x times. Multi-region systems are more complex to operate, which means more engineering time spent on maintenance, monitoring, and incident response. Now, the good news is that there are ways to optimize these costs. One effective strategy is to scale each region based on local traffic patterns rather than keeping all regions at peak capacity at all time. In this code example here, we define different peak hours and replica counts for each region. US East has peak hours from 9 a.m. to 9 p.m. EST, with 10 replicas during peak and 3 during off-peak. EU West peaks from 8 a.m. to 8 p.m. Central European Time with 8 peak replicas and 2 off-peak. Asia Pacific peaks from 9 a.m. to 9 p.m. Singapore time with 5 peak replicas and 2 off-peak. By scaling replicas based on regional traffic patterns, you can significantly reduce compute costs while still maintaining enough capacity for failover scenarios. So the key takeaway is this: multi-region is expensive, often 2 to 3 times your single region cost. You should go into it with eyes open and implement regional scaling to optimize cost without sacrificing resilience. Now let us cover what we have learned about the multi-region architecture. For architecture decisions, you should use active-passive when your primary goal is disaster recovery. You should use active-active when you need low latency for global users. And consider data sovereignty requirements early in your design process because retrofitting them later is painful and expensive. For data replication, you should use synchronous replication when you need strong consistency, but understand that it comes with higher latency costs. You should use asynchronous replication when you can tolerate eventual consistency and need better performance. And always plan your conflict resolution strategy upfront because two users in different regions will eventually update the same record at the same time. For operations, automate your failover process but include safeguards to prevent accidental triggers. You should test your failover regularly, at least monthly, through game day exercises, and monitor cross-region replication lag continuously because that lag represents your data loss window if a region fails. For cost, remember that multi-region is typically 2 to 3x more expensive than a single region. You should be optimizing costs through region scaling based on local traffic patterns and minimize cross-region data transfer wherever possible because those egress charges add up pretty quickly. The key insight is that multi-region architecture is a significant investment in complexity and cost, but it's the only way to achieve truly global scale with resilience. You should make sure that your business requirements actually justify that investment before committing to it. Okay, now let's move to a new section which is about incident management. This is about what happens when things go wrong and things will eventually do go wrong. The incident lifecycle has 5 phases. First is detection, where you discover something is broken. Second is response, where you acknowledge the problem and start working on it. Third is mitigation, where you stop the immediate bleeding. Fourth is resolution, where you actually fix the underlying problem. And fifth is a postmortem, where you learn from what happened. Now, I want to challenge some more common myths about incidents. The first myth is that we will prevent, let's say, all incidents. So, the reality is that incidents are inevitable. In any sufficiently complex systems running at scale, things will eventually break. The question is not whether you have incidents, but how you will handle them when they do occur. The second myth is that more process equals fewer incidents. The reality is that the speed of response matters more than the process. A team can detect, respond, and mitigate in 10 minutes will have less impact than a team that takes an hour following a detailed process document. The third myth is blaming the person who caused it. The reality is that systems fail, not people. When an incident happens, it is almost always a combination of system design, tooling gaps, process issues that allow the human error to have impact. Blaming individuals does not make systems more reliable and is not the right thing to do anyways. So the key insight is this. The goal is not zero incidents. That is an impossible standard. The goal is fast detection, fast mitigation, and learning from every incident so you can improve your systems over time. Now let us talk about finding problems before your users actually do. Because the worst way to learn about an incident is from a customer complaint, or even worse, multiple people complaining on social media. There are multiple sources for detecting incidents, and each has a different characteristic. Synthetic monitoring has a faster detection time, often within seconds. This is where you have automated health checks constantly hitting your endpoints. When those health checks start failing, you know immediately that something is wrong. The downside is that synthetic monitoring only catches problems that affect the specific endpoints you are checking. Real user monitoring, as they mentioned as RUM, detects problems in seconds to minutes based on the actual user traffic. This catches issues that synthetic monitoring might miss because it is based on real user behavior. The downside is that you need traffic for it to work, so it may not catch issues during low traffic periods. Log analysis typically detects problems in minutes. This is where you are looking for exceptional patterns or error spikes in your logs. The upside is that logs capture a lot of detail. The downside is that is delay in aggregation and analysis. Customer reports are the slowest, typically minutes to hours. So if customers are reporting issues through support tickets, that means all your automated detection has missed the problem. They should be rare if your monitoring is good and operational. So now let me explain how alert severity should map to your response. Sev1 is ideally for customer service outages or data loss risk. The criteria is that the core service is down for all or most users. Response time should be immediate. Notification page, you should have the page, and then the notification should go to the on-call engineer and notify the management if needed. An example would be, for example, the API returning 500 HTTP 500 errors for all requests. Sev2 is for major features broken with significant user impact. Response time should be 15 minutes. Notification should page the on-call engineer as well. And an example would be the checkout flow, let's say failing for 20% of the users. Sev3 is ideally for minor features broken with limited impact. Response time can be 4 hours, and notification can be Slack alert rather than a page to the on-call engineer. An example would be something like delayed email notifications to users. Again, these severity levels depend on your teams and specific business scenarios, so it differs from team to team, but these are like the standard guidelines. The key here is that having clear definitions that everyone agrees on in your team so that there is no debate during an incident about whether something is Sev 1 or Sev 2. But in the real world, ideally, teams can definitely collaborate, and sometimes, a lot of times, depending on the incidents, they do get upgraded to higher severity, or sometimes when humans, engineers, they analyze that, okay, this incident is not as severe as being stated, sometimes they get downgraded too. So again, it depends teams to teams, companies to companies. So the first few minutes of an incident are very important. What do you do in those initial moments often determines how long the incident lasts and how much impact it has. Some teams call this the golden hour, but really it's the first 5 minutes that matter most. Let me walk you through what should happen in those first 5 minutes. The first step is acknowledge. The on-call engineer should acknowledge that the alert so that the team, knows someone is looking at it. They should also join the incident channel immediately. And then they should declare the incident severity based on what they know so far. A lot of times the incident severity will be directed towards you, if it's like automated monitoring system, but the human engineer should still, make a judgment on it. Even if you're not sure, sometimes, you can do is like you can have a group teams call with your wider team to understand the severity and impact, because you can always upgrade or downgrade later. The second step is SS. You should be asking 3 questions. Okay, what is broken? This sounds pretty obvious, but you need to quickly narrow down the scope. Who is affected? Is it all users, some users, one region? And third is what had changed recently. So was it a deploy, a config change, or a traffic spike? The third step is communicate. You should be updating the status page so customers know that you are aware. You should notify the internal stakeholders so that they are not surprised by customer complaints. And you should set expectations about when you will have more information. Now let me talk about the incident commander role. In any significant incident, you need someone whose job is coordination, not debugging. This is the incident commander. The incident commander has 5 key responsibilities. First is coordinating the response by assigning tasks and tracking progress. Second is communication by updating stakeholders at regular intervals. Third is decision making by approving risky mitigations when needed. Fourth is documentation by ensuring the timeline of events is being captured. And fifth is escalation by bringing in additional help when needed. The reason you need that role is that when engineers are deep in debugging, they lose track of time sometimes and they forget to communicate, or they may not notice when they need help. The incident commander keeps the big picture in focus. So let me show you what a well-run incident channel ideally looks like. This kind of a structure that keeps everyone aligned during a high stress situation. So the incident channel should have a clear naming convention. In this example here, let's say it is incident 2025 115 API outage. The date and a brief description makes it easy to find later. The first thing that should happen is a pinned message at the top with the key information. The pinned message should include the incident description, which is the API returning HTTP 500 errors. It should include the severity, which is Sev 1. It should include what the incident commander is, which is Alice, let's say in this example. It should include the current status, which is investigating. It should also include the start time. It should include the user impact, which is all users unable to check out, for example. And it should also confirm whether the status page has been updated or not. Also, it should have the last update with the timestamp. The pinned message should be updated regularly so anyone joining the channel can immediately understand the current state without scrolling through messages. Below the pinned message should be a timeline that captures everything that happens. Let's say at 1432, the alert fired showing API error rate above 5%. At 1434, let's say a person named Bob acknowledged and started investigating. At 1438, Alice joined as an incident commander. At 1442, let's say the team identified the deploy at 1430 as a potential cause. At 1445, let's say they initiated a rollback. The timeline is invaluable during the incident for keeping everyone aligned, and after the incident for the post-mortem. You should be capturing everything, even things that seem obvious in the moment. The key insight is that good incident response is about communication as much as technical skills. A well organized incident channel dramatically reduces confusion and speeds up resolution. Now, let us talk about mitigation, which is about stopping the bleeding. The goal of mitigation is to restore service as quickly as possible, even if that means a temporary or down degraded solution. Different problems call for different first actions, so let me walk through the most common scenarios. If the problem is a bad deploy, the first action should be to roll back. The rationale is that you're restoring a known good state, so do not waste time debugging if a rollback will restore the service. If the problem is resource exhaustion, like CPU or memory maxing out, the first action should be to be able to scale up. You should be adding more instances to buy yourself time to investigate the underlying cause. If the problem is a dependency failure, the first action should be to enable your fallback. You should degrade gracefully rather than failing completely. If the problem is a traffic spike, the first action should be to enable rate limiting. Protect your system by shedding load deliberately rather than collapsing under it. If the problem is data corruption, the first action should be to stop writes. Prevent further damage while you assess the situation. Now let me show you a more detailed decision framework for the rollback scenario specifically, since bad deploys are one of the most common incident causes. Over here, the should rollback function captures the three conditions that all be true before you roll back. First, was there a recent deploy within the last hour? Second, is there a clear correlation between the deploy time and when the issues started to happen? Third, is the rollback safe, meaning there are no database migrations that would break if you roll back the code? If all three conditions are true, roll back immediately. Do not spend an hour debugging when a 2-minute rollback will restore the service. The key insight here is that mitigation is not about finding the root cause. That comes later. Mitigation is about restoring service as fast as possible. Now, I want to make sure that the distinction between mitigation and resolution is crystal clear because confusing these two causes a lot of unnecessary downtime. Mitigation is what you do first. The goal is to stop the immediate bleeding and restore the service, even if the restoration is degraded or temporary. An example is rolling back a bad deploy. After the rollback, users can use your service again, but you have not actually fixed the bug that was in deploy. Resolution is what you do after the service is stable. The goal is to fix the root cause and prevent the issue from happening again. An example is fixing the bug, adding tests to catch it, and redeploying. This takes longer, but that is fine because your service is already backing up. Too often I have seen teams waste time trying to debug and fix the root cause while their service is down. You should be mitigating first, get the service back up, and then take your time to properly fix and prevent. Now let me show you some degraded operation modes that can be useful during incidents. The first is the read-only mode. This enable read-only method disables write operations to protect your data integrity. Then it extends the cache TTL by a factor of 10 to reduce database load. This is useful when you suspect data corruption or database issues. Users can still read data, they just cannot make changes. The second is essential only mode. So this enable essential only method here disables the non-essential features like recommendations, analytics, and notifications. This reduces the system load and lets you focus resources on the core user journey. Users lose some features, but the critical path still works. The third is the static fallback mode. This enable static fallback method here serves the static content when dynamic generation is failing. Users will see cached or pre-generated content instead of errors. The key takeaway is that partial functionality is almost always better than complete failure. You should design your system with these degraded modes in mind so you can enable them quickly during incidents. About keeping everyone informed during an incident. Poor communication during an incident often causes more damage to customer trust than the incident itself. Let me walk you through what good status page updates should look like at each phase. In the investigating phase, your update should acknowledge the problem and set expectations. Something like, okay, we are investigating reports of checkout failures. Some users may experience errors when completing purchases. So notice that this specific about what is broken, and this message also does not make any promises when it will be fixed. In the identified phase, your update should explain what you found and that you are working on it. Something like, let's say, we have identified the issue as a problem with our payment processing service. We are working on a fix. Now users know what the problem is and that you have a path forward, and then you're actually working on it. In the monitoring phase, your update should indicate that the fix is deployed, but you're watching for any remaining issues. Something like, let's say, if you can say the message, like a fix has been deployed, we're monitoring the situation, checkout page should now be working normally. So when you use the language like that, it is very important because you do not want to declare victory prematurely. In the resolve phase, your update should confirm that the incident is indeed over and apologize for the impact. This message should be something like, okay, this incident has been resolved, checkout is fully operational, and we apologize for the inconvenience. Now let me talk about the communication cadence. So the frequency of updates should match the severity of the incident. For 7 incidents, you should update every 15 minutes. Even if you do not have new information, you should update saying that the investigation is ongoing. Silence during a major incident makes customer think that you are not working on it, and that's not good. For SEF2 incidents, you should be updating every 30 minutes, and for SEF3 incidents, you should ideally be updating every 2 hours. The key insight is that regular communication, even when there is no information, will build trust. Customers can tolerate downtime much better than they can tolerate uncertainty. Now, different audiences need different information during an incident. Let me walk you through who needs what. The incident team working on the problem needs technical details and specific actions through the Slack incident channel. They need to know what has been tried, what failed, and what is being adapted next. The broader engineering organization needs a summary and key decisions through the incident channel. They do not need every debugging step, but they should understand what is happening at a high level in case they can help. Leadership needs their business impact and timeline estimates through email or Slack direct messages. They need to know how many customers are affected, what the revenue impact is, and when the service is expected to be restored. Customers need user-facing impact and expected resolution time through the status page. They do not need technical details about which microservice failed. They need to know what they can do and cannot do, and when they can expect it to work again. Support teams need customer-facing responses through internal documentation. They need scripts for how to respond to customer inquiries and what to say about the issue. Now, let me show you what a good customer communication should look like after an incident has been resolved. The email should have a clear subject line indicating that the incident is resolved. The body should cover 4 things. First, what happened. So between these times, on this date, some users experienced this issue and problem. Second, it should cover the impact. So for example, approximately this many checkout attempts failed during this period, and you should be specific with the numbers. Third is the root cause. You should be explaining what caused the issue in terms of customers can understand. For example, you can say a configuration change caused payments processing to fail for certain payment methods. Fourth, the resolution. Explain what you did to fix it and what you're going to do to prevent it from happening again. The key insight is that transparent post-incident communication actually builds customers' trust. Customers understand that systems fail. What they want to know is that you take it seriously and are working to prevent recurrence. What happens after the incident is resolved, which is the postmortem. The goal of a postmortem is to learn from what happened and improve your systems. Let me be clear about what a postmortem is for and what is not for. So the goal is to understand what happened, not to find someone to blame. When you blame individuals, people hide information and the organization learns nothing, and it's just not a right thing to do anyways. The goal is to identify systematic issues, not to document individual failures. If an engineer made a mistake, the question should be, okay, why did our systems allow that mistake to have impact? The goal is to prevent it from happening again, so not to create more process. The solution is to most instances is not about more approval steps or more checklists, is better automation and better safeguards. The goal is to share learnings, not to hide mistakes. Postmortem should be shared widely so the whole organization can learn. Let me walk through what a good postmortem document should contain. It should start with a summary, a few sentences describing what happened. In this example, let's say API returned HTTP 500 errors for 73 minutes due to a misconfigured rate limiter deployed at 14:30 UTC. Then it should have an impact section with specific numbers. So duration was 73 minutes, users affected was approximately 15,000, failed requests were approximately 45,000, and the revenue impact was approximately $12,000. These numbers matter for prioritizing the improvements. Then there should be a detailed timeline of events, then a root cause section with a technical explanation of what went wrong, and then a contributing factor section identifying the systematic issues that allow this to happen. And finally, action items with specific assigned tasks to prevent recurrence. The key insight is that blameless does not mean accountability free, it means focusing on systems rather than individuals. The question is never who screwed up, the question is how did our systems allow this to happen? One of the most effective techniques for root cause analysis is the 5 whys. The idea is simple. We keep asking why until you get a systematic root cause that you can actually fix. Let me walk you through an example. The incident is that the API returned HTTP 500 errors. So why number 1 is, why did the API return HTTP 500 errors? Because the rate limiter rejected all requests. Why number 2 is, why did the rate limiter reject all requests? Because the rate limit was set to 0 requests per second. Why number 3 is, why was the rate limit set to 0? Because the config file had the wrong value after deploy. Why number 4 is, why did the wrong config get deployed? Because the config change was not reviewed. Why number 5, why was the config change not reviewed? Because config changes bypass the code review process. So the root cause is that config changes lack the same review process as code changes. The action item is to require review for all config changes going forward. So notice what has happened here. We started with the symptom, API returning errors, and drilled down to a systematic issue, which is config changes are not being reviewed. If we had stopped at why number 3, we might have just fixed this one config value, but by going deeper, we identified that there is a gap that would have caused other incidents in the future. The 5 whys technique works because it forces you past the surface level explanation to underlying systematic issues. It is simple but incredibly effective and super important. The whole point of doing postmortems is to generate action items that prevent recurrence, but not all action items are created equal. Let me show you what makes a good action item versus a bad one. Good action items have 4 characteristics. First, they are specific. Add rate limiter config validation is specific. You know exactly what needs to be built. Second, they are measurable. Reduce detection time from 5 minutes to 30 seconds gives you a clear target to hit. Third, they are assigned. Like owner, for example Alice, makes it clear who is responsible for making this happen. And fourth, they are time bounded. So for example, due by 2025 1 2, so like 22nd January 2025, creates accountability and ensures that the work actually gets done. Now let me show you some bad action items as well. So like for example, be more careful is not an actionable. Add more monitoring statement does not specify what monitoring or where. And improve testing statement does not also say what test to add. Review processes statement like that is also vague and will likely result in meetings that just produce nothing. Action items should fall into 3 categories. Detection items helps you find problems faster. Examples include, like for example, adding an alert for rate limiter, config changes, or adding synthetic checkout monitoring. Mitigation items help you reduce the impact when problems do occur. So examples include things like implementing config rollback automation or adding a circuit breaker to the rate limiter. Prevention items help you stop the problem from happening in the first place. Examples include requiring review for config changes or adding config validation in the CI pipeline. A good postmortem should have action items in all these 3 categories. Detection ensures that you find the problem faster if it happens again. Mitigation reduces the impact, and prevention stops it from happening at all. Let me talk about tracking action items, because the secret of postmortems is that a lot of action items never get done. Teams write up beautiful postmortems, they assign action items, and then they move on to the next urgent thing. The improvements never happen due to this reason. The example we show over here, like for example, this action item tracker class shows how to implement proper tracking. The add item method stores each action item with the incident ID it came from, a description, an owner, a due date, status, and priority. This gives you visibility into all outstanding action items across all incidents. The weekly report method is the key to accountability. It finds all overdue items, action items where the due date has passed but status is still open, If there are overdue items, it alerts the engineering leadership. This creates organizational pressure to actually complete the work. The report returns three key metrics. Total open items tells you how much work is outstanding. Overdue count tells you how much work is flipping. And complete this week tells you the rate of progress. In my experience, teams that review action item progress weekly close about 90% of the items on time. Teams that do not track items close maybe 30%. So the tracking is what makes all the difference. The key insight is that a postmortem without completed action items is just documentation. The real value comes from actually making the improvements. Build a system that ensures that action items do get done. Now let us talk about on-call, which is a critical but often painful part of operating production systems. Done poorly, on-call burns out engineers and leads to turnover. But if it's done well, it can be sustainable and even educational. There are four principles for healthy on-call. The first principle is compensate fairly. On-call is actual work and it should be compensated with extra pay, and if that's not allowed, then you should definitely give your engineers time off or both. Engineers who are giving up their evenings and weekends to keep systems running deserve to be compensated for that. The second principle is limit burden. No one should be on call more than 1 week per month. Beyond that, the stress and sleep disruption becomes unsustainable. The third principle is to reduce toil. If engineers are getting paid for the same issue repeatedly, you should automate the fix. Repeated manual work during on-call is a sign that your systems need improvement. The fourth principle is support on-call. Engineers on-call should have clear escalations path, so if they do get stuck, they should know exactly who to call for help. Now let me show you what a good on-call handoff should look like. This happens at the start of each rotation, so the handoff document should identify who is outgoing and who's incoming. It should list any active issues that are still being worked. It should summarize the recent incidents so the incoming engineer knows what has been happening. It should highlight the things to watch like upcoming deploys or expected traffic spikes. It should note any runbook updates that has happened during the previous rotation, and it should include any questions or concerns for the incoming engineer. The handoff ensures that the continuity between rotations. The incoming engineer is not starting from zero. They do have context about what has been happening and what to watch out for. Now let me show you how to measure and improve on-call health over time. This on-call health metrics class over here captures the key metrics. The weekly report method here calculates several important numbers. Pages received is the number of total alerts that has been paged an engineer. Pages per day, normalize this to a daily rate. Night pages counted pages between 10 p.m. and 6 p.m. because these are the most disruptive to sleep. False positives count alerts that did not require any action, and mean time to acknowledge measures how quickly engineers respond to pages. Mean time to resolve measures how long incidents take to fix, and toil hours estimate the time spent on repetitive manual tasks. The suggest improvements method turns these metrics into actionable recommendations. If night pages exceed 5 per week, it suggests reviewing alerting thresholds to reduce noise. If the false positive rate exceeds 30%, it suggests tuning alerts. If toil hours exceed 10 per week, it suggests automating repetitive tasks. Now let me give you target numbers to aim for. Pages per week should be under 10. More than that, and your engineers are constantly being interrupted. Night pages should be under 2 per week. And sleep disruption is the faster way to burn out, so you should avoid that. False positive rate should be under 10%, and if it's more than 10% of pages do not require action, your alerts need tuning. Mean time to acknowledge should be under 5 minutes, and because this measures responsiveness. Mean time to resolve for SEF2 incidents should be 1 hour. The key insight is that on-call health is measurable and improvable. If your team is struggling, measure these metrics, identify the biggest problems, and systematically address them. Now let us wrap up what we have learned about incident management. For detection, you should have multiple detection sources, including synthetic monitoring, real-use monitoring, and logs. You should have clear severity definitions so there is no debate during an incident. And you should have alert on symptoms, not causes. So alert when the users are experiencing problems, not when CPU is high. For response, acknowledge fast and communicate faster. Users can tolerate downtime better than uncertainty. Use an incident commander to coordinate the response. And always mitigate first, investigate second. Restore the service before you worry about the root cause. For postmortems, cultivate a blameless culture. Focus on systems, not individuals. Use the 5 whys technique to get to the root causes. Create specific assigned action items and track completion to ensure improvements actually happen. For on-call, implement the sustainable practices so your team does not burn out. Do clear handouts between the rotations and reduce the toil continuously by automating anything that pages engineers do repeatedly. The key insight across all of these incident management is that the incidents are learning opportunities. Every incident makes your system a little more resilient if you do the work to understand what happened and prevent the recurrence. Okay, so we have covered a lot of concepts throughout this course. Now let us apply everything we have learned to real world systems. We're going to analyze 3 case studies in depth. For each system, we'll examine 4 things. First, the requirements and constraints that shape the design. Second, the architecture decisions and why they were made. Third, the production challenges that emerge at scale. And fourth, how the principles we have learned throughout this course apply. The 3 systems we'll analyze are: first, an Instagram like social media feed. This is a great case study for understanding data at scale, aggressive caching, and the fan out problem. Second, a payment processing system. This is a great case study for understanding strong consistency, reliability, and idempotency. Third, a real-time chat system. This is a great case study for understanding WebSockets, presence systems, and message ordering. These 3 systems cover different trade-offs and different challenges. By the end, you should have much better sense of how to apply production principles to any system you design. So now let us start with the social media feed like Instagram or Twitter. This is one of the most challenging systems to build at scale. Let me give you a sense of scale we are talking about here. 500 million daily active users, 100 million new posts created every day, 10 billion feed reads every day, and the average user follows, let's say, 500 accounts. Now let me walk you through the requirements. Feed load time should be under 500 milliseconds for the 99th percentile. Users expect their feed to load instantly. Any delay and they will close the app. Post visibility should be under 5 seconds after posting. When a user posts something, their followers should see it almost immediately. Availability target is 99.99%. The feed is the core product. If it is down, the entire app is effectively down. Consistency can be eventual, so this is important. Users can tolerate seeing a slightly stale feed. They cannot tolerate slow or fade loads. These requirements shape every design decision, so the combination of massive scale, low latency requirements, and eventual consistency being acceptable tells us that caching will be super important here. Now let me walk you through the high-level architecture for the system. A request comes from client to an API gateway, then to the feed service. The feed service reads from a feed cache that contains pre-computed feeds. It also talks to the post service for the post details and the follow graph for relationship data. The post service stores posts in a post data store. The follow graph uses a graph database for relationships. Let me explain the key components and why each one was chosen. The feed cache uses Redis cluster because we need sub-millisecond reads and we need to store pre-computed feeds for hundreds of millions of users. The post data store uses Cassandra because we need to handle 100 million writes per day with high availability. Cassandra's write optimized architecture is ideal for this. The graph database uses Tau or a similar custom solution because we need to traverse relationships efficiently. For example, who does this user follow and who follows this user? The message queue uses Kafka because we need to handle the async fan out of posts to followers. Kafka's durability and high throughput make it ideal. The architecture is designed around 2 key insights. First, reads vastly outnumber the writes, so we optimize for reads with aggressive caching. Second, generating a feed on every request is too expensive, so we pre-compute feeds and cache them. Now let us talk about the fan-out problem, which is the central challenge of building a social feed at scale. When a user creates a post, how do you get that post into feeds of all their followers? There are 2 basic approaches, push and pull. With the push approach, also called fan-out on write, when a user creates a post, you immediately write that post to the feed cache of every follower. In this create post function, we first store the post, then get all followers of the posting user, then push the post ID to each follower's feed cache. This approach has huge advantage. Reading a feed is instant because it is already computed and cached, but it has a massive problem: celebrities. Imagine a user with 100 million followers posts something. You need to do 100 million cache writes. You need 100,000 writes per second. That takes 1,000 seconds. That is over 16 minutes before all the followers can see the post. That is unacceptable. So the push fan out works great for normal users but breaks completely for celebrities. The alternative is pull approach, also called fan out on read. With this approach, when a user requests their feed, you compute it on the fly. In this get feed function, we first get who the user follows. Then for each followed account, we get their recent post. Then we sort all the posts and return the top 50. This approach has big advantage for celebrities. When a celebrity posts, there is no fan out work at all. The post just gets stored. But it has a massive problem for users who follow many accounts. If a user follows 1,000 accounts, you need to fetch posts from 1,000 different sources, sort them, and return them. Even with batching, that is pretty slow. So pull fan out handles celebrities well, but that is too slow for normal feed reads. The solution is a hybrid approach that combines the both strategies. For regular users with less than 10,000 followers, you should be using the push approach. When they post, fan out to all followers caches. For celebrities with more than 10,000 followers, you should be using pull approach. Do not fan out their post, instead pull celebrity posts at the read time. When loading a feed, combine the cache push post with freshly pulled celebrity post. This gives you the best of both worlds, instant cache reads for most content and efficient handling of celebrities. Now let me show you how the hybrid approach works in code. First, we define a celebrity threshold. In this example, let's say it is 10,000 followers. In the create post function, after storing the post, we check the follower count. If the user has fewer than 10,000 followers, we enqueue a fanout job to push the post to all followers caches. If the user has 10,000 or more followers, they are a celebrity, so we skip the fanout and just add the post to a celebrity post cache. In the get feed function, we first get the cache feed, which contains all the push posts. Then we get the list of celebrities this user follows. For each celebrity, we pull their recent post from the celebrity post cache. Then we combine everything, sort by timestamp, and return the top 50. The key insight here is that hybrid approaches often beat pure strategies at scale. The push-only approach fails for celebrities. The pull-only approach fails for normal users. But combining both, we get a system that works for everyone. This is a pattern you will see repeatedly in production systems. Pure approaches work only in theory, but they break at scale. Hybrid approaches that adapt to different access patterns are what actually work. Now, modern feeds are not just chronological, they are ranked based on relevance and engagement. Let me walk you through how ranking works. There are multiple signals that influence ranking. Recency has high weight. Recent posts rank higher than the old post. This comes from the post timestamp. Engagement has high weight. Posts with a lot of likes and comments in the first hour rank higher. This is a strong signal that content is interesting. Relationship has medium weight. Posts from accounts that you interact with frequently rank higher than accounts you follow but never engage with. This comes from your interaction history. Content type has medium weight. Posts might rank higher than text-only posts based on what works best for engagement. User preferences have medium weight. If you always engage with certain types of content, you'll see more of that. In this rank feed function, we calculate a score for each post by combining these signals. For recency, we use an exponential decay function that decreases the score as the post gets older. A 24-hour-old post scores significantly lower than a 1-hour-old post. For engagement, we add a weighted sum of likes and comments. For relationship strength, we get an interaction score between the user and the post author and multiply it by a weight. After scoring all posts, we sort them by score descending and return the ranked feed. The key insight is that ranking adds complexity but dramatically improves user engagement. Users see content that is more relevant to them, which keeps them on the platform longer. I'll show you the caching architecture in more detail. At this scale, you need multiple layers of caching. The first layer is the client cache on the user's device. This provides instant loads when reopening the app. The second layer is CD and edge cache. This served cache responses close to users geographically. The third layer is the regional cache. This cache feeds at the regional level. The fourth layer is feed service cache. This is the main Redis cluster that stores pre-computed feeds. The fifth layer is the database, which is the source of truth. Now let me talk about cache invalidation, which is famously one of the two harder problems in computer science. In the onNewPost function, when a new post is created, we need to invalidate the feed caches for all the followers so they see the new content. We get the followers, we batch them into groups of 1,000 and enqueue async invalidation jobs. The invalidate feeds function simply deletes the cache feed for each user. The feed will be rebuilt on their next request. We also have a cache warming strategy. The warm active user feeds function runs periodically and pre-computes feeds for the most active users. This ensures that the active users almost always have a warm cache even after invalidation. The key insight is that at this scale, caching is not an optimization. It is an architectural requirement. Without aggressive caching, you cannot serve 10 billion feeds reads per day. Let me summarize the key production insights from this case study. So what has worked well is the hybrid fan-out approach handles reliabilities without delay while keeping feed reads instance for everyone. Redis cluster provides a sub-millisecond cache reads, which is essential for latency target. ASIC fan-out decouples the act of posting from the work or distributing followers. Users see their posts instantly, even if the fan-out takes longer. Multi-tier caching reduces the database load by 99%. Without this, we would need vastly more database capacity. Now, let's talk about what has required iteration. Hot partitions become a problem for celebrity feeds. The solution was a dedicated cache tier for high traffic accounts. Feed staleness caused complaints, so the solution was to implement stale while reviewed late approach, which serves the cache feed immediately while refreshing it in the background. Ranking latency was also too high when computed on every request, so the solution for that was to pre-compute rankings and update them asynchronously. Cache memory costs also grew quickly, so the solution for that was LRD eviction and tier storage, keeping hot feeds in fast storage and cold feeds in cheaper storage. The production principles we applied are: eventual consistency is acceptable for feeds, which opens up many optimization options. Cache aggressively, invalidate carefully. Hybrid approaches beat pure strategies. And use async processing for write-heavy operations. Now let us look at a very different system, which is payment processing. The requirements here are almost the opposite of social feeds. Let me walk you through the requirements. Consistency must be strong. Money cannot be lost or duplicated. Every transaction must be processed exactly once. Item potency is required, so if a request is retired due to a network timeout, it must not result in double charge. Charging someone twice is a terrible user experience and is potentially a legal issue. Durability must be 100%. You cannot lose transaction records. They are needed for reconciliation, auditing, and dispute resolution. Latency should be under 2 seconds for the 99th percentile. Users will tolerate a couple of seconds of payment processing, but not more. Availability target is 99.99%. Every minute of downtime is lost revenue. Additionally, there are significant constraints. PCI DSS compliance is required for handling credit card data. You need to support multiple payment providers like Stripe, PayPal, and others for redundancy and cost optimization. Multi-currency support is needed for global users, and fraud detection must be integrated. Regulation and requirements, they do vary by country, so this is a very different challenge from the social feed. Here, correctness is much more important than speed. Let me walk you through the architecture. Requests come from the checkout service to a payment orchestrator. The payment orchestrator is the brain of the system. It talks to an item potency store to prevent double charges. It talks to a payment gateway that can route to multiple providers like Stripe or PayPal. It integrates with fraud detection and records everything to a ledger for auditing. Let me explain the key design decisions. We use the synchronous processing rather than the asynchronous processing. For payments, you must confirm the charge is succeeded before confirming the order to the user. Asynchronous does not work here. The item potency store is at the orchestrated level, so we have a single source of truth for what has been processed. We integrate multiple payment providers for redundancy. If Stripe is down, we can fail over to another provider. We maintain a separate ledger for audit trail and reconciliation. This is separate from operational data. Every design decision here is about correctness and reliability. We sacrifice some simplicity and speed for guarantees that the money is handled correctly. Let me show you how item potency works in detail. This is critical for preventing double charges. In the payment orchestrator class over here, the process payment method starts by extracting the item potency key from the request. This key is typically generated by the client and sent with every retry of the same request. The first step is checking if this item potency key has already been processed. If it has, we simply return the stored response. The payment is not being processed again. If it has not been processed, we require a lock on the item potency key with a 30-second timeout. This prevents concurrent requests with the same key from both trying to process. After acquiring the lock, we double check that the payment was not processed while we are waiting for the lock. Then we actually execute the payment. If the payment succeeds, we store the result with 7-day TTL on the item potency key. That means retries with 7 days will return the same result. If the payment fails, we will store the result but with a shorter 1-hour TTL. This allows the user to try again with the same idempotency key after an hour if they want. The key insight is that this pattern guarantees explicit exactly once processing regardless of how many times the request is tried. Network timeouts, client retries, load balancer retries, none of them can cause a double charge now. Processing is essentially a state machine. A payment moves through defined states and only certain transitions are valid. The states are created, processing, authorized, captured, settled, failed, and voided and refunded. The valid transitions are strictly defined. From created, you can only go to processing. From processing, you can go to the authorized or failed. From authorized, you can go to captured or voided. From captured, you can go to settled or refunded. From settled, you can still go to refunded. In the payment class, we define these valid transactions explicitly. As you can see in the code over here, in class we define these valid transitions explicitly. The transition to method checks if the request transition is valid. If someone tries to transition from created directly to captured, that is invalid and we raise an error. When a valid transaction do happen, we record it in the state history with timestamps and we write it to the ledger so we have an audit trail of every state change. The state machine approach has several benefits. It makes the payment lifecycle explicit and documented. It prevents invalid operations like capturing a failed payment. It creates a clear audit trail as well. And it also makes the system easier to reason about and debug. The key insight is that for critical financial systems, making the state machine explicit is essential. It is too easy to have bugs where payments end up in inconsistent states otherwise. Payments fail for many reasons. Let me walk you through how to handle different payment failure scenarios. For network timeout, the right action is to retry with the same idempotency key. The idempotency store ensures you will not double charge. Either the original request succeeded and you get that response back, or it failed and you retry back. For provider down, the right action is to fail over to a backup provider. This is why we integrate multiple providers. For card decline, the right action is to return the error to the user. There is nothing to retry here, so the card does not have sufficient funds or is invalid. For fraud detected, the right action is to hold the payment and queue it for manual review. For unknown errors, the right action is to queue for manual review, so do not guess. Now let me show you how provider failover works. In the payment gateway class over here, we have a list of providers in priority orders: Stripe, then Aiden, then Braintree. The charge method iterates through providers. For each one, it first checks if the provider is currently marked healthy. If not, it skips to the next. If the provider is healthy, we try to charge. If it succeeds, we return. If we get a provider unavailable error, we mark that provider as unhealthy and continue to the next. Critically, if we get a card declined error, we do not retry with another provider. A declined card is declined everywhere mostly. If all providers fail, we raise an alarm, indicating no provider could process a payment. The failover logic is what enables the 99.99% availability despite the individual provider outages. Now, reconciliation is how you ensure your books match the payment provider's books. This is critical for financial correctness. In the reconciliation class here, the daily reconciliation method compares the internal ledger with each provider's records. For each provider, you get all the transactions your system has recorded for that provider on that date. Then you get that settlement return report from the provider, which is what they recorded. And then you compare. For each transaction in your records, you look for a matching transaction in the provider's records. If a transaction exists in your records but not in provider records, that is a discrepancy of type missing at provider. This could indicate a failed charge that your system thought was succeeded. If a transaction exists in both but the amounts do not match, that is an amount mismatch discrepancy. This is pretty rare but serious when it happens. If there are any discrepancies, you alert the finance team for investigation. Reconciliation typically happens daily for the previous day's transactions because providers need time to finalize their settlement reports. This is called T1 plus reconciliation. The key insight is that in payment systems, you cannot just trust that everything worked. You need verification. Reconciliation catches issues that would otherwise go unnoticed until a customer complains or an audit finds them. Now let me summarize the key production insights from the payment processing case study. So what has worked well? Idempotency keys resulted in zero double charges. This is the kind of guarantee you need for financial systems. The explicit state machine made the payment lifecycle clear, debuggable, and auditable. Multiple providers enabled 99.99% availability despite individual provider outages. Maintaining a separate ledger made auditing and reconciliation straightforward. Now let's talk about what would have required iteration. Things like, let's say, provider latency variance would have caused issues. Different providers have different response times. The solution was dynamic timeouts per provider rather than one global timeout. Second, reconciliation delays caused confusion. So if that happens, the solution was to implement T+1 reconciliation with proactive alerts when discrepancies were detected. Now, another thing that happens pretty common is distinguishing fraud from legitimate declines, which is pretty difficult. The solution for that was continuous ML model tuning based on the feedback. Another issue that happens quite a bit is multi-currency complexity grows over time. The solution for this is a dedicated currency service that handles exchange rates and formatting. And these are the production principles that we applied. Strong consistency is mandatory for financial operations. Idempotency is not optional. Every operation must be idempotent. Defense is depth with multiple providers ensure the reliability. And you should be auditing everything. You need the records to be auditable at all times. Now let's look at our third case study, which is real-time chat. This presents yet another set of challenges. The requirements are message delivery latency should be under 100 milliseconds at the 99th percentile. Chat needs to feel instant. Any noticeable delay breaks the experience. Message ordering must be guaranteed per conversation. If Alice, let's say a person sends a message A, then message B, then message C, the receiver, let's say Bob, must receive them in order. Presence updates should reflect within 2 seconds. When someone comes online or goes offline, their contact should see the change quickly. History sync must be instant as well on reconnect, so if the user closes the app and reopens, they should see all the messages they miss immediately. Offline support is required. Messages sent while a user is offline should be delivered when they come back online. Also, the scale is pretty significant. If you look at it, the requirements are ideally for a chat system like 50 million concurrent connections, 10 billion messages per day, 1 million messages per second at peak. The combination of low latency requirements and massive concurrent connections makes this a challenging system to build. Now let me walk you through the architecture. Clients connect to WebSocket gateways, which maintain the persistent connections. The WebSocket gateways talk to the chat service for message handling. The chat service writes messages to a message queue for durability, which then stores them in a message store. The chat service also talks to the presence service for tracking who is online, which uses the presence cache. Let me show you how connection management works. The WebSocket gateway class maintains a map of user ID to connection and a map of user ID to which server are connected to. When a user connects, the onConnect method stores the connection locally. Then it registers in a distributed registry recording which server this user is connected to. This is important because when someone sends a message to the user, we need to know which server to deliver it to. Finally, we publish to the presence service that user is online. When a user disconnects, the onDisconnect method removes their connection locally and from the distributed registry. For presence, we set the status to offline with a delay. The delay is important because users often reconnect quickly, like when switching between Wi-Fi and cellular. We do not want to show them going offline and online repeatedly. The architecture is designed for the specific challenges of real-time messaging. Maintaining millions of persistent connections, routing messages to the right server, and tracking presence accurately is pretty important. Now let me show you how message delivery works. In the chat service class over here, the send message method first generates a message ID using a Snowflake ID generator. Snowflake IDs are ordered and unique, which is important for message ordering. Then we construct the message object with the ID, sender, conversation, content, and timestamp. The next step is critical. We persist the message first. Durability comes before delivery. If the server crashes after the delivery but before persistence, the message would be lost. By persisting first, we guarantee the message is saved. Then we get the list of members in this conversation and deliver to each one. The deliver to user method first checks the registry to see which server the user is connected to. If they are connected somewhere, we push the message to that server for delivery. If they are not connected, meaning they are offline, we enqueue the message for later delivery when they do come back online. The offline queue is important. Messages are not just lost because someone's phone lost connectivity. They are queued and delivered when the user reconnects. The key inside is here is persistence. So in any durable messaging system, you must use persistence before confirming delivery. Otherwise, messages can be lost. Guaranteeing messaging order is trickier than it sounds. So let me explain the problem. If a person, let's say name Alice, sends messages A, then B, then C, she expects the receiver, let's say Bob, to see them in that order. But in a distributed system, messages can arrive out of order due to different network paths, load balancer distribution, and race conditions. So now the receiver Bob might receive A, then message B, then after that they might receive the message B. This is confusing and breaks the conversation flow. The solution to this is to use sequence numbers. The conversation sequencer class over here provides an atomic increment for each conversation. Every message in conversation gets this next sequence number. So in the chat service, when creating a message, we get the sequence number and include in the message object. So on the client side, the chat client tracks the last sequence number it has received for each conversation. When a message arrives, it checks if this is an expected next sequence number. If yes, then display the message and update the last sequence number. If the sequence number is higher than expected, that means we missed some messages. The client fetches the receiving messages from the server before displaying. This approach guarantees the ordering at the client even if messages arrive out of order from the network. The client reconstructs the correct order using the sequence numbers. Now let me explain the presence system, which shows who is online. The presence service class uses a Redis cache and a heartbeat interval of 20-30 seconds. The setOnline method stores a key in Redis with a TTL of twice the heartbeat interval, so 60 seconds. Then it publishes the presence change event, refreshes the TTL on existing key. As long as the client keeps sending heartbeats, they stay online. If a client stops sending heartbeats, the key expires after 60 seconds and they automatically go offline. This handles cases where the client crashes or loses connectivity without sending a clean disconnect. The isOnline method here simply checks if the presence key exists. The getOnlineFriends method here is where things get more interesting. To show which of your friends are online, you need to check the presence of potentially hundreds of users. We use a Redis pipeline to bash these checks, get all friends, create a pipeline, check the existence for each, execute the pipeline, and return the friends whose keys exist. This batch approach is essential for performance. Without it, checking 200 friends would be 200 round trips to Redis. The presence becomes a scaling challenge at large scale. Let me walk you through the math. With 50 million users online, each with an average of let's say 200 friends, if everyone checks their friend's presence every 30 seconds, that is 50 million times 200 divided by 30, which equals to 333 million presence checks per second. That is not sustainable at all. The solution for that is presence bucketing. In the scalable presence class, we partition the presence data into 10,000 buckets. The getBucket method here assigns each user to a bucket based on a hash of the user ID. Instead of subscribing to presence changes for each individual friend, the subscribe to friends method groups friends by buckets and subscribes to the relevant buckets. If your friends are spread across 50 buckets, you subscribe to 50 bucket channels instead of 200 individual channels. When a user's presence changes, the onPresence change method publishes to that user's bucket. All subscribers to that bucket receive the update, filter it to see if it is someone they care about, and update accordingly. The bucketing approach dramatically reduces the number of subscriptions and publications needed. So instead of millions of individual channels, you have thousands of buckets, each handling a subset of users. The key insight is that the presence is a classic fan-out problem, and bucketing is a standard solution for reducing fan-out at scale. Now let me summarize the key production insights from a real-time chat case study. So what has worked well is like WebSocket with HTTP fallback provides universal connectivity. Some networks and proxies do not support WebSocket, so having a fallback ensures everyone can connect. Sequence numbers guarantee the message ordering regardless of network behavior. Offline queuing means no messages are lost even when the users have intermittent connectivity. Presence bucketing makes presence scalable to millions of users. Now let's talk about what would have required iteration. Connection thundering herd was a problem, so when a service restarts, all the clients would have tried to reconnect simultaneously. The solution for this would have been jitter reconnect, where clients wait a random delay before reconnecting. Memory per connection also can be growing too high, so the solution would have been to have the connection pooling and optimizing what state is kept per connection. Cross-region message delivery can also have high latency, so the solution for that would have been regional routing, keeping messages within a region when possible. And the read receipts at scale also, can create too much traffic. So the solution for that would have been batching and delaying read receipts rather than sending them instantly. So these are the production principles we have applied. Asynchronous for delivery, but synchronous for critical path or acknowledging to the sender. Idempotent message handling with deduplication at the client. Graceful degradation, which is like presence is optional, but the core chat functionality can work without it. And the client-side ordering reconstruction handles the network out-of-order delivery. Now let us step back and let's look at the patterns that have emerged across all these three case studies. The first pattern is hybrid strategies. For the feed, we use hybrid fan-out combining push and pull. For payments, we use multiple providers. For chat, we use WebSocket plus HTTP fallback. The lessons is that the pure approaches rarely work at scale. You need to combine strategies based on access patterns. The second pattern is eventual consistency where acceptable. For the feed, eventual consistency is fine. Users can tolerate a slightly stale feed. For payments, strong consistency is required. You cannot have eventual consistency for money. For chat, eventual consistency is fine with ordering guarantees within a conversation. The lessons is to choose consistency based on business requirements, not technical preference. Do not use strong consistency everywhere just because it seems safer. The third pattern is asynchronous for scale. For the feed, we use async fanout for post distribution. For payments, we use asynchronous for charge itself but asynchronous for notifications. And for chat, we use asynchronous for delivery but synchronous for the send acknowledgement back to the sender. The lesson is to move work out of the critical path where possible. Asynchronous processing lets you decouple and scale. The fourth pattern is cache everything. For the feed, we use multi-tier caching at every level. For payments, we use an idempotency cache to prevent double processing. For chat, we use presence cache and message cache. The lesson is that scale caching is not an optimization. It is an architecture requirement. You cannot serve billions of requests hitting your database every time. The fifth pattern is idempotency everywhere. For the feed, we detect a duplicate post. For the payment, we use idempotency keys. For chat, we deduplicate the messages at the client. So the lesson is that at scale, every operation will be retired. So network issues, load balancer retries, client retries, they all do happen and make everything idempotent so retries are safe. The sixth pattern is observability is not optional. All three systems need request tracing to follow requests through the system. They need error tracking to find and fix the issues. They need performance metrics to understand latency and throughput. And they need business metrics to understand the user behavior. The lesson is that you cannot operate what you cannot observe. Invest in the observability from the start. The final section, let me recap everything we have covered so far in this course. The course followed a progression from foundations through data, reliability, operations, and scale. In the earlier sections 1 and 2, we had covered foundations. The key concept was developing a production mindset and understanding the architecture boundaries. In the next section followed by that, we covered data, so we key concepts like schema evolution, replication, and consistency trade-offs. In section after that, we covered asynchronous patterns, which is key concepts for like caching, queues, and eventual consistency. The section after that, we covered reliability, so key concepts for like timeouts, retries, and circuit breakers. And after that, we covered observability, which were key concepts for logs, metrics, and traces. Then we also covered deployment, so key concepts for like CI/CD, deployment strategies, and feature flags. And then we covered security, so key concepts we covered were authentication, secrets management, and defense in depth. Also, we covered cost, so for that we covered right sizing and optimization strategies, and then we followed up that with multi-region section where we covered key concepts like global scale and data sovereignty. After that, we covered incident management, in which we covered detection, response, and postmortems, and then we just covered case studies applying everything to real-world systems. Let me articulate the shift in thinking this course represents. Before this course, a typical approach would be to design the happy path, assume services are available, optimize for features, and deploy and move on. But after this course, I want you to follow approaches like where you should be designing for failure. You should assume that everything in production will fail at some point. You should optimize for reliability first, and you should understand that deployment is just the beginning. Let me contrast the interview focus versus the production focus. In interviews, the focus is more on functional requirements. What features does the system need? However, in production, the focus is more on the non-functional requirements. What availability, latency, and throughput does the system need? In interviews, the focus is on feature completeness. So, for example, does the design handle all the use cases? Whereas in production, the focus is on operational excellence. Can we deploy, monitor, debug, and evolve the system? In interview, the focus is also on best case performance. So, for example, how fast can this be? In production, the focus is on worst case handling, like for example, what happens when things fail. And in interview, the focus is also on initial design, like here's the architecture. In production, the focus is more on evolution over time. How do we change this safely and grow the system over time? The shift in mindset is what separates engineers who build systems that work in smaller scale versus systems that build on global scale in production. Most important principles we covered. For reliability, first, every external calls needs a timeout. Without a timeout, one slow dependency can bring down your whole system. Second, retries need backoff and jitter. Without a backoff, retries can overwhelm a struggling service. Without jitter, retries synchronize and create thundering herd problem. Third, circuit breakers prevent cascade failures. When a dependency is failing, stop calling it and you should fail fast instead. Fourth, graceful degradation beats total failure. Saving partial functionality is better than serving errors. Now for data, first, schema changes need careful coordination. You should be using expand contract patterns to avoid breaking changes. Second, replication lag is a feature, not a bug. Understand it and design for it. Third, choose consistency based on business needs. Strong consistency has cost. Use it when required, not everywhere. Fourth, backups must be tested. An untested backup is not really a backup. For operations, first, you cannot fix what you cannot see. Observability is super important. Second, you should be alerting on symptoms, not on causes. Alert when the users are affected, not when the metrics look weird. Third, blameless postmortems improve systems. Focus on the systematic issues, not the individual blame. Fourth, automate everything you do twice. So, for example, toil does not scale. Now, for scale, you should first cache aggressively, invalidate carefully. Caching is essential at scale, but cache invalidation is where bugs live. Second, asynchronous processing decouples and scales. You should move work out of the critical path. Third, partition data to distribute load. No single node can handle everything. Fourth, multi-region is 2 to 3 times more complexity. Make sure you need it before committing. Now for security, here first, the defense in depth is always important. So multiple layers of security is important. Second, secrets never, should be in the code. You should be using secret managers. Third, zero trust networking. Verify everything and assume nothing. Fourth, audit everything. So you should, you need the records, you should have them. Now for the cost section, the first is important point is visibility enables optimization. You cannot optimize what you cannot measure. Second, right size based on the actual usage. Do not provision for imagined peaks. Third, reserve the baseline capacity. Use on demand for burst. This optimizes cost while handling variability. Fourth, architecture drives cost. Sometimes the cheapest change is an architecture change. These principles are not just theory. They emerge from real systems, real failures, and real lessons learned in production. So please keep them in mind when you are building systems in production. Let me give you some practical guidance on how to demonstrate production knowledge in system design interviews. When discussing architecture, you should say something like, okay, before diving into the design, let me clarify the production requirements. What is the availability target? What is the latency acceptable? What consistency guarantees do we need? This shows you understanding that non-functional requirements drive architectural decisions. When discussing data, you should mention the expand contract pattern for schema changes. You can say that, okay, for schema changes, I would use the expand contract pattern to ensure zero downtime migrations. We would also add the new column as nullable, backfill data in batches, and then migrate the code. This shows you understand how to evolve production systems safely. When discussing reliability, you should mention timeouts, circuit breakers, retries, and idempotency. You can say things like, okay, all external cords would have timeouts and circuit breakers. We would implement exponential backoff with jitter for retries, and all operations would be idempotent to handle duplicates. This shows you think about failure modes and resilience, and this is super important in interviews. When discussing caching, you should show depth beyond just adding a cache. You can say, I would use a cache aside pattern with ETL-based invalidation for most data. For the celebrity use cases, we might need key salting or dedicated cache tiers to handle hot partitions. This shows you understand cache invalidation strategies and hot partition problems. When discussing deployment, you should mention Canary Deployments, automated rollback, and feature flags. You can say that, okay, I would use Canary Deployments with automated rollbacks based on error rate and latency metrics. Feature flags would let us decouple deployment from release and enable the gradual rollouts. This shows you understand the safe deployment practices. So when discussing monitoring, you should mention specific methodologies. Like you can say that, okay, we would implement the read method for request metrics and the use method for resources. Every request would have a trace ID for correlation across services, and we would allow them symptoms, not causes. This would show them that, okay, you understand observability best practices. These are the kind of answers that demonstrate production experience and set you apart from candidates who might not have that much experience in production. So make sure you display all these best practices. Or not to say, because these are common interview red flags. You should not be saying that, okay, we'll just add a cache without discussing invalidation, TTL, or thundering herd protection. That shows that you have not thought through the complications. You should also not say that, okay, we will just retry on failure without discussing back off, high potency, or retry budget. That shows you that you do understand, okay, retries can make things worse, so you need to do them carefully. Then also do not say that we'll use a message queue without discussing ordering guarantees, delivery guarantees, and dead letter queues. This shows shallow understanding if you don't mention those things. Also, do not say that, okay, we'll just deploy the new version without discussing important things like rollback strategy, canary deployment, or feature flags. Also, do not say that, okay, we'll replicate to another region without discussing the consistency models, config resolution, or latency implications. This shows that you understand multi-regions properly. Instead, you should also be showing depth. A good answer about caching sounds like, okay, we'll use caching with a 5-minute ETL, stale validate for thundering herd protection, and explicit invalidation for on writes for critical consistency. See, the deep answer addresses complications that make caching hard, which makes it more realistic, and that's how things works in production. And use some resources to add more addition to your learning. So for example, you should definitely consider reading these books. For system design, you should read Designing Data Intensive Applications by Martin Klebman. It's a very big resource on data systems. For reliability, you should definitely consider reading Site Reliability Engineering from Google. It essentially defines the SRE discipline. For distributed systems, Martin Klebman also has excellent resources. For operation, you should read the DevOps Handbook for practical guidance and operational experience excellence. For practice, you should first build systems end to end. Do not just design on paper. You should be building actual working systems. Second, run things in production. Even with the personal projects, the learning comes from operating, not just building. Third, break things intentionally. Chaos engineering teaches you how your systems really behave under stress. Fourth, read the postmortems from major companies. They publish detailed analysis of their failures, so learn from them. And you should contribute to open source infrastructure when possible. Working on widely used systems will actually teach you a lot. For communities, you should follow engineering blogs from Netflix, Uber, Stripe, and similar companies. They publish great content about their systems. You should also join SRE and DevOps communities, and you should attend meetups and conferences. And you should yourself share your learnings. Teaching actually reinforces your learning. Now let me share some final thoughts on building production systems. So the journey looks something like this. On day 1, it works on my machine. On day 100, it works in staging. On day 500, it works most of the time. And on day 1000, it works reliably at scale. On day 5000, it works reliably at scale, cost effectively, with minimal on-call burden. The late stage is where you would want to be, but getting there takes years of iteration and learning. The reality is that production systems are never done. They evolve, scale, and require continuous attention. The best engineers are not the ones who build perfectly the first time. They are the ones who build systems that can evolve safely over time. There is a saying I love. In theory, there is no difference between theory and practice. In practice, there is. Production is where theory meets the reality. Systems that do look beautiful on a whiteboard, they kind of fall apart in production. So when they hit the real traffic, real failures, and real users, you should embrace the complexity. This is where the interesting engineering happens. Recap what we have covered in this course. So you have learned how to design product systems that survive production, not just systems that work in demos, but also systems that handle failures, scale to demand, and remain stable under pressure. You have also learned in this course how to evolve systems safely over time, schema migrations, deployment strategies, feature flags, the tools you need to change running systems without breaking them. In this course, we also learned about how to operate systems at scale, which is observability, incident response, and on-call, the practices that keep the systems running. And we also talked about how to do production system design interviews, so how to demonstrate depth and experience that sets you apart. The key message is this: The gap between it works and it works in production is where engineering excellence happens. Anyone can build something that works once. Building something that works reliably at scale, day after day, through failures and changes is real engineering. Now you have the knowledge to bridge that gap. So the next step should be first apply these principles in your current work, starting with one thing. Let's say you add timeouts, improve your monitoring, or implement circuit breakers. Second, practical system design, with production focus. When you design systems, think about failures, operations, and evolution. Third, share learnings with others. Teaching is the best way to solidify your own understanding as well. Fourth, keep learning and iterating. This course is the foundation, so let's keep building on top and keep learning as we go along. Thank you for watching this. Take care.